I have the distinct privilege of welcoming you to CEDAR and giving you a very short introduction to what CEDAR is all about. First, let me tell you that I am live from the beautiful Front Range of the Rockies, and I'd like to introduce the student workshop team and a large fraction of the CEDAR leadership team. I am finishing my term as the CEDAR Science Steering Committee Chair. That means we get to do the meeting planning and generally steer the science that goes on within the CEDAR community. Astrid is Mata. I think you've probably interacted with her. She sends out all of the emails and generally keeps everything on track for the entire CEDAR community all year. Larissa Goncharenko is our incoming CEDAR Steering Committee Chair. And you've already heard from Komal and Megan. Megan was saying that we're replacing Komal, but I think Komal is irreplaceable. But we can't have a situation where we have irreplaceable people. So we want you to be the next irreplaceable person as a CEDAR student representative. So what is CEDAR? It stands for Coupling, Energetics, and Dynamics of Atmospheric Regions. It has a physical domain, which covers essentially the entire realm of spheres that are gravitationally associated with Earth, from the troposphere all the way up through the thermosphere and its embedded ionosphere. And then all the way up to the exosphere, which then links into places that we call spheres because they're spheres of interaction, but they're not very spherical. They're more bullet shaped or maybe torus shaped. So our spheres of influence are embedded within a much larger geospace and solar system, true system. So we work, the CEDAR community does, at the Space Interaction region. Our primary start in this business over 30 years ago was dealing with the aeronomy, essentially the chemistry that allows these regions to couple, and also the wave and field coupling, which I know you're going to learn more about. If I were to try and go for a bookshelf, where would I find CEDAR? Well, we're right here in the middle with aeronomy and space weather. We're bookended by meteorology and by particles and plasma in the space region. Certainly solar studies are important for helping us understand the driving, and we definitely are linked into the earth sciences. About 10 years ago, a previous CEDAR Science Steering Committee worked with the entire community to come up with 6 strategic thrusts that have taken us through this decade. We did a community survey a couple of years ago and basically reaffirmed that these are the areas we want to continue working on up through the time that we start our participation in the upcoming decadal survey, which you will hear more about on Tuesday morning's workshop. What we have been doing is we've made a lot of progress in these two in the middle and top right, exploring exchange processes and processes related to geospace evolution. At this meeting, I think you're going to hear more about this middle and bottom right, managing and mining the incredible amount of data that we have and helping us to know how that fuses across disciplines. And then where we have progress yet to make is developing the observational and instrumentation strategies so that we can look at the full coupled geospace system. And certainly that then will allow us and encourage us to undertake a systems perspective to geospace. You're going to hear just a sea of words, people talking about all of these spheres of influence in plasma and physics. So there are places that we talk about in CEDAR. There are certainly processes that help us understand what the connection and coupling is. We are very much moving into a realm where we are cross-disciplinary. You will hear speakers in the meeting who are also talking about the Geospace Environmental Modeling effort, which is a sister supported scientific group in National Science Foundation. You're going to hear a lot about measurements and the data science that help us understand what those measurements mean. And then ultimately, we want to apply those to give ourselves a much bigger, more holistic view of what is happening in our system. I do know, however, that it can be pretty intimidating to hear all of these words coming at you almost from a fire hose. So one of the things that I did last year was to ask for some help in creating a bookshelf for CEDAR. So in this link down here, which I may update a bit later this summer, we've listed about 40 texts that are relevant to CEDAR. They cover these areas that I have already mentioned, and at the end provide some additional references. Like I said, over the year, those references probably need a little bit of an update, and we'll try and get that update in and provide it to this CEDAR student newsletter. So let me end by commenting about the effort that Mack Jones is going to talk about right after lunch. And it is an effort that has become, that touches everything we do in CEDAR, and that is the idea of diversity, equity, and inclusion. And put into action, that means inclusion and respect. You know, we are running a grand experiment right now, providing free access supported by the National Science Foundation and CEDAR for 200 students today, and then a much larger community across the next week to engage in a virtual mix. That virtual mix means that we've also got a virtual mix of cultures. We are crossing time zones and boundaries and cultures. We're crossing many levels of expertise. And some people may find some words that are used perhaps a bit more sensitive. I hope that's not the case, since we'll probably be talking almost exclusively about science. But I do ask you to think about the words that you use and maybe the pronouns that you use if someone asks specifically to be addressed by a specific pronoun. I want to welcome you again and really encourage you to engage via the Slack channel and Slido, and also really to participate in the DEI plenary and workshop that will go on later this week. In doing that over the past year, it has been absolutely eye-opening. I'm also working on a DEI initiatives within my institution. It really has been a learning experience. And I suppose it's a learning experience that's better late than never. So I encourage you to jump in early. If you do experience anything that is inappropriate behavior, you can go to this virtual code of conduct. That's where the information is to report any behavior that's unacceptable or unwelcome. And certainly you are willing, you're more than willing to contact me as well. So I encourage you to learn, communicate, share, and enjoy this moment. And I'll just finish off by again showing you this team and leaving you with my email address in the event that you do need to contact me. So welcome to CEDAR. I'll be on and off most of the day today, and hope to be participating via Slido and just engaging and meeting a whole bunch of new students. By the way, I was a student myself. In 1987 was my first CEDAR student experience. It has changed, but it's still such a fundamentally great community to work in. Thank you so much, and I'm turning it over to the next speaker.
Thank you so much, Delores, for that wonderful introduction. Now we will start our feature presentation. In this lightning round, we're going back to the basics on instrumentation and techniques. There will be 7 talks total, with talks on ISR, meteor radars, LIDAR, rockets, optical instrumentation, CubeSats, and GNSS. Our first talk today is by Dr. Ashton Reimer on ISR. Dr. Ashton Reimer is a research engineer in the Center for Geospace Studies at SRI International in Menlo Park, California. Dr. Reimer earned his PhD in physics and engineering physics at the University of Saskatchewan, Canada in 2018. Beginning in November 2016, Dr. Reimer joined the Advanced Modular Incoherent Scatter Radar, better known as AMISR, operations and maintenance team at SRI, where to this day he maintains and oversees the data processing, distribution, and archival systems while supporting other related engineering tasks and user science. Let's hear from Dr. Reimer.
Hello, my name is Dr. Ashton Reimer. I'm a research engineer at SRI International, and today I'm going to talk about incoherent scatter radar. So at SRI, I primarily work on the Advanced Modular Incoherent Scatter Radar project, or AMISR, and I'm in charge of all the data processing, distribution, and archiving for the project. In the background of this title slide, you can see one of the radars that we maintain as part of the AMISR project. This is the Resolute Bay Incoherent Scatter Radar up in northern Canada. So first, let's review some of the objectives of this talk. We're going to look at ISR as basically a black box, just kind of peek at some of the bits and pieces of it, the essential fundamentals of the technique, and as well as review a little bit of the signal processing, so you have a sense for how we get the data that is then used to do science. So as part of that, we'll then talk a little bit about data access and a little bit of the science you can do with ISR data. So at the end of the talk, you should understand some of the basics of the incoherent scatter radar technique and how you might be able to use ISR for your own research. So first, what does an incoherent scatter radar look like? Well, they're big, usually. They're quite large instruments. And so here's a picture of the MIT Haystack Millstone Hill incoherent scatter radars. There's the steerable antenna here, single dish that's movable, and a fixed zenith pointing or vertical pointing antenna in the back. And so, you can see some of these buildings. There's a little door there, right? There's a car, some cars in the background. They're quite large antennas, right? We're talking tens of meters across. And so this is one type of incoherent scatter radar, what they look like. And here's another. This is a phased array type radar. So what you're seeing here on the face are a bunch of different antennas in an array. And the way that you are able to steer these radars is by changing the phase between all the antennas electronically. And so then we're able to point beams electronically instead of having to move a large structure around to point. This particular radar here is the Poker Flat Incoherent Scatter Radar located in Alaska. This is one of the AMISRs. So in short, if you don't take anything else away from the rest of the presentation I'm going to get, I think this slide here summarizes everything pretty nicely. So the ISR technique itself is a very powerful remote sensing technique, right? We require large radars, right? Large antenna apertures. We also require quite large transmit powers, and we'll see why in subsequent slides. In order to do the data processing, to extract out the physical parameters that we want, the plasma parameters, we need to have some theory, some model, and we have ISR theory that tells us how we can get the measurements that the radar makes as a function of these plasma parameters, and therefore infer those plasma parameters. Of course, that also requires some assumptions. And so then using this incoherent scatter radar data, specifically the most common data products people look at are the electron density, denoted NE, the electron temperature, TE, the ion temperature, TI, and the line of sight velocity, which is the velocity in the medium projected into the look direction, the radar beam. So it's the projection of the velocity along the line of sight, hence line of sight velocity. Using these data products, we're able to study a large variety of different phenomena, right? Including plasma instabilities. We look at spatial gradients in the plasma, particle precipitation. You can see the upflow of ions into the upper altitudes of the ionosphere. We can look at conductivity, Joule heating, a whole bunch of different things. We can even look at meteor echoes, infer neutral winds from their effect they have on the ions in the lower E region, and look at large databases of incoherent scatter radar measurements over years, over solar cycles, and start to look at some of the climatology of all these things. So really quickly, before we jump into the ISR theory, I wanted to review some fundamentals of instrumentation. These are instruments. And so when I talk about measurements, I'm meaning things that are directly recorded by the radars. So in this case, the radar actually measures voltage samples. We transmit some electromagnetic radiation, and the signal we get back is converted into voltage samples by the voltages by the antennas, and then we sample that voltage using an analog to digital converter. Observations or observables are things that we can estimate from the measurements using some physics. So in this case, our physics is incoherent scatter radar theory, and that allows us to get the plasma parameters, electron density, temperatures, and velocity. And so there's these other two concepts that I'd like to introduce. One's called a Ford model. So a Ford model is basically a function f that contains all the physics we need to predict our measurements y, given our observations or observables p. So if we know our plasma parameters, then f allows us to predict what the measurements the radar would see. And so that's the kind of thing we want to do. We want to solve this inverse problem. If we know the physics and we have the measurements, how do we get our plasma parameters? So that's what we're going to try to do here, is work towards that. Briefly, we'll talk a little bit about radar. I just want to highlight the radar equation here and point out that the radar equation tells us what the received power is as a function of our power we transmit, the antenna gain on transmit, the antenna gain on receive. This is the effective receive area, which is related to the gain. We have some R squared losses terms, and we also have this radar cross section. And the ISR theory tells us what this radar cross section is. There's also two different regimes of radar that you'll probably hear about. One is called hard target radar, where you have a target that doesn't fill the beam. The other is soft target radar, or volume filling it. The target you're scattering off, getting scattered signal off of, is filling the entire beam that the radar is making. So incoherent scatter, what is it? It is extremely weak scatter from electrons in the plasma. If you think about what a plasma is, it's a collection of electrons and ions. If you scatter off of a single electron, that's what's known as Thomson scatter, and it has a ridiculously small cross section, right? I mean, it's a single electron. But remember, we said we have a beam and the plasma is distributed. So that beam from the radar is actually filled with plasma. And so we have this volume filling this soft target. And that means we have many, many, many electrons, right? Filling that beam, and that increases our cross section and allows us to actually do this. When you work through the ISR theory, you end up with two limits. One's non-collective limit, where there's no collective interaction between the ions and the electrons that you can see. And in that case, all you're seeing is the motion of the electrons. And so the cross section ends up being like this. In the collective limit, you actually have information about the ions encoded in the motion of the electrons that you can see. And then you end up with a cross section that looks like this. One thing to highlight is that in that case, you end up with this temperature ratio term in the denominator here. And this, depending on the electron and ion temperature, then that actually changes the cross section. And just one quick thing to note, when we do ISR, we're transmitting about a megawatt, and based on these cross section formulas that ISR theory gives us, we only get about 10 femtowatts back. So when they say extremely weak, this is what they mean. So ISR theory predicts a power spectrum which is related to an autocorrelation function via Fourier transform, and we can actually estimate. We can get the autocorrelation function from the voltage samples we measure. So if ES here is a voltage sample, or are the voltage samples, then we can take the voltage samples the radar actually measures, calculate an autocorrelation function, and now we can predict that autocorrelation function as a function of these plasma parameters. The power spectrum ISR theory predicts looks something like this. It's this double humped spectrum denoted in this cartoon. And you can see how the shape of that spectrum varies as a function of the plasma parameters. If you look at an altitude profile of the electron density, so we get altitude here on the right, or on the left, sorry, and then this is the electron density magnitude on the x-axis. You have some increasing and decreasing profile. You can see how the spectrum changes. So as the density increases, these plasma lines, these outrigger lines here, increase in separation and frequency, as well as the area under the curve for the ion line increases and then decreases. So that's ISR theory in a nutshell. Now we want to try to create a forward model so that we can take our measurements and that the radar makes and extract out the ionospheric parameters. But we have to remember that the radar is a real instrument making a real measurement, and how we measure things often affects what we measure. And in the case of a radar, we have to transmit a finite length pulse, right? And that pulse actually smears out what we observed, and that or blurs it. And so that's known as ambiguity. In the plot here, I am showing how that finite pulse length creates a smearing, or sort of you can think of it almost like a running average. And so the real electron density profile, this blue one here, has this nice E region feature that gets smeared out by the pulse, right? And so if we want to get the plasma parameters out, what we need to do is construct a forward model that includes the ISR theory, but also a measurement model, an instrument model. And so then once we have that, if we can compare our measurements to modeled measurements. And so we have our voltages that we measured, we construct some autocorrelation function lag estimates, and then we will compare them to some modeled autocorrelation function lag estimates. And so we start with some initial guess notionally of what we think the plasma parameters might be, crank that through the ISR theory to predict the spectrum, Fourier transform that, apply the ambiguity to get our modeled lags, and we compare them in some way, and then we can update what our initial guess was based on how these things compare. And the typical way to do this cycle is using a technique called least squares regression. There are other techniques as well that can be used, but the most common is the least squares regression. Now, all of this comes with some assumptions. The ISR theory isn't just a function of the electron density and the temperatures in that, it's also a function of ion composition, collision frequencies, assuming things are Maxwellian, the plasma is in thermal equilibrium. There's magnetized ISR theory, unmagnetized ISR theory, that kind of stuff. So the plasma parameters you're looking at will have some of these assumptions kind of baked into the analysis that was done to obtain them. And that's just something you should be aware of. So if you want to know more about those assumptions, you should contact the facility who you got the data from. So speaking of data, obtaining ISR data is actually quite easy. You just go to Madrigal, this Madrigal database. It's a distributed database. Each facility feeds their incoherent scatter radar data into it, and you just have to click on this access data and you can grab it. When you're using Madrigal, there's sort of two terms that you'll likely encounter. You want to look at the calibrated data. Another thing is this uncorrected term. This just means that the electron density that was obtained, they obtained it in a way that didn't include that temperature correction factor that we saw in the cross section. And so this is what some of that data will look like. If you look at incoherent scatter radar data, we have our electron density in the top panel, electron temperature, ion temperature, and line of sight velocity. These are so-called range time intensity plots. We have altitude on the left, on the y-axis, time on the right axis, and you can see how the electron density and the electron temperature are changing as a function of time of day. This is 2 days worth of data, and so you can see it's increasing during the day, decreasing at night, increasing during the day, kind of a thing. There's also derived data products. In this case, we have derived electric fields from the Pfizer data, the Poker Flat Incoherent Scatter Radar. So we can actually estimate the electric fields in the F region from all the individual line of sight velocity measurements. And so all of this data allows incoherent scatter radars to provide significant scientific utility. Here's just a very short list of different published studies that you can go look at to get a flavor of the type of research you're able to do with these radars. So like precipitation studies, looking at density gradients and scintillation of radio signals propagating through those gradients. There's gravity waves that you can look at. You can look at traveling ionospheric disturbances, which are related to gravity waves. And even fun, interesting events like solar eclipses, like the one that occurred in 2017. Incoherent scatter radar is an incredibly useful and powerful tool for performing CEDAR research. It is pretty much the only instrument, the only technique that provides you with altitude profiles of the plasma temperature, which allows you to study all kinds of electrodynamics that you couldn't study otherwise. And the technique is constantly improving and becoming more capable as time goes on. If you want to engage with incoherent scatter radar beyond this presentation, you should consider attending summer school. We have these yearly summer schools where we get together for a week and we try to do this presentation in a bit more detail over the course of a week. So you learn a lot more about incoherent scatter radar, you get hands-on experience operating a facility and working with the data and analyzing the data. Also, you can get in contact with a facility. Feel free to reach out to any of us and we'll be happy to work with you. With that, thank you.
Thank you, Dr. Reimer, for the great ISR introduction. Just a reminder that to the participants that the Q&A will be held after this lightning session. Don't forget to put questions in Slido with the speaker name. Now, we will hear from Dr. Ryan Volz. Dr. Ryan Volz will be presenting an intro on meteor radars. Dr. Ryan Volz is a research scientist at MIT Haystack Observatory with interests in signal processing, statistical estimation, and novel instrumentation applied particularly to radio science. He and colleagues at UC Boulder are currently developing the Zephyr Meteor Radar Network, a novel MIMO system designed to estimate the 3D wind field in the upper atmosphere by way of meteor trail scattering. So let's hear from Dr. Volz.
My name is Ryan Volz, and I'm a research scientist at MIT Haystack Observatory. And at today's student session, I'm going to be talking about meteor radar. I'll start at a high level and say that a meteor radar is any radar designed to measure scattering from meteor trails. They are most used to observe the atmosphere, for instance winds, at altitudes of about 80 to 100 kilometers. They're typically composed of multiple simple antenna elements. They have a transmitter with power on the order of 10 kilowatts, and they operate at a fixed frequency in the upper HF or lower VHF band, i.e. between 15 and 40 megahertz. Before I get into too much detail on meteor radar, I want to talk a little bit about meteors in general. You may have heard of a few different terms that sound like meteor, maybe meteoroid, meteor itself, meteorite, but perhaps you're confused about what all these mean. A meteoroid is a small body in space. Not just a small body, but a solid body in space. It is small, less than 1 meter in diameter. They're moving fast relative to the Earth, between 11 and 72 kilometers per second, and they are exponentially more common as size decreases. A meteorite is any meteoroid body that has survived passage through the atmosphere and lands on the Earth. And finally, a meteor is the phenomena, which is light or plasma, that is caused by the meteoroid entering the atmosphere. And the meteors typically form at altitudes between 70 kilometers and 120 kilometers. You might also be familiar with the related term asteroid. Well, an asteroid is any body in space that is bigger than a meteoroid. And so these are things that are much more rare, and if they were to impact the Earth, they would cause a lot of destruction. Meteoroids generally fall into two different groups, showers and sporadics. Showers you're probably familiar with. These are associated with a specific parent body, either a comet or maybe a parent asteroid itself, and they're named for the radiant or the apparent source in the celestial frame that they appear to come from. And that background is called sporadic meteoroids. These are quasi-continuous in that we're always seeing sporadic meteoroids impacting the Earth's atmosphere. Sporadic meteoroids and meteors essentially occur at random. They are relatively spatially uniform, so if we were to plot a bunch of detections on a map, as we see here on the left, of different meteors, they look like they kind of cover the entire map uniformly. They also have diurnal and seasonal patterns in how often they show up as a function of time. So in the day, meteors peak around sunrise, and they have their lull around sunset. And this is because of the bug on a windshield effect. The Earth is moving through space, and at 6 a.m. local time, you're on the side of the planet that is in the direction that the Earth is moving in space. And so you tend to see more meteors then because you're actually impacting more meteoroids on that side of the Earth than on the opposite side of the Earth, where it's near sunset. When a meteoroid enters the Earth's atmosphere, it encounters increasing atmospheric density and starts heating up and shedding particles, and that's a process called ablation. Once these particles start to shed from the meteoroid, those particles will collide with atmospheric particles, and both of them will ionize and form a plasma. And this plasma is initially very dense in the region surrounding the meteoroid itself, and we call that the meteor head. That head quickly starts to diffuse into the atmosphere, and it expands outward through ambipolar diffusion, and the meteoroid keeps traveling forward at kilometers per second, and so it leaves this plasma trail in its wake that is diffusing. Now I think you probably know enough about meteors that we can talk about how a meteor radar works. So we have meteoroids entering the atmosphere all the time, sporadic meteoroids. But what does that mean for a radar? Well, the trail itself is briefly uniform and compact enough to coherently reflect like a mirror, and we call this the specular scattering condition. So let's imagine we're the radar in this upper right figure, and we're sending out signals that are going out in all directions. And eventually some of those signals are going to encounter this meteor trail, scatter some of that energy in all directions, but it just so happens, because this trail is kind of a line, scattering from all these points in that trail will add up coherently so that you can see it with strong signal back again at this radar. And so it's that coherent adding up process that makes this specular scattering condition work. We call this first zone here around the reflection point the first Fresnel zone. And that's where the primary signal contributions come from for what we see returned back to the radar. Those neighboring Fresnel zones, and alternating white and gray, they alternate in destructively and constructively adding signal back to this signal that we receive at the radar. So you can get this kind of pattern where as the meteor trail's forming, we can see signal rising up until it reaches a peak, where this peak is happening where the meteoroid has created the trail up to this point where we've filled out the entire first Fresnel zone. And then as more of this fills out, we're getting destructive interference, and so the received signal power goes down and then back up again as we go through more Fresnel zones, and then we get that oscillating back and forth. That's in the ideal case where this power stays kind of constant, but of course the meteor trail itself is diffusing, so in actuality you see signals more like this, where you get a ramp up in power, and then that diffusion causes the signal power to drop off exponentially. So that intuitive process of reflection of the signal from a meteor trail that I've just described is what's called an underdense echo. And that happens when the trail plasma frequency is less than the radar frequency. In contrast, there's another case which we call an overdense echo, where the trail plasma frequency is greater than the radar frequency. And in that case, your radar wave can't penetrate fully into the plasma of the trail. Instead, the trail itself is acting as a plasma, and you're reflecting almost off the surface of that plasma, where that radar frequency is equal to the plasma frequency. And so you get scattering that is more akin to say a metal cylinder in the sky. And some of those signals can look like this, where you still have a large ramp up, but then they're kind of flat with some oscillations. And then because of diffusion, that trail plasma frequency will eventually drop down below the radar frequency, and then you might see a kind of exponential drop off that you get with an underdense echo. So from that description of underdense and overdense echoes, you might be able to surmise why meteor radars operate at HF or VHF frequencies. There's a minimum of about 15 megahertz due to the typical peak ionospheric density. We want to stay above that peak, or else we start getting issues with refraction and ionospheric reflections that are unrelated to the meteor trail. The maximum practically is about 40 megahertz, and that's due to what's called the ceiling effect. In order to get a good, strong signal from your meteor trail, the trail diameter must be small compared to the radar wavelength, but that trail diameter increases rapidly with height because the mean free path is increasing rapidly in the atmosphere. This ceiling effect is also related to the distributions that you see in detected meteors as a function of altitude. Most detections will occur between about 80 and 100 kilometers in altitude. And you can see that in this histogram over here from 1 day's worth of data. And there's a rapid fall off above 100 kilometer, and that's due to this ceiling effect. So we've seen what meteor trail echoes, specular reflections at least, look like. But we haven't really talked about how we can locate the meteor in the sky. We have individual antennas in these meteor radar systems that typically have a broad beam. So they're sending signal up almost everywhere in the sky, and that means it could be coming back from almost anywhere in the sky. And that is good. We do that because it increases our chance of meeting that specular condition and actually seeing reflections from the meteor trails. And then in order to solve for the location of the meteor using these broad beam antennas, we set them up in an array. And with that array, we can get the direction using interferometry. So that means we compare the phase of the signals arriving at the different antenna elements, and that received phase difference relates to the direction. And we typically use what's called a Jones cross, and that is 5 elements that provide 2 angular estimates in each direction, and that lets us form virtual baselines for increased accuracy. So we get a, say, 4.5 lambda baseline, and reduced ambiguity, which is a half a lambda baseline. We do this kind of Jones cross because it allows the actual antenna spacings to be greater than 2 lambda in order to reduce the mutual coupling between the elements, and so we can treat them as individual antennas and not have to model the effects of them interacting with each other. So what can we do with this information? Well, one thing that meteor radars are typically used for is to measure winds, and that's because the trail plasma drifts with the neutral wind, and that movement imparts a Doppler frequency shift in the Bragg vector direction, and we can relate that measured Doppler frequency shift to the wind at the meteor location and time. By fitting a diverse set of measurements within a given volume, you can solve for the U, V, and W wind components. So the U wind component, zonal wind, for example, is plotted on the left here, and the meridional wind, V component, is plotted on the right here. And you can see that we're successfully detecting these winds between 80 to 100 kilometers, where we're getting the bulk of those meteor reflections. And you can see tidal signatures in these winds, which is exactly what we'd expect. But that's not all that meteor radars can measure. For an underdense echo, the returned power is a function of the trail radius. We've already talked about that a little bit. And that means we can measure the echo's exponential decay time to estimate the ambipolar diffusion coefficient, d sub a. And that ambipolar diffusion coefficient relates to temperature and pressure. It's proportional to temperature squared over pressure. And so with some care and some modeling assumptions, we can then estimate the temperature from the ambipolar diffusion coefficient. Meteor radars are also useful for studying the meteoroids and meteor plasma itself, of course. They're useful for estimating the mass flux from meteoroids, which is on the order of 10 kilograms per second onto the Earth. You can calculate the meteoroid orbit and track populations of different meteoroids statistically. And of course, it's also interesting to study the meteor plasma dynamics and the instabilities that they can cause. So that's everything you need to know about what meteor radars do and how they work. So in this last section, I'm going to talk a little bit about what the future might bring for meteor radars. One big area of development is in forming networks of meteor radars. And so you can set them up in a network like this where we have multiple transmitters, and each of those transmitters is transmitting its own unique code. And then we surround it with receivers where those receivers can decode signals from multiple transmitters, and they know which transmitter a given signal comes from because it's matching with the code that they know that that transmitter sent. We can get a combinatorial number of links between these different transmitters and receivers, all operating over one frequency. And each link is effectively its own meteor radar. So you have a meteor radar between each of these transmit and receive links, and they have overlapping fields of view where they're viewing different specular geometries, and so we get more meteor detections in a given volume. Because we have these overlapping fields of view, we also get non-degenerate wind field sampling. So you can imagine, because a single meteor radar is only able to measure velocities along the line of sight towards the radar, it's blind to any wind velocities that are swirling in a circle around the radar. And so if you combine multiple radars and their different fields of view, you can then break that degeneracy and measure the full wind vector in a given area. So the really great thing about these meteor radar networks is that they give enough information to estimate the 3D wind field as a function of time. And so we can make maps like these, where now we're seeing the winds as a function of latitude and longitude within the meteor radar field of view. And we can see that these are much more complicated than the single vector that a traditional meteor radar would be able to estimate. And we can take another different look at that same data and instead plot what's more of a traditional meteor radar plot, the zonal and meridional wind as a function of altitude and time, but now we can sample it at different latitude and longitude locations. So it's important to remember that a single meteor radar averages over all of this, and with a network, you can see all these details. So I'll end it with a nice little summary with some new terms that you've learned. A meteor radar observes specular scattering from meteor trails, and it can measure the Doppler shift of a received signal to estimate winds at altitudes of about 80 to 100 kilometers. The strengths of using a meteor radar as a technique is that it operates continuously day and night. It has good spatial coverage when operating in an overlapping network. And meteor radars can be built with commodity hardware at a reasonable cost. And so it's not unreasonable to think that we could actually build networks of these things and get wide coverage of measuring winds in the upper atmosphere. So I want to thank you for listening, and here's a list of references that if you want to learn more about meteors or meteor radar, a lot of the figures that I showed here were pulled from these references, and these are very good places to go to look for more information. Thank you very much.
Thank you, Dr. Volz, for the fantastic introduction on meteor radars. Now, Dr. Katrina Bossert will be presenting an intro on LIDAR. Katrina Bossert is an assistant professor at Arizona State University in the School of Earth and Space Exploration, who studies dynamics in the near space region. She uses optical remote sensing instrumentation to look at coupling between lower atmosphere and thermosphere ionosphere system. Let's hear from Dr. Bossert.
Hi, I'm Katrina Bossert. I'm an assistant professor at Arizona State University, and I'll be giving a short presentation on LIDAR, also known as light detection and ranging. So before we get started on LIDAR, we need to understand what photons are. So what is a photon? A photon is an elementary particle representing a quantum of electromagnetic radiation. Most light we see is made up of large numbers of photons. Each photon has an energy associated with it. E is equal to hc over lambda in joules, where h is Planck's constant and c is the speed of light, and lambda is the wavelength of this particular wave. Shorter wavelengths are associated with higher energy, and longer wavelengths, lower energy. Each of these photons has this energy, but many things that we use are constantly sending out photons all the time, and so they'll have a certain power associated with them. So for instance, a light bulb in your house is sending out a number of photons per second, and that's going to be in units of joules per second or watts. So photons can scatter off of objects. You've probably seen this when you look at a lake, like this image over here on the right, and it's very sunny out. You can see the sun's reflection in the water. You also may have noticed, if you ever try and turn lights on in a car, and it's foggy or really cloudy out, that light scatters off of all the tiny, fine water particles in the air. Photons can also be absorbed by atoms or molecules, and they can cause excited states and then re-emit those photons. So this is something that commonly happens in nature, and it's called fluorescence. This is an image down here of fluorescent coral. And the waves that are re-emitted, they can either have a very similar or almost the same wavelength, or they can be re-emitted at a different wavelength. So when we talk about LIDAR, we're using a laser. And a laser operates by sending out pulses with many focused photons. So each laser is going to have an associated wavelength. So a very common one is 532 nanometers. If the laser is pulsed, which is what we use in LIDAR, it's going to have a repetition rate. So 30 hertz or 30 pulses of light per second is another thing that is commonly used in LIDAR. And then that laser is going to have a power associated with it. And remember, that's going to be joules per second. That's going to be dependent on the photons, the number of photons emitted over time, and the energy of those photons. We can actually calculate the number of photons emitted by a laser if we know the energy of a laser pulse, or we know the power of that laser. And this is just this equation here on how we would do that. So with LIDAR, we are focused on photon counting, and it's all going to come down to photon numbers. So, like I said, it's all about the photon counts. Each pulse of light has a certain number of associated photons. As these photons travel through the atmosphere, they're going to have a probability of scattering. And the return times of the photons tell us what altitude the photon is coming from. We look at that time that a photon has traveled, and we can calculate distance from that. So here's just an example. We've got a laser pulse that starts at time t equals 0. Several photons are emitted into the atmosphere. And let's say at time t equals t1, the photons have traveled a certain distance. And that distance is equal to the speed of light, 3 times 10 to the 8th meters per second, times that time t1. Okay, so that's the distance that this photon, we'll say photon B here, has traveled. And then when it makes it back to the detector, that time is going to be t is equal to 2 times t1. And so this is why the distance, we have to divide that time by 2, because we're accounting for time traveled there and back. And when we talk about LIDAR as well, it all comes down to something called the LIDAR equation. We use this for all sorts of LIDARs, but I'll be talking about resonance and Rayleigh LIDARs here. So this right here, this INSABES, this is received photons from one pulse. And INSABEL is going to be your number of transmitted photons, but there are some other things that we have to take into account when we use LIDARs. So this right here, this is your backscattering coefficient. So it's going to be different depending on whether you're using Rayleigh LIDAR. And so in Rayleigh LIDAR, this is something that is calculated based on the scattering process and assuming that everything is backscattering, because particles, molecules in scattering can scatter in different directions. And we're just interested in things that are going to come back to the telescope and back to the system on the ground. And then for resonance fluorescence LIDAR, this backscatter coefficient is going to be related to the backscatter from atomic absorption and emission. We also have to take into account the transmission through the atmosphere. And for clear air, this is very close to 1, which means that you won't lose a whole lot of your photons early on. They can propagate quite far through the atmosphere. But as we said before, each photon is going to have a certain probability of encountering an atom or a molecule. In this case, you'll have transmission up and transmission down. And as you can imagine, when it's cloudy out, your transmission is very low. So LIDAR doesn't really work when it's cloudy. This is also another reason we like to operate LIDARs in very dry places at higher altitudes, because there's just less stuff for the photons to propagate through. We also have to take into account system parameters and efficiency. things like the size of your telescope mirror. So when you're collecting all those photons, how big of an area are you able to look at? And then we also have to account for background photons. You know, the best time to operate LiDARs is at night because it's low noise. We can operate LiDAR during the day using a really narrow band filter, but one of the issues is that you can't filter out light that overlaps with the frequency or the wavelength that you're looking at. So, you know, you have sunlight and all these wavelengths across all different spectrums. You're still going to have some noise associated with that during the day. So again, interested in photon counts. LiDAR photons are collected in a telescope, and then they're sent to a photomultiplier tube. And, you know, this isn't a perfect process. These photomultiplier tubes have certain efficiencies associated with them. But when a photon hits, in general, what will happen is you this travels through the photomultiplier tube, and we end up getting a signal, a count, and that's sent to a computer, a counter board. And so we start to count the number of photons that come in a given time frame. So we see this voltage spike, and then it's counted in a time bin. And so what we like to do is we like to have a range bin. And so we look over a given time period. So a range bin of 25 meters corresponds to a time of 1.67 times 10 to the negative 7 seconds. I mean, this is, you know, pretty short time periods that we're seeing here, but you can get numerous photons in that time period. And then, of course, we average over several different laser pulses and several different profiles. So in the case of Rayleigh LiDAR, it's a single photon process. We're looking at molecular scattering. And densities are going to be derived from the return photon counts. From the densities, we can derive temperatures. And the returns are going to drop off exponentially with altitude just because we have less atmosphere the further you go up. The scattering cross-section is going to increase with decreasing wavelength. So you're going to get more returns as you decrease your LiDAR wavelength. And scattering, of course, is going to drop with decreasing density. And so the typical ranges are from 30 to 80 kilometers. You want to use this in clear atmosphere. You don't want clouds, you don't want aerosols. So typically you can't get too low into the atmosphere. You're looking at returns from the stratosphere, and probably up to around 80 kilometers or so is where you can still get reasonable signal. Now with resonance fluorescence LiDAR, we are using the metal layer, which is centered near about 80 to 100 kilometers. We use this to determine winds and temperatures in the region. So metals used with LiDAR systems include iron and sodium and potassium. We're going to focus on sodium here. And what happens is, in this little diagram over here, resonance LiDAR excites an outer electron, which then relaxes and it emits a photon. So it's a 2-photon process. And the scattering cross-section for resonance fluorescence LiDAR is about 1,000 times greater than for Rayleigh scattering. So we can measure this up to fairly high altitudes. So like I said, this is a 2-photon process. We get absorption and emission. And we can actually use multiple frequencies to start looking at the cross-section. So with sodium, we're looking at something called the D2A line. And what happens is we get a Doppler broadening from temperature. So everything has a certain temperature associated with it, and you're going to get more broadening the hotter that is. We also get winds from the Doppler shift. And so we can use 3 frequencies. And from those 3 frequencies, we can tell what the winds and temperatures are. And again, we're using neutral sodium from about 80 to 105 kilometers. And I just have a nice diagram here over to the right, which shows what a typical sodium densities look like. Now, we like to pretend that the sodium layer is just this perfect Gaussian distribution. But as you can see, it's pretty complicated. You have waves present, and all sorts of things can be happening. On the top side, we have ionic chemistry. And then on the bottom side, we have neutral chemistry. And then in the middle, we have the sweet spot where neutral sodium is just able to exist. And what does sodium LiDAR data look like? Well, we have LiDAR photon counts returned. So this is an example of the peak frequency LiDAR photon counts. And then, of course, we have our two other shifted frequencies. And you can see here, this is a photon count profile taken at a specific time. So these are our derived temperatures and winds over here. Down here, we see Rayleigh scattering, which drops off exponentially. And then we get this spike where we have sodium returns up above 80 kilometers. And like I said before, the scattering cross-section is much, much greater than the Rayleigh scattering cross-section. So we're able to get these measurements at this high altitude. We do this with 3 frequencies. We take a ratio for each of these frequencies. We make a map of these ratios, and then we're able to determine based on these 2 ratios from 3 frequencies what the winds and temperatures are. So I'm just going to briefly, real quick here, talk about how LiDAR is used in the CEDAR community. We use LiDAR for all sorts of things, including looking at climatology, variability in the stratosphere in the MLT region, coupling between the lower and upper atmosphere, gravity waves, tides, polar mesospheric clouds, sporadic metal layers, and regions of instability. So, all sorts of things. LiDAR is very, very important to our community. I'm just going to show a few publications here, and of course there are many out there. I just wanted to get some examples of different LiDARs. So this is a paper, the Raja 2010. We've got Rayleigh LiDAR measurements that were used from the Poker Flat Rayleigh LiDAR, from the Rayleigh LiDAR that was in Greenland at Sonderstrom, and Rayleigh LiDAR from the Institute for Atmospheric Physics in Germany. This is an example of Rayleigh LiDAR used to look at polar mesospheric clouds. So you have these tiny ice particles forming near 82 kilometers, and their scattering cross-section is going to be higher than just the Rayleigh scattering that occurs. So we get this backscatter from that. These are derived secondary gravity waves from the LiDAR in McMurdo, Antarctica. That's another Rayleigh LiDAR. We've got all sorts of uses for resonance fluorescence LiDAR too, thermospheric iron layers, climatology, sporadic sodium. They're also used for all sorts of gravity wave studies, persistent gravity waves, instabilities from gravity waves. And, we overlap a lot with modelers and combined modeling studies with the LiDAR observations. So with that, I'm just going to leave you with a few of these LiDAR stations that are currently in use around the world and are commonly used in our community. And, this is, I hope that you learned a little bit about LiDAR today.
Thank you, Dr. Bossert, for a great introductory talk on LiDAR. Now we will hear from Dr. Rafael Mesquita. Dr. Rafael Mesquita will be presenting an intro on rockets. He earned his PhD in physics from Clemson University in May 2021 with me. He will start his postdoc at Johns Hopkins University Applied Physics Laboratory in early July. Dr. Mesquita's research interests are mid and high latitude neutral dynamics and magnetosphere-ionosphere thermosphere coupling. His research includes the study of instabilities in the lower thermosphere and auroral forcing using sounding rockets. Dr. Mesquita is an experimentalist who spent much of his PhD analyzing sounding rocket data to produce winds and position of atmospheric instabilities through the triangulation technique and the release of vapor tracers. So let's hear from Dr. Mesquita.
Hello everyone, my name is Rafael Mesquita. I graduated with my PhD from Clemson University this past May, and I'll be starting my postdoc at Johns Hopkins University Applied Physics Laboratory in July. Today I'll be talking about sounding rocket measurements with vapor traces and the triangulation technique. This picture in the background is me, the camera setup, and the TMA in Alaska. We do the sounding rocket experiments with chemical releases in Alaska during the winter. That's why it's necessary to protect the cameras with the orange boxes that you can see here, which have their own heating system. Here I would like to take some time to thank the CEDAR meeting organizing committee for inviting me for giving this tutorial talk. I spent most of my time as a graduate student working with rocket data, and I hope to be able to provide some resources and answers to questions about sounding rockets and the chemical traces before the end of this talk. This is a question such as, why do we need sounding rockets to measure winds? And what's the basic principle of operations? How does the triangulation work and what results from it? I'll also add some extra information at the end in case you'd like to keep up with the NASA sounding rocket program. I'd like to start with a bit of a disclaimer. Even though historically rockets have been used to measure a multitude of atmospheric parameters through a number of techniques, I'll focus on the chemical release technique, and I invite you to visit the CEDAR wiki page. There you find a number of tutorials and keynote talks that cover these additional techniques. Here I listed a few. So why do we need rockets? Well, passive instruments are cheap to deploy and have the capability of measuring winds in multiple time intervals. But they have no information about the exact altitude of the measurements, and they don't cover every altitude range. Active instruments such as radars and lidars have also the ability to measure winds with time, but they don't cover every part of the atmosphere and often have a coarse altitude resolution. Well, similarly though, sounding rockets have pros and cons. Among the pros, it covers virtually every altitude range in the atmosphere, providing wind profiles with high altitude resolution. It has a relatively low cost compared to satellites. It's a great way to validate ground-based and satellite measurements, and it can be used to test instruments that are going to be flown in more expensive satellite missions, for example. Well, wind measurements are also very, very accurate. They have really low measurement errors. The cons: one can only measure a single snapshot of the atmosphere, which means that the rocket launch is used to measure the winds at one particular time. It has relatively high cost compared to ground-based and optical instrumentation, for example. It's a high-risk experiment, as in one cannot simply launch a rocket in any direction. There's got to be very careful consideration on where the rocket's going to land, so we avoid any accidents. There's a limited number of launch sites available in the world to launch rockets from. It also needs to take place between the evening and the morning twilights, so the star background can be used as a reference for the triangulation. The basic principle of operation is rather simple. You pick the chemical you'd like to deploy, release it in the atmosphere, and use it as a dye. And you follow the evolution of this dye by photographing it from different camera sites. The picture on the left here shows the trimetal aluminum, or TMA, the trail at the bottom, and the lithium cloud, which is the red part of it. These are different chemicals that are used to measure winds in different altitude ranges. Other chemical tracers like barium are ionized, which allow us to measure plasma drifts and electric fields. So you load these chemicals into a canister and release it from a rocket flying through the region of interest. On the right here, you can see the evolution of the TMA as the rocket goes. The TMA is what we'll focus on from this point on here. With pictures taken from the ground, and you can see how quickly it takes for the velocity of the medium to start pushing the TMA and create this highly structured feature. To release these chemicals in the atmosphere, we use the NASA sounding rockets picture here. These are large instruments that have the capability of flying above 200 meters, 200 kilometers. The chemicals are loaded into the payload, which is the top part of the rockets in the figure. The canisters look a little bit like these figures here at the top left and bottom left. As you can see, there's a pressurized piston that pushes the chemical out of the rocket as it flies through the atmosphere through a set of valves that get triggered at the altitude of interest. These pictures are also used to triangulate. These pictures on the right are used to triangulate and find the position of the TMA at time. At the center here, we have a picture of the camera setup and how we set up the cameras on the camera side. So once we have the pictures, the evolution of the TMA looks a little like this. These figures were taken from two different ground sites, offering two different perspectives on the trails as they evolve. They're also synchronized by time. To do that, we use a GPS receivers to determine the synced GPS time. That is where the triangulation takes place. Well, simply put, the triangulation is the process of determining the location of a point by forming triangles to the unknown point from multiple known points. What that means is we use the two different perspectives of the TMA that we just spoke of and the known star background to convert pixels in each of the images to right ascension and declination. Then we use the known position of the ground sites to determine latitude, longitude, and altitude of each point in the trail, as shown here in this picture on the right. The distance of closest approach between the lines from the camera size to the point to the trail is here used as the error in the position and determining the position. So we repeat the procedure for the whole trail, and this is the result. In blue here at the center we have the rocket trajectory, and in bold black we have the position of the trail with altitude corresponding to the TMA pictures in the background. With these positions we can already do some really cool science. For example, here we determined the time evolution of the atmospheric feature like this Kelvin-Helmholtz instability. For the winds, we repeat the same procedure for a number of images and get the three-dimensional position of the trails, which results in something like this. The left-hand side image shows the latitude and longitude with altitude and time, where the color plot is the position. The blue dots are in each altitude grid point. Here you can see the evolution of the positions with time. Also on the right hand side, plotting these three-dimensional results in the figure that you can see here. So if we have the rating change in the position with time, we can calculate the velocity at a certain altitude range. We do that by feeding a line to the latitude and longitudes versus times. That results in velocities with units of radians per second, which we then transform using to zonal and meridional winds by using equations 1 and 2. To find velocities and estimate the error, we use this procedure here. Focusing only on the latitude, we pick an altitude. In this case, I chose the 100 kilometers there. Then we use the distance of closest approach between the projections that we discussed earlier to weigh the error, the fitting. The lower the error in the position, the more confidence the fitting should give to that particular point. And we use the diagonal of the covariance matrix to estimate the feeding error. The top right figure shows the feeding with exaggerated errors for the sake of this explanation. The error between two grid points there is approximately 600 meters, while the distance of closest approach is rarely larger than 100 meters, for example. Repeating the procedure for a few altitude bins from the left-hand side figure results in the wind plots shown in the bottom right here. The result is a very accurate representation of the winds with errors of the order of 3 to 5 meters per second and a very fine altitude grid. As you can see, this technique has been used many times, producing 500 plus wind profiles over the years. We can also design the experiments to accommodate to the scientific goals of the campaign. For example, this image here was taken during the Azure campaign that took place in Norway. It shows the releases from 2 different rockets. Each of these rockets carried an array of smaller rockets with ampules of TMA and barium, strontium, to measure winds and plasma drifts in the F region. The result is a series of wind profiles and electric fields in multiple locations at the same time, which is really cool. The chemical releases can also be ionized, which drifts with the E cross B motion. Here's a picture that shows the TMA trail, the strontium clouds, and the ionized barium clouds from an all-sky imager. A few useful resources here. This paper by Miguel Larson in 2002, he collected 400 plus wind profiles from the late 50s on. All of those citations and publications are listed, as well as the locations for each experiment, as you can see in this map. This is a great resource for finding wind profiles at a particular latitude and period of time. The Wallops Flight Facility website is also another great resource for finding sounding rocket experiments. In this website, you'll find the best and future missions carried by the NASA at Wallops team. The NASA Sounding Rocket annual report is also a great read for those of you who are interested. They usually feature the details about each rocket experiment the Sounding Rocket program ran each year, including information about the vehicles and the mission success history, for example. So to summarize everything, here's the order of operations during any campaign. We travel to the region around the rocket range and set up the camera sites. Then we wait for the right scientific and launch conditions, which usually tied to the weather or geomagnetic activity or what have you. Then we launch the rockets and hope that all the preparation leading to the campaign results in mission success, with all the releases appearing in the field of view. This is usually a little bit nerve-wracking for a few minutes. Then we photograph the evolution of the TMA from the ground or an airplane. We then use the triangulation to determine the three-dimensional positions of the trails for each image pair. We repeat that for approximately 2 to 3 minutes, with each image pair separated by 5 seconds. Once we have the set of positions in the trail, we produce the altitude bin fitting procedure that I spoke of earlier. At that point, we estimate the velocity and measured winds for each altitude in the trail. The final product is the wind profiles and for all wind profiles in each campaign. The highlighted plot contains the winds from 5 campaigns here. Well, I hope that I have covered the basics of the wind estimation through sounding rockets and chemical releases. But please feel free to contact me with any questions and I'll be glad to address them. I would also like to once again thank the CEDAR meeting organizing committee, and I thank you for your time.
Thank you, Dr. Mesquita, for the wonderful presentation on rocket instrumentation and techniques. Now, Dr. Asti Bhatt will be presenting an intro on optical instrumentation. Dr. Bhatt has over 10 years of experience as an ionospheric scientist. She currently leads 2 active NSF projects. On the Daisy Mango project, she builds, installs, and calibrates optical imagers to create a nested network of red and green line optical imagers. She also develops data management and analysis systems and mentors students. On the Integrated Geoscience Observatory, supported by NSF EarthCube and Cyber Infrastructure for Sustained Scientific Innovation Awards, she has led a team to build a software platform designed to increase collaboration among geoscientists and ensure scientific reproducibility, and led community discussion on data and software stewardship. For these projects, Dr. Bhatt manages a team of early and mid-career scientists and interfaces with partners from collaborator institutions. She has chaired several national and international academic conference sessions at AGU, COSPAR, and CEDAR meetings, and serves on science steering committees for CEDAR, COSPAR, Commission C, and radio frequency ionospheric interactions workshops. Let's hear from Dr. Bhatt.
Hi, my name is Asti, and today I will talk a little about how optical instruments are used in CEDAR science. Optical instruments use natural and sometimes artificial light in the upper atmosphere to investigate the geophysics of it all. While there are several different types of optical phenomena that are community studies, here I will focus on observations of airglow and aurora, as this image from the International Space Station indicates. Here is the aurora, and the uniform layer here is the airglow. This talk will also focus more on ground-based optical instruments, which are more relevant to the CEDAR community. First things first, what are the mechanisms causing any emission in the upper atmosphere? There are several known and unknown mechanisms responsible for optical emissions seen in the upper atmosphere. But for airglow and aurora, let us consider 2 dominant mechanisms. We know that ultraviolet energy from the sun causes neutral gases to charge separate, which creates the ionosphere. These unstable ions also tend to go back to their neutral states continuously, a process that accelerates at nighttime. While the ions can directly combine with electrons, which is a process known as radiative recombination, it's a slow process. A faster process that takes place in the ionosphere is called dissociative recombination, in which an intermediate product gets created in the recombination process. The other mechanism is called excitation by particle impact, where the emissions are a result of energy of the incoming particle and the atom or molecule that is impacted. Excited oxygen and nitrogen dominate auroral emissions seen in the bright, colorful displays, where the color tells us which species are being impacted, and it also allows us to deduce the altitudes of the visible emission. To understand any of the emission wavelengths, we need to look at neutral and ion density profiles for terrestrial thermosphere. The red airglow in the ionospheric effulgence is the result of oxygen atoms in excited O-D state relaxing to the ground state. O-D can be created in multiple ways. However, the primary process is dissociative recombination of O2 plus ions. O2 is actually a minor species in the thermosphere, but O plus is abundant. O2 plus comes from a charge exchange between O plus and O2. In the figure on the right, we see red airglow near F peak and green and yellow airglow layers down below, which are from atomic oxygen O singlet state and sodium respectively. Now let's talk about observing these emissions. Optical imagers are a popular way to observe both airglow and aurora. Here is a figure from Josh Cemeter that shows a few different configurations: simple camera, a telecentric design, and a multispectral design. As you can see, the telecentric design allows use of narrow band filters with large fields of view. To create an all-sky imager, we tend to use a fisheye lens at the top. The rest of the imager assembly is to make sure that the light coming at multiple angles from across the sky makes its way down to CCD. This is essentially called telecentric design, as the one used in the Themis camera. Themis cameras are white light cameras, which means that they receive entire spectrum of the light. But since they operate at nighttime and have exposure time of seconds, they primarily observe the dynamic aurora. The figure on the right shows a mosaic created by stitching individual camera images to show the process over the entire Canadian sector. But what is the white light really? To understand that, we take help from spectrographs. Spectrographs have been used by scientists to observe what is really within the broad spectrum of the light. It uses a narrow slit to split the light into multiple wavelengths. As you might expect, at night, different species in the upper atmosphere emit a different wavelength. Note that when you observe from the ground, you will observe all the emissions coming from different altitudes. That is why it is important to understand the density profile we saw earlier that tells us what emission comes from where. Here is a spectral plot. We prominently see emissions from atomic oxygen, sodium, molecular oxygen, and OH. We know that there is a thin OH layer at mesospheric altitude of around 85 kilometers, which is where this band comes from. We already saw the yellow sodium layer in the photograph from the ISS. The green and the red spectral peaks we see here can come from both airglow and aurora, and sometimes a combination of the two. With an all-sky camera or a camera observing a specific emission wavelength, we can figure out which process is causing this emission. This is where the single wavelength or monochrome imagers come into play. The monochrome cameras use telecentric design with a narrow band filter that blocks light from outside the band. It is important to note here that the wavelength passband depends on the angle of the light impinging on it. Here in this figure, you can see a filter response for a 55 7.7 nanometer filter. The different curves represent incidence angle at different values. As you can see, different incident angles mean that the center wavelength changes. To ensure a uniform filter response, we use lenses in the telecentric imager design that parallelize rays coming from odd angles in the sky. Otherwise, your center wavelength moves, and that is not good, because what you think you are observing, you are not. Using filters like this, you can see images from the same location in different wavelengths that show different phenomena since they are coming from different altitudes. As an example, these two images are from the Boston University All-Sky Imager located in Texas and taken only a couple of minutes apart. The left is from 55 7.7 nanometer, while the right is from 630 nanometer. This right here is the Milky Way. On the left, you see waves that are likely from around 95 to 100 kilometers. And you do not see the same waves in the right image. Note that the waves at the edges on the left figure look a lot finer than waves in the center. This is an effect of the fisheye lens, one that we need to correct to do further analysis. Once we do that correction, we can start making sense of what we're observing. It is often hard to understand what you're observing in the all-sky image, but we can do the correction and start making sense of it by flattening the all-sky image so that all features are represented equally, which means no more bunched pictures at the edges. This then allows us to map pixels onto a geographic grid. For airglow images, another way to make sense is to use difference between the two images to enhance the contrast. Often, airglow features move slowly over the time scale of several minutes, which is unlike aurora, which is a lot more dynamic. So creating one airglow image every few minutes still preserves the essential dynamics. Another way is to use multiple imagers. We can create a mosaic from images taken at around the same time, which gives us a broader view into the propagating features. Here we see a difference image from multiple individual sites in the Mango network that has been created into a mosaic where we see elongated features that are likely medium scale TIDs propagating across the United States. Another way is to use kyograms, which are essentially cuts over a range of latitudes or longitudes plotted over time. Here, for example, we have taken a north-south cut over this projection of two all-sky difference images that seem to show wavefronts propagating northward, likely from a thunderstorm event in North and Southwestern United States. The kyogram shows us these propagating features over time and also allow us to identify individual propagating features. So much about airglow. What about aurora? We know that aurora has all kinds of amazing colors and patterns. How do we figure out what is going on there? One interesting way is to use a multi-wavelength auroral imager. One example is shown here from Semeter et al. Of using a simultaneous multispectral imager that we saw earlier. This allows us to see features in different wavelengths, which essentially means different species and energy levels. If we combine this ability with a narrow field of view imaging like this, we can begin to understand auroral forms much better. In this image from Watt et al., a small region was zoomed in using a narrow field of view imager showing swirls in the auroral form that are almost invisible in the wide field image. And of course, our old friend kyogram can also be used to understand aurora, especially when we combine that with multispectral imaging. Kyograms help us understand how different features show up in different wavelengths. For example, in this image from Conde et al. 2018, we see kyograms created by cut along the magnetic meridian from 4 wavelengths that show auroral features developing north to south in the beginning of the night, for example. It is really nice to have different ways of looking at the images. But the question is, what more could we derive from optical emissions? This is where Febrile interferometer, or FPI, comes into picture. FPI is used to derive neutral winds and temperature from the same emissions. The basic design includes an etalon, which is 2 parallel plates of partially reflective glass separated by a distance. Light incident upon the etalon from above will undergo multiple reflections between the plates. At each reflection, some light is transmitted. The transmitted rays have different phase shifts due to the different distances traveled. So they interfere either constructively, destructively, or somewhere in between, depending on the incidence angle. When light is incident from a cone of angles, this creates a circular interference pattern characteristic of FPI data. The lens projects this image onto the CCD where it is recorded. Here we see the basic design and a real-life version of an FPI from Brian Harding. The FPI output is a fringe pattern. For the airglow fringes, the source spectrum is a Gaussian function with the width determined by the thermospheric temperature and the Doppler shift, determined by the line of sight thermospheric wind. Here are some equations that tells us this process. In these equations, V is line of sight thermospheric wind velocity, defined as positive away from the instrument. The line width is related to the temperature T. Using these equations, we can derive neutral winds and temperature from the FPIs. On the left, we see winds plotted over time from 4 directions and vertical from the FPI at University of Illinois. Another way is to plot the winds as vectors on a geographic plot for single time. The plot on the right is a derived wind vector field from multistatic interferometers in Alaska by Mark Conde. You can imagine that combining wind vectors with an all-sky image here would give us a nice understanding of dynamic features. So it is always advisable to combine data from multiple instruments wherever possible. So I have only touched upon a subset of optical instruments here. I encourage you to look through CEDAR archives to find presentations about various other instruments and phenomena. However, all optical instruments deal with these tricky things, and it is useful to understand if you're setting out to build one. As you may imagine, observing the ionosphere requires clear skies and also dark skies. So location choice involves really understanding the weather, cloud cover, and light pollution at that location. The weather also plays a role in building a container for the instrument. Places with high humidity can cause all sorts of challenges, including visibility due to condensation, so drier locations are preferred. The third critical thing to keep in mind is that ambient light of any type will want to get in your camera. This includes tiny LED lights from computing hardware. You will begin to appreciate little things like electrical tape to cover all the LEDs. You will also begin to appreciate some bigger things like code automation and data science, because there will be a lot of data to process every night. And finally, I want to leave you with the moon, that big, beautiful satellite of Earth. Just a heads up that you will begin to hate the moon a little bit or a lot, because there was a big storm that you really wanted to catch some data for. But oh, the moon is up, so maybe no data or maybe very little data. Well, I will end this presentation on that cheery note, and let me know if any of you would like to work with optical instruments or data from it. Thank you.
Thank you, Dr. Bhatt, for giving us the great introduction of optical instrumentation. Now we will hear from Dr. Jonathan Brent Parham. Dr. Parham will be presenting an intro on CubeSats. Dr. Parham is a member of the technical staff in Space Systems Analysis and Test Group at MIT Lincoln Laboratory, where he had studied the space environment and its effects on national infrastructure for the past 10 years. Before joining the group, Dr. Parham received a bachelor's degree in aerospace engineering from MIT. During his time employed at Lincoln Laboratory, he earned a master's in mechanical engineering and a doctorate in electrical engineering from Boston University as part of its Center for Space Physics. He has been involved with several CubeSat build efforts over the years, including Boston University's NJIT mission that was launched in 2020 and is currently supporting several missions to develop next generation space weather instruments. So let's hear from Dr. Parham.
Hi, I'm Dr. Jonathan Brent Parham, and I'm here to talk to you about CubeSats. I work at MIT Lincoln Laboratory today, but I did my graduate studies at Boston University in the Center for Space Physics, where I helped develop the CubeSat andesite, which launched last year under the work of Dr. Joshua Simitar and Brian Walsh, who many of you might know. So without further ado, let's talk about CubeSats. What is a small satellite? Well, it's hard to quantify a satellite's capability based on its exact size. And in the past 10 or 15 years, things have gotten smaller and more capable. Satellites such as SpaceX's Starlink satellite system, which is providing internet to people in rural areas, is technically a small satellite, though not a cube satellite. And there are several hundred up on orbit right now. There are also things that are even smaller, and you might call them picosatellites, femtosatellites, or whatever, but typically they take on the form of what's known as a cube satellite. Cube satellites are a standard that was developed by Cal Poly back in the early 2000s and late 90s. This standard is based around the idea that you can basically make a volume 10 centimeters on each side and call that a 1U cube, as you can see in this picture. Then you start stacking those cubes together and you create other standard dimensions. By having the standard, you're able to create common dispensers that attach to rocket bodies, that attaches secondary payloads to launch systems. This really enables everyone to be able to make a CubeSat and get it to orbit, because rather than having your own satellite be the primary payload where you have to buy your own rocket, you can get attached to the underside of a major rocket that is launching something else. This enables a lot of people to iterate and design and put things into space with very little cost in terms of launch capability, but then also more flexibility because you can kind of attach to whatever is going into space. There's a lot of intermediary providers that help you negotiate this, and NASA actually has a program called the CubeSat Launch Initiative which a lot of universities use, including BU for our CubeSat and Andesite that launched this past year. So these providers will find a launch for you. All you need to do is design to a specific standard deployer, as you can see in the bottom right picture here on this chart, that then no matter what you're attached on, you know that you fit into that box and you can get ejected into space once you launch. So why is this cool? Well, or why is it interesting? You get to use new technologies much more quickly. And if you put stuff into low Earth orbit and places that are interesting to this community in CEDAR, where you're looking at the atmospherics of things, the aurora, the ionosphere, or upper atmosphere, you can quickly put small sensors that are cheaply made and put a lot of them up there and sample things you never could sample before because you had to wait for a primary instrument or a secondary instrument on a major mission. I give you an example of how this is really enabling. We can look at what's in a small sat typically. It's a full satellite system, and we're going to look at as an example here the Mars Cube 1 or MARCO, which was launched by NASA and JPL a few years back and actually flew by Mars. It wasn't the primary satellite on that mission, but it added impressive communication capability and ability to relay information from Mars, from the major mission that was being launched there. These satellites were CubeSats. They were attached to the main rocket body and deployed just like what I showed in the previous chart. And they were their own full system with their own radio systems and propulsion and power and comms and flight computers and payloads of various little instruments. They were what's considered a 6U. So there's 20 centimeters by 30 centimeters by 10 centimeters deep, and there were 2 of them. This is really, really impressive to be able to fly CubeSats or satellites that small deep into space. Now in CEDAR community, you're usually thinking about things closer to space, or maybe you might think about the Martian atmosphere, but this just gives you a sense of how far this sort of technology can go. Here we can see both sides of one of the MARCO satellites and just kind of pick apart the different things you need to know about when you design a CubeSat. So as a scientist, you might be really interested in a certain data stream, and you're not really thinking about how to get that data stream. Well, a CubeSat makes you have to think about that. It's a systems integration problem. And that's kind of the difficult part about it, is being able to build satellites means you have to know all the parts that make a satellite, and you have to be able to know how they balance with each other according to mass budgets, power budgets, link budgets for comms, and all of those things in order to make sure the whole system works together very tightly. It's almost like designing a cell phone, but it's a little bit bigger than your iPhone. That's a lot to take in, right? There's several different subcomponents you have to know about: power systems, you have to know about radio and comms and RF energy, you have to know about your attitude and control and structures and thermal environment, radiation effects, all these things in order to design a satellite that works in space. And you haven't even gotten to your payload for your science mission. So when you're thinking about using CubeSats, you need to think about it's a systems engineering design problem. And then when you're thinking about the payload you want, does it fit into this tightly packaged system? And how would you manage that expectation and also manage the capability, or maybe design a new way to sense something so that fits into that small package? So how do you get there? Well, it's a lot of process. And I learned this especially during the time with Andesite, knowing that the process helps you get there in a timely manner and helps make sure your end product, your satellite, actually works by the time you fly it. This is just an example from the NASA CubeSat Launch Initiative CubeSat 101 pamphlet, which you can find at the link at the bottom of the chart, of all of the different steps from concept development, which is when you have the cool idea for your mission and taking a payload that you might have designed and putting it in space and measuring something in the atmosphere, to getting funding for that, to go through reviews internally with yourself and whoever might be funding you, like NASA, to make sure that it's feasible and you develop a system that actually might work. Then you might want to go through the CSLI selection process to find a launch, and then you start looking for a launch. But throughout all of this, you also are building your system. You're going through all these different hardware fabrication reviews, your design, your software development, and you're in coordination going through this chain one by one, getting licensing to be able to do your radio emissions, doing all the documentation because people change over and you might have new students or new faculty come in that take over projects, and you want to make sure that the work you've done can be passed on efficiently and picked up, and the program can keep going, because a lot of times these last longer than your tenure as an undergrad or maybe even as a grad student in my case. And then once you get through all this review cycle, the development and building, you finally do have a satellite. You have to wait for the launch. You have to integrate with the launch provider, which is somewhere like SpaceX or United Launch Alliance or Rocket Lab like Andesite, and eventually launch. And then you're still not done because you actually have to operate the satellite, which is yet another load of work. So there's a lot here. It's not just putting something up and getting data immediately, like taking out a compass and putting it on your desk and measuring the magnetic field. So just to give you a sense of a little bit of what a case study of this would look like, I'm going to walk through my experience with Andesite a little, just give you some cool pictures and just give you a flavor of what a development looks like. So Andesite was a 6U CubeSat that BU launched last June that was meant to measure the ERAU current system, the Brooklyn currents, by deploying a set of the pico satellites or small satellites like these guys that each have a magnetometer and a GPS on them. These satellites would then fly in a swarm, and then you could back out the current system through Ampere's law. So rather than get into too much detail about that, because you can look that up if you want, let's talk about what it took to get to the point of actually having a satellite that went into space. So here we can see just a few snapshots of boards. We had to do electrical engineering design, board design and layout for the instruments. These boards in the top left actually have the magnetometers that were doing the science mission. We had to calibrate the magnetometers or do testing to make sure they worked right. And then that was all in concurrence to actually building the full 6U spacecraft that would launch the small guys. So starting my PhD, I had this optimistic view of going through those steps, like I showed from the NASA chart, the different readiness reviews. We were under the university NanoSat program, and we had this kind of structure to keep us going. And this was all with the intention of having a launch in a couple years, so build to launch in about a year and a half or so, and do all the building and things concurrently. And I was expecting to have our built satellite by the summer of 2017, and then delivered to the rocket. So here's the process, kind of the montage scene. This is one of the students, O.C. Van Dessel, who now works for Aerospace at Starlink, testing power. He's measuring the irradiance of that bulb so we can know how much power is being delivered to that CubeSat solar panel, and then be able to back out whether the panel is working correctly. We have Hannah Levin, who's working at MIT Lincoln Laboratory with me right now, actually integrating the satellite together and putting the sensor nodes into the main payload bay of the 6U CubeSat with the deployer mechanism that we had to design and test. This is Maria Kromis, who's now at Draper, as she is putting into stack that has the attitude control system and the radio, which you can see it in the purple glove holding, the power system, the battery, and all of that fits in this 2U section at the front. So that gets integrated in separately after the sensor nodes get added in. And then this is vibration testing. So once the satellite was integrated, we put it into the canister that would launch into space. And we tested it by shaking it and putting through the paces of what it would be like going into launch. This is nominal things that you would have to do with any launch. You have to put it through a thermal vacuum chamber, you have to vibrate, you have to do all these things to prove to NASA that your satellite wouldn't fall apart as it's getting launched. And in the end, we had a built satellite. And this satellite, this is the final build. We're weighing it to send to the launch provider because they need to have mass estimates. So you can see it's a little over 10 kilograms in weight. And where were we by the time we got this? Well, this was the summer of 2017. And we had a built satellite, but the launch was uncertain now because we were kind of at the whim of the launch provider, Rocket Lab. This happens with any launch provider, mind you. And our last rigid schedule for launch, where we thought we were going to launch in the March-ish of 2018, we had our mission readiness review with NASA in December of 2017 and passed. So at that point, the launch got delayed and canceled, and I was finishing up other work I was doing in grad school. So this opens up the question of how do you transition to other people? Well, you know, I wasn't the only person working on this, so we tried to scramble to make sure things were in order so that as new people came in, we could transition it to the new students. I graduated that fall, but then Andesite, even though the build was still there, we tried to use the remaining time we had to better build up the software and better test things that we just wanted to make sure really worked. So we used that time to refactor the software after I graduated until it got launched. So all that time we were kind of playing chicken with the launch provider. So we actually got in the news eventually. COVID-19 hit by the time we still didn't have a launch, but we were starting to integrate. And we took it to Rocket Lab in March of 2020. So if a lot of people know, March of 2020 was an interesting time. This is the BU team that actually flew out to LA with Andesite, which you can see in the picture. We made it into the spacenews.com articles, and we integrated the satellite right before BU shut down. And this is kind of the ultimate playing chicken with the world, right? Luckily, New Zealand, it got shipped to New Zealand before everything got shut down there. And if it over some time, it became clear that Rocket Lab would continue the integration process. And throughout the spring, we were kind of holding our fingers crossed, and we launched. So in June of 2020, we launched. So that's the beginning of the mission. And you know, so much effort went into actually building the satellite. Now the mission is there. Is yet another whole story to go. But I just wanted to give you a flavor of how much work and how much goes into making a CubeSat nowadays if you want to design a CubeSat from scratch and put your own instrument onto it. I just want also point out, I really like the name of the rocket that launched us. The mission was called Don't Stop Me Now. So Andesite was on there under the NASA umbrella on this patch. Launched also with a satellite from University of South Wales in Australia and the National Reconnaissance Office. So key things to remember, software. I can't stress this enough. I see this in my current work, and I see this from Andesite, and I see this in other satellites I've come in contact with. It's the hardest thing you can do on a CubeSat, and it's the most important because the CubeSat is basically a computer, and without software, none of the hardware does anything. So don't underestimate it at all. Have good software engineers. Even if you think you're good with software, make sure you have multiple people checking the work and it's well documented, because that is the thing that makes and breaks most satellites, big, small, CubeSat, whatever. Also, testing takes time and you need to test. I didn't really fully understand this when I started with Andesite, but kind of learned it over the time. The testing isn't so much for you to prove to other people that things work, but more so that you need to prove to yourself that what you designed actually does what you thought it did. And you need to come up with every single way that you can possibly break the system in terms of software, in terms of thermal stressing, in terms of, for us, the deployment mechanism, just to make sure that it works exactly like you want it to work and there's no bugs or hiccups along the way. Also, schedules change, and I made that pretty clear with my examples here, where throughout the whole mission, we were kind of playing chicken with the launch provider because the launch provider was delaying. Sometimes it's not necessarily the launch provider, it's you that are delaying, and we probably would have been the bottleneck if the launch provider hadn't been delaying. So you need to work as if you're always working to that most optimistic deadline, because otherwise you won't make it. And it's a lot of work, and you need to make sure your team is together and all on the same page, and you have discrete objectives on your process towards that launch. So in closing, I'd like to finish out by pointing out to a great resource for learning more here. The NASA SmallSat Institute, the website given there, has a lot of great open source videos and reports on technology and descriptions of missions. And it's just a good place to start if you're interested in knowing more about SmallSats. You can also go to the SmallSat conference webpage, which has publicly available conference proceedings for the past 30 years of the SmallSat conference. And I just wanted to thank you for your time. And if you want to reach out to me at any more questions about andesite or SmallSats or CubeSats in general, here's my work email and phone. Thank you.
Thank you, Dr. Parham, for the awesome introduction on CubeSats. Now we have our final presentation for this lightning round. Dr. Seebany Datta-Barua will be presenting an intro on GNSS. Seebany Datta-Barua is an associate professor of mechanical and aerospace engineering at Illinois Institute of Technology in Chicago, Illinois. Professor Datta-Barua researches the use of global navigation satellite systems, GNSS, for remotely sensing the atmosphere and Earth's surface, tomography and data assimilation for ionospheric and thermospheric predictions of dynamics, and upper atmospheric effects on GPS-based navigation systems. Dr. Datta-Barua has received the NSF Career Award and in 2019, the Institute of Navigation's Per-Eng Early Achievement Award for outstanding contributions to the understanding of the dynamics of the ionosphere and its impacts on satellite-based navigation integrity. Let's hear from Dr. Datta-Barua.
Hello, everyone, and welcome to my talk today. My name is Seebany Datta-Barua. I'm an associate professor at Illinois Institute of Technology, and I have named this talk The Hitchhiker's Guide to GNSS in honor of the 42nd anniversary of the publication of Douglas Adams's sci-fi comedy, The Hitchhiker's Guide to the Galaxy. So if you're looking for some fun summer reading, I suggest that. I'd like to acknowledge the National Science Foundation and NASA for the support for that. So I will be taking you through a trilogy in 13 slides. I'll talk about global navigation satellite systems and kind of the basics of how they work and how we use them to measure ionospheric total electron content and to quantify ionospheric scintillation. So global navigation satellite systems, or GNSS, consists of a constellation of satellites that are maintained by operators in ground segment and used by users, typically for position, navigation, and timing. So this user is represented with an aircraft. So if you want to use GNSS for positioning, then the satellites transmit signals that arrive at the user, who measures the time of transit, delta T1, that it took for that signal to leave the satellite and arrive at the receiver. You multiply by the speed of light in vacuum, c, and you get the distance from the satellite to the receiver, the user. With multiple satellites, you can get multiple range measurements. And then the position can be estimated as the intersection of, in this case, circles. In actuality, we use at least 4 satellites for solving for 3-dimensional position and the time synchronization. So for PNT, position, navigation, and timing, you use these ranging signals, and you can use it for aircraft landing systems, for example. But here's the thing. The ionosphere, which we're interested in studying in CEDAR science, is refractive. So that means that the signal, when it leaves the satellite, for much of the space, our approximation of the speed of propagation being c, the speed of light in vacuum, is a good approximation because the index of refraction is unity. But as the signal goes through the ionosphere, the group index of refraction exceeds unity, which means that the signal slows down, slower than the speed of light in vacuum. And when it slows down, the receiver measures a longer transit time than corresponds to the distance. So the upshot is that the ionosphere delays the GNSS signal. That index of refraction exceedance of unity really, it depends on the ratio of the plasma electron frequency squared at any point in the ionosphere to the signal frequency squared. And the plasma electron frequency squared is proportional to the electron density in the ionosphere. So all of this is to say, if you want to compute the accumulated delay or accumulated ranging error, if you want to convert it to distance, then you're integrating that excess from unity of the index of refraction. Or in other words, you're integrating the electron density along the signal path as it slices through the ionosphere. And in the end, if you take all the constants and multiply them out, you end up with the fact that the ionospheric range error in meters on the left-hand side is proportional to this integrated electron density on the signal path, which we call TEC, total electron content. And it's inversely proportional to the signal frequency squared. And there's this constant that relates the total electron content to meters. That's not quite 42, but for GNSS purposes, this is pretty much the answer to the ultimate question of life, the universe, and everything. So if you're using GNSS for PNT, position, navigation, and timing, the ionosphere is source of error. And for single frequency users, it's the largest source of error. But don't panic. If you are receiving 2 GNSS frequencies, you can use the 2 frequencies to eliminate the ionospheric error if you're using it for positioning. Or in the case of CEDAR scientists, you can actually use those measurements, you can combine them to sense the ionosphere. And the particular effects that you can sense in the ionosphere are essentially the refraction, as we've talked about. The ionosphere acts as a prism. So in other words, the amount of refraction, the ranging delay, depends on that frequency of the signal. And there's also diffractive effects, where plasma variations in the ionosphere cause constructive and destructive interference, and that sometimes shows up in the received GNSS signals. So I'll kind of talk about those two later on after we go through a little bit about how the GPS, or more generally GNSS signal structure works. So here I'm using an example, but basically every GNSS signal has a digital sequence of bits of data, so zeros and ones that contain information about the satellite position, the time of transmission, the satellite health, and other parameters. And these are overlaid on top of a coarse acquisition code, sometimes also referred to as a pseudo-random number, PRN, sequence. This is a special sequence of zeros and ones, digital chips or bits that is unique to each satellite that transmits. So each satellite has its own CA code fingerprint. And those two data and the CA code combined give you, through modulo 2 addition, a sequence of ones and zeros. Those are then carried by a carrier sinusoid. At L1 frequency, this sinusoid is 1575 megahertz. L2 is at 1227 megahertz. And L5, which GPS also transmits at, is 1176. So the effect of having these data bits overlaid on the sinusoid is that the modulation then flips the phase of the signal each time there is a bit flip. And so if you read across the bottom, over time, the sinusoid undergoes a change in its phase, and those correspond to those data and CA code bits. So this bottom sequence is what arrives at the GNSS antenna. And there will be another set of these for each frequency transmitted by a satellite. And again, each satellite has its own unique code. So a typical GNSS receiver has to pre-process that signal that we showed at the bottom of the previous slide. It then acquires satellites, and it does this because the CA codes, those unique identifiers to each satellite, are known and published. And the receiver creates a replica of that sequence and correlates it against the incoming signal for different time shifts. And when the CA code is aligned in the replica with the incoming signal, that satellite's power accumulated will be boosted and the signal is acquired. After acquisition, the receivers track satellites and then solve for position. Now, for our purposes, we use the outputs of the tracking of the satellites. And those GNSS receiver observables or outputs are known as pseudo-range, rho, at each of 2 frequencies, and carrier phase, phi, at each of 2 frequencies. So again, you need 2 frequencies to do this ionospheric measurement. The pseudo-range is called pseudo because it contains the true range R plus that ionospheric error, the slant error for having transited through the ionosphere, plus other error sources that on the pseudo range are kind of noisy. And I'll just remind you that this ionospheric range error in meters here is, again, it's proportional to the total electron content and inversely proportional to the frequency of the signal transmitted. So in this case, at row 1, it's f1 squared. So you can measure pseudo range at each of 2 frequencies, and you can measure the carrier phase, which is less noisy. It contains the range. It also contains the ionospheric slant TEC, but it undergoes phase advance rather than group delay. So the sign is opposite on these 2. The carrier phase is less noisy, so the epsilon over here is a much smaller sigma on the model for the noise. But it is ambiguous. It's like having a ruler without any numerical markings. Lots of gradations, but no markings. And so this ambiguity is a whole number, an integer, n1, a whole number of cycles. And here multiplied by the wavelength of lambda 1 of L1 to convert to meters. So you measure this at 2 frequencies, and when you combine the frequencies, you end up with some additional biases. These are nuisance parameters that arise on the satellite and the receiver for having the signals travel through different parts of the hardware when transmitted from the satellite and received at the receiver side. So those are sometimes called DCBs as well. And to learn more about this, I would suggest looking at the Misra-Nenge textbook on GPS. So here's the point. GNSS is, for CEDAR science, your all-purpose towel. The ionosphere is dispersive. So with 2 frequencies, you can combine those measurement observables and estimate that range error, I sub s, or which is, again, proportional to TEC. Okay, so if you combine the pseudo-range measurements, row 2 minus row 1, subtract the ratio of their frequencies squared minus 1, divide by gamma, the ratio of the frequency squared minus 1, then what you end up with is an estimate of that TEC plus some biases plus some noise. Same thing with the carrier phase measurements. You difference them, divide by f1 over f2 squared minus 1. You get an estimate of that slant TEC in meters at L1 plus bias plus the integer ambiguity plus noise. So if you take a bunch of these measurements from the ground receivers, each one tracking multiple satellites, then each one has a total electron content along a single ray path And you can measure how much integrated electron content, total electron content, is along each of those paths. But you can see that if you combine these, they all have kind of different geometries because the satellites are at different elevation angles. So typically, if we want to combine these measurements, we take each slant TEC measurement and we multiply it by a geometric factor, sometimes called the obliquity factor, that depends on the elevation angle and basically converts them all to an equivalent vertical column if that signal had passed through an equivalent vertical column. Now, for the purposes of mapping, the ionosphere it has thickness, but for the purpose of making maps of electron content, you often have to choose, the mapper has to choose a specific altitude at which the ray path is effectively piercing through the ionosphere. And usually this is the height of the peak density of the ionosphere. So usually in the F2 layer, around 350 to 450 kilometers. So if you look at that intersection of those ray paths with that particular altitude, then you can find the latitude and longitude for it, and you can make a map of TEC. So you may have seen TEC maps before, but what people don't always plot is the fact that each one of these has a pierce point associated with it, so an assumed height, and is looking or is being observed from a particular direction. So they're measuring from a receiver to a satellite. So oftentimes you're combining measurements that have been looking and slicing through the ionosphere in different directions. Okay, so the color here corresponds to, in this particular map, that equivalent vertical ionospheric delay in meters at L1. But more often in CEDAR science, we'll talk about this amount of delay in terms of the number of electrons, okay? And we'll use units of TEC units. One TEC unit is 10 to the 16 electrons per meter squared. And so this color scale here goes from about 0 to 60-ish TEC units. And so this is how we make maps. Ionospheric scintillation happens due to irregularities in plasma that scatter the GNSS signal. This causes the amplitude, the power of the signal and or the phase of the signal to fluctuate or scintillate rapidly, which can make the receiver have difficulty tracking the satellites. And to read more about this diffractive scatter theory, there's a classic review paper by Ye and Liu, and more recently, Kintner 2007 paper review. So here's an example of a receiver that if it outputs the power and phase at more than 1 hertz cadence, in this case 50 hertz cadence, you can actually measure those amplitude fluctuations and phase fluctuations across the bottom. Now, if you don't have a receiver that's outputting data at 50 hertz, that's not a problem. You can still use standard dual frequency receivers at, say, 1 second, providing those observables, pseudo-range and carrier phase observables at about 1 second cadence. And you can compute the rate of TEC, or rate of tech. And that is a pretty good proxy for scintillation. And so without going further into details, because I know you'll be talking about it more later today, I'll leave you with this thought. We've been collecting this high rate data for several years now. I'll point you to the link here. And if you are interested in other data sources, well, the CEDAR Madrigal website here has many types of GNSS data. You can select distributed ground-based receivers. You can look at the worldwide GNSS receiver network or the GNSS scintillation network. Select your dates and start using TEC maps and data in the way that we've talked about. These are run by Anthea Koster, and the main point here is that you can leverage GNSS signals, which were designed for positioning, to actually study ionospheric and upper atmospheric dynamics. So thank you for your time, and I've provided my email. I look forward to interacting with you virtually. Thanks.
Thank you. Thank you, Dr. Datta-Barua, for the wonderful talk on GNSS. We just finished a series of short talks on different instrumentation techniques by different speakers. We will be having our Q&A session now. Among the speakers, Dr. Seebany Datta-Barua and Dr. Katrina Bossert are not available live, so we will publish their answers in student newsletter. Rest of the speakers, when the question is directed to you, please unmute yourself and you can also switch on your video to answer the question. And I'll ask the question in the same order as the talks. So the first question is for Dr. Ashton Reimer. What is the total observation area for ISR radar, like Pfizer and Millstone Hill?
Yeah, that's a great question. I answered a bit on Slido, and I also put it in the CEDAR Slack channel under the CEDAR students. So if there are people that have questions later, please feel free to ask under there, and I'll do my best to answer you there. So the total spatial extent that the radar is able to provide measurements over is given by its field of view. And for the steerable dishes, they can steer to different elevation angles that are limited basically by a couple things. One is the signal to noise ratio. So as you go out further in range, you're going to have less signal, because as you go out in range, the signal drops off as a function of range. And also your elevation angle is then limited how far you can steer down, either physically by what the dish can steer to or your environment around you, right? So if you're in a valley and there's mountains around you, you can't obviously steer below the mountains, right? And you don't want to steer too close to the mountains either, because you get echoes off the ground clutter that can cause you problems. For the phased arrays, they are limited by how far you can phase the beam before you start hitting grading lobe limits. And the grading lobe is a function of the antenna spacing and the frequency you're transmitting at. So if you think about like a diffraction grading, it's similar to that. So if you space your antennas properly, you can actually steer, practically all the way to 100, all the way to zero. But then you also run into effective area issues. So as you steer, if you think about phasing, as you steer your beam, the amount of area that is seen in that beam direction, the amount of area of the array that's seen in that beam direction is decreasing, right? There's a cosine angle dependence to it. And so if you steer too much, you actually run out of receiving area, and that decreases your signal to noise as well. So for Pfizer and for Millstone Hill, you can get out to several hundred kilometers at F region altitudes. So at several hundred kilometers altitude, you can get out to a few hundred kilometers. For Millstone Hill, they can go all the way around 180 degrees. So you can get a couple hundred kilometers all the way around. And for Poker Flat radar, it is tilted to the north a little bit, and you get out to a few hundred kilometers downrange to the north. So I could share really quickly to wrap up just a quick photo of some of the fields of view of the radars that are out there. And that gives you a sense. So the spacing, the latitude spacing here is about 10 degrees on this plot. So there's Millstone Hill. So you can get out pretty far. This is a 30 degrees elevation angle for Millstone Hill. And the field of view here for Pfizer, which is that phased array radar. These little dots are all the individual beam positions that the radar is programmed to be able to steer to. And you can see how it goes. The Resolute Bay radars are tilted more steeply so they can see further downrange.
All right. Thank you, Dr. Reimer. There is more discussion, like said already, on Slido channel as well. So if you haven't been to Slido yet, please check it out. Now I will ask Dr. Ryan Volz to mute himself and switch on video if he wants. Dr. Reimer. So the first question to you is, are there certain locations where meteor radars have more detection than others, or work better than other locations due to noise factors, such as equator or the poles?
This is a really good question that I will admit I don't have a definitive answer to, so I haven't been able to pull up any sources that give me a great answer to this. But I'll say my best guess, if I can hazard a guess, is that not really. The meteoroid population, the sporadic meteoroid population, is going to be pretty uniform no matter where on the Earth you're looking for them, and so the effects that are going to be happening based on whether you're at the poles or the equator are mostly going to be geometric effects, and those will also change with the seasons. And it's based on the specular scattering condition, whether you're able to see meteors that are coming in at particular angles and the distribution of angles of the meteoroids that you're seeing. And so you can imagine meteoroids that come in, it's hard to see meteoroids that are right above your radar at a 90-degree zenith angle, because these meteoroids would have to come in and pass through a lot of atmosphere at this perpendicular angle in order to get to the point where you're seeing them. So they would tend to have burned up by that point, and you don't tend to see them. So it's geometric effects like that that would perhaps lower the counts in different regions. But overall, I think it's not something that you would decide to put a meteor radar somewhere based on that fact at all.
Thanks. I'll ask another question from you. Can meteor radar metrics follow one big meteor trail and study the small structure like turbulence?
Yeah, so this is not something that we've really seen much of because we don't have much data from these new meteor radar networks. But absolutely, this is something that you could do. You can imagine that with multiple links and multiple effective meteor radars covering the same volume, you'd be able to get that specular scattering condition at multiple points along a single trail with these different effective radars. And so you'd be able to study the winds and the structure and turbulence along the meteor trail path at those different locations. But you can do this even better with high power large aperture radar that's observing the non-specular reflections from that meteor trail. So you can see this near the equator with Hickamarca. If you observe non-specular meteors, you can get Doppler shifts from the trail for the entire trail mostly, and get really detailed winds off of that. And that's something that has been done and published. And it's almost like you're flying a rocket, the quality of those wind measurements.
Thank you, Dr. Volz. We will send you the rest of the question later. Now, the next question would be for Dr. Rafael Mesquita. So please unmute yourself and you can switch on the video as well. So the question is, why such low error for rocket launching data? And for how long do you get the data during the rocket launch?
Thanks for the question. This is a really good question. Yes, so the low error comes from just the triangulation. Like when you do the triangulation, you have the projection from one side to the TMA and another side to the TMA, and the distance between the two projections is the distance of closest approach, and what we call like the errors in the position. So at any given position in the TMA, those that distance is of the order of like 20 meters or so. It's rarely over 50. It's even rarer to be over 100 meters. So you do have the error in the position to be, between 10 and 20 meters. And then you repeat that for 20 images or so. So that makes the error be really, really small. So oftentimes we even have like error bars there in the order of the thickness of the line that you're plotting. So we often neglect the error bars at all. And how long do we record those the data during the rocket launch, that's really simple, as long as the TMA is visible in the sky. So the up leg, you know, the before the apogee of the rocket, it usually is visible for, you know, anywhere from 8, you know, like 3 to 8 minutes, depending on which altitude you're talking about. The higher it goes, the faster it faints away. The down leg takes a lot longer. It takes 25 minutes because a lot of the TMA that gets released in the up leg gets burned in the down leg. Like the TMA gets released and gets sucked back into the rocket, the vacuum left by the rocket behind it, behind the rocket. And as it re-enters the atmosphere, the density of the atmosphere, the density of the oxygen just increases greatly, and that burns like all at once in the 100 kilometers, 90 kilometers range. So that stays visible for a long time. So we record it, you know, it depends on which trail and what, you know, what part of the rocket you're looking at.
Great. I will ask one more question to you. How much does the choice of camera change the reliability of triangulation?
That's another good question. We usually use, and also there are more questions in there that I responded to them already in the Slido if you're into it. So the reliability of the triangulation. Yes, so we tend to use the best DSLR that's in the market. Like, for example, for those of you who are, you know, aspiring photographers, we use the D850, the Nikon D850. That's a really good camera, and that gives us a sensitive sensor. You know, it's a really good sensor in a way that, like, you can take pictures with low ISO and still have like a great detail on the trail, and that makes it so the picture is less grainy. For those of you who understand the photography term, and it also makes it so, like, it has a bigger sensor, so you have more pixels in the image, so you can really pinpoint the you know, like the projections into the TMA trail. So yes, it makes it so it's better, but not necessarily reliable, but, you know, like, it's just a better, more accurate, you know, measurement.
Thank you. Interesting. Thank you.
You're welcome.
So I will move to the next speaker who is available, Asti Bhatt, Dr. Asti Bhatt. You can unmute yourself, Dr. Bhatt. So the question to you is there a central database for all sky data?
Hey, that's a really good question. I also tried to answer that on Slido. There is not a central database for all sky data at the moment, but that is a really good goal, and I think an achievable goal. Right now, the data from different data providers or different all sky imager operators, the data provided by them separately on their own websites. Some data are available in the CEDAR Madrigal database, but not all of it. The challenge there is how the data are displayed, data are accessed, what format the data are in, and whether those are usable by the user community. So these are some of the issues that we need to actually work through in order to make this a reality, but this is a good and achievable goal in the near future. Thanks for the question.
Thank you. For the second question, how difficult is it to remove noise from multi-wavelength spectrum?
Well, again, I answered that a little bit on Slido because the answer is a little bit more complicated. It's not straightforward, depends on what type of noise that you're trying to remove. There are instrument specific noise that you can remove rather easily given the full instrument profile that you have from the instrument provider. And by that, I mean,
the CCD manufacturer will give you what the noise sources are and how you can remove them. But then there are other noise sources which play a role into your messing up your observations, like street lights can often create this spurious signals within your spectrum. And one way to deal with that is you can take a background image, a background spectrum and remove it from your data. But that may or may not always work depending on how dynamic your noise source is. What I would do right now is I encourage you to attend the session on Friday by Jeff Baumgartner on instrumentation and calibration. That session will cover a lot of these questions related to optical instrument, and Jeff is a world's expert on figuring out how to calibrate any instrument, any optical instrument. So yeah, this is a short answer to complicated question. Thank you.
Thank you, Dr. Bhatt. Now I will move to the next speaker, Dr. Jonathan Brent Parham. So you can unmute yourself. So the first question to you is, how do you find resources? First question to you is, at what altitude do you operate the CubeSats to reduce any drag from the atmosphere?
So I was thinking about this. It's an interesting question about reducing drag when actually the opposite is usually what you think about. CubeSats, because they're secondary payloads and oftentimes don't have propulsion, you consider what's the highest altitude you can operate so that you deorbit safely. And so you don't really think about operating above the atmosphere to stay up longer. You actually want to be lower so you deorbit safely and don't hit something. And that's an active consideration right now being debated like in legal frameworks. The FCC is kind of the stakeholder that manages whether you get a license for radio operations, but they also check your orbital debris requirements. And then NASA will too if you launch through them. So for like andesite, we had to talk about what parts of the mission do we do when, and we actually launched above the International Space Station, and we have to wait until we get below to deploy the nodes. So I know it's kind of up in the air right now, but in the future, they might actually put requirements on if you're above a certain altitude, say like the International Space Station, you need to have propulsion so that you can go down quicker. But typically, satellites that get launched from the ISS are okay. And that's actually the most common way CubeSats get launched, is they get carried up as cargo and launched to the ISS, and then they have a box there. They basically cram the CubeSat in, and it springs out and by definition goes below the ISS. So you're thinking about how high you need to, rather than think about how low can you safely operate.
Interesting. So the second question to you is, how do you find resources on parts that have already been tested to be safe for space, or do you rigorously test everything individually regardless?
Yeah, this is a tricky one. So I would say you want to test everything. From my experience, but there's a level of testing, right? Not everybody can afford to put something in front of a particle accelerator, but you want, when you get a part from a vendor, they have a spec sheet or data sheet, and sometimes you want to kind of verify that spec sheet operates or does what they say they do, because it's kind of you're a consumer and they're a business person, so you want to make sure that you're actually getting what you're paying for. In terms of radiation effects, it's harder because, like I said, putting things in front of particle accelerators that radiation test them or any other source is pretty expensive. For CubeSats, there's kind of a risk. You're taking on risk approach to things, and if you look at I mentioned the SmallSat conference that happens every year. There's quite a few papers talking about what sort of things can you do to mitigate your risk, but not when you don't know how the part will operate in space, because that's another trade of if you bought only parts that build themselves as space rated and have all the data there. Sometimes they're prohibitively expensive. So it's the best resources for that would be looking through and seeing what the SmallSat conference papers where people have done this. There's one paper I'm thinking of. I'm blanking on the title, but I can send it out. That where the author walks through mitigation techniques for CubeSats when you don't know how the part might behave. And a lot of that is in software or just having multiple of the same part, so you have kind of redundancy. NASA has a few resources and databases. I think Goddard has a list of parts that they have done testing on that's publicly available. JPL has one too, but I just tried to go to the website and it was failing to load. But look around. The IEEE Transactions on Nuclear Science publishes data on parts when they do radiation testing. So those are the main sources. Either NASA does testing or the IEEE papers are a good source for kind of first pass looking to see what parts have been tested.
Thank you. Thank you for the answers to all the speakers. All the questions that have not been answered, we will send the questions to the speaker and we will publish the answers in the student newsletter. Now we end the first lightning session and we go for a short coffee break. I know we are running over a little bit time, but we will have a 10 minutes coffee break and then we will listen about satellites and models after that. So see you after break. Hello, everyone. Welcome back. I hope you had a nice short break. Now we will listen about satellites and models. These will be longer talks, and we will have a 5-minute Q&A session after these two talks, if the speaker is available. If they are not available, we will send the question to them and publish in student newsletter. So the first talk after the break is from Katelynn Greer. Dr. Katelynn Greer will be presenting a talk on satellites, past, present, and future. After she studies the thermosphere and its connection with the ionosphere and the lower atmosphere. She is particularly interested in quiet geomagnetic conditions, longitudinal variability, and local time structures. She has also been working on developing FUV hardware instrumentation. She received her PhD in aerospace engineering sciences from the University of Colorado Boulder in 2013 and completed a postdoc at the University of California, Berkeley, where she worked on the ICON mission. She has been with LASP since 2017. In 2020, she was awarded the NASA Early Career Public Achievement Medal. So now let's hear from Katelynn about satellites.
Hi and welcome. My name is Katelynn Greer, and I'm going to talk to you a little bit about satellite missions, past, present, and future. I hope you get something out of this, and I had a lot of fun putting some of this together. So just to give you a little outline of what we're going to talk about, I'm going to do a little introduction, and then we're going to talk about some past satellites, some present missions that are ongoing, and some future missions. And then lastly, I want to give you some tips, some tricks, and how to avoid some pitfalls. So when you think about satellite missions, you want to think about where they come from. And most people only think of NASA missions. So the big missions that they usually think of are NASA Explorer missions, like the current ICON mission. But you need to come to understand that there's a lot of different areas that satellite missions come from. So the next agency to think about is actually NSF, which sponsors the CEDAR workshop. And one of the things they're known for is CubeSat missions. There's a large variety of them. They are of a different, usually when they come from NSF, they're of a different type of science data in that a lot of the emphasis in CubeSats from NSF in the past has been on education in building the satellites and not as much on the getting important science data down. But I believe that's changing now. Another area to look in the United States for different satellite missions is the Department of Defense, NOAA, and other agencies. So some of the instruments that you might, or satellite missions that you might interact with that have data from these organizations are like the GOES satellites. And if you haven't heard of the GOES satellites are the satellites that sit at geostationary orbit, and they image the Earth on the Western Hemisphere. So if you ever see an image of a hurricane coming towards, say, the Gulf Coast, that likely came from a GOES satellite, but they also have important space weather instruments on them. Another satellite mission or instrument that you might have heard of is the CINDY instrument on CNOS. So you might look that up. And then there are obviously other countries put satellites up into space, and you should be looking for other nations' satellites or groups of nations. One of my favorite satellites is actually the Gochi satellite, which came from Europe. And that one has some really important information on thermosphere density. And I think it was a gravity mission initially, but they've got some really cool data that's been derived from that. Another one is the cluster mission. And then don't forget about private or commercial satellite missions. So I'm sure you've heard of the Starlink missions, but if you think about it, Starlink is an opportunity to put an instrument up into space, and who knows what kind of information we could get from a satellite constellation that's just that big. And then lastly, there are missions of opportunity, perhaps, that come on different types of commercial communication satellites. And these usually are very big missions and can go out to geostationary orbit, which is pretty hard to get to. So when you think of satellite missions, you need to look at the whole ecosystem of potential satellite investigations. In this talk, I'm actually only going to focus on mostly NASA and NSF type missions, but I wanted to remind you that there's a lot of opportunities in other agencies and commercial. So how and why are NASA missions planned? Well, really it comes back to the decadal survey. The decadal survey really does a couple of things. It provides an overview of the science and the current state of the knowledge of the field, but it also really tries to drill down to what the compelling science challenges are at current time. And they try to identify, considering the scientific value, urgency, cost, and risk of the highest priority scientific targets is what they call it for the interval of that decadal survey. So these are the different missions that they would really like to see funded. And then they also develop an integrated research strategy that presents means to address these targets. If I were you, I would go to this link that's on this slide right here and download the decadal survey. Not only will it tell you how and why satellite missions are funded, but it will tell you what the scientific priorities are in the field. And this is really important for whenever you, if you apply to a NASA ROSES grant, they're always asking about the relevance of your scientific idea. And if you can tie it back to something that's called out in the decadal survey, you can just quote, say the decadal survey says, quote, we need X. And I would provide X with this money to do whatever it is you want to do. So the decadal survey is really important. To that end, I want to note that the decadal survey that we're under right now was started in 2013 and only goes through 2022. So we're actually in the next cycle of the next decadal survey. And to that end, some of you may have participated in the workshop called Helio 5050. And there's some ongoing white papers that are coming of that. And I think on the agenda for this meeting for CEDAR on Tuesday, there's a Helio 5050 report. And then I'd also pay attention to the agency reports. I know they can seem kind of boring when you aren't very far in your career yet. And yeah, they talk a lot about numbers and budgets and that sort of thing, but you can glean a little bit of information about where the state of the field is going and what the decadal survey is going to do. I believe the next decadal survey, which they're starting to get ready to write now, is actually going to be informed also by, it's not just NASA, it'll be informed by NSF and NOAA as well. So keep that in mind and maybe pay attention to anytime anyone says decadal survey. So now we're going to move on to some historical satellites. I want to point out that any satellites I talk about here is not comprehensive to what's available out there. This is a very subjective list that I put together. And part of the reason is A, there's so many satellites, you can't name them all. And B, I wouldn't want you to sit through a talk on just a survey of satellites, just a list. I think that would be kind of boring. So I've just kind of picked highlights here and here. So the first one I wanted to highlight was the Atmosphere Explorer missions. They're labeled C, D, and E. They happened in the 1970s. And these had all kinds of instruments on them, from atmospheric density to extreme solar ultraviolet monitoring, monitoring electrons. There was a magnetometer, there was a spectrometer, just all kinds of really great stuff. So I would recommend, you know, going out and reading a little bit about what kind of instruments were on these satellites. The next satellite that I think you should know of and be able to say, oh yeah, I know what that satellite is the Dynamics Explorer. And this came in the 1989 to 1990. And there were two of them, Dynamic Explorer 1 and Dynamic Explorer 2. And they were set into a polar orbit at the same time. And they had a lot of different instruments that were interested in the high latitude energy and momentum transfers of the upper atmosphere. So they had ion drift meters, they had magnetic field observations, they were looking at neutral plasma interactions, all kinds of things. So again, take a look at these lists and see if you don't understand what one of the instruments did, go look it up and find out what a Langmuir probe does. What does that investigate? I know you probably are wondering, well, what does a Langmuir probe do? Please tell me. I just don't want this to be a laundry list of instruments and satellite missions. So I'm hoping to just pique your interest in some of these missions that are decades old, but still really relevant to today. A lot of these instruments, while they have been developed significantly in the intervening decades, many current instruments are based on these types of instruments that were originally flown in the 70s and 80s. All right, so these early missions have had profound influence on today's science. What I want to highlight is that a lot of this data from these early 70s and 80s missions are in the models that we use all the time for our research. So the one that you might be most familiar with, when I say empirical, it means that they have some data that went into producing this data. So the data that went into MSIS includes, there's a variety of it, and I encourage you to go read up on the MSIS papers. Atmosphere Explorer data, which I just mentioned to you from 1979. OGO-6 mass spectrometer data from the 1960s. And then there's also some rocket data. And this plot is from a paper showing the years that the data was collected and the altitude ranges that are available. So you can see a lot of the data that's available in this model was collected before 1980. So I would say the data is of good quality before 1980, but what you need to take into account is the solar cycle. So a lot of the data that we have for different models may not have covered an entire solar cycle or even several solar cycles, because as we know, every solar cycle is a little different. So that's something to keep in mind with how MSIS is developing. And there's a new MSIS out called MSIS 2.0, which I encourage you, if you're getting involved in this now, go straight to MSIS 2.0, learn where its data came from, learn what models are inside it and how it works. Other models that you might be familiar with that have data from some of these early missions include IRI, the horizontal winds model that came from Dynamics Explorer. Some of the Weimer and Helix models had DMSP data in it. And then also some of the L1 satellites contributed. When I say L1, I'll explain that in a little bit more detail later. Contributed to also some of these properties of our heliosphere and what's coming in to the Earth geospace system. So again, I'm going to talk in a very subjective way about current satellite missions. This is a graphic that's a couple years old that you can get from NASA. I bet during one of the agency talks on Tuesday, you will see this sort of figure again, and hopefully it'll be a little more updated than the one that I have. But you can see based on the color what's available right now and what's coming up. So I'll show you a couple of these. But it's really cool to see that we have missions in different regions of the geospace area. So everything from the thermosphere, ionosphere, out to the plasmasphere, magnetosphere, and out to the sun. So the first one I want to talk about is the timed mission, which has been in operation since 2002 in low Earth orbit. And TIME stands for Thermosphere, Ionosphere, Mesosphere, Energetics, and Dynamics. It has 4 instruments. The main ones that I use are GUVI and CEDAR. GUVI tells us about the different composition of the thermosphere, as well as some plasma information. And then CEDAR has, in addition to composition information, it has temperature. The thing to keep in mind about CEDAR is it really only goes up to about 110 kilometers in altitude if you're really pushing it. And so this is one of the things that we need to improve, is that we get temperature at higher altitudes within the thermosphere. I just pulled this graphic off the web, but one of the results that they're working on is showing that even in the upper atmosphere, we're seeing a CO2 trend with time. Next is a satellite called ACE, which is the Advanced Composition Explorer. It's been in operation since 1998 at L1, and they believe it has enough fuel until about 2024. So what is L1, you say? L1 is a place, if you look at the graphic in the upper right-hand corner, where basically there is a balance between the gravitational pull from the sun and the gravitational pull from the Earth. And you can balance a satellite at that point. I call it balance, but it's an orbit or small motion. There are 4 other points. There's one that's balanced on the other side of the Earth. There's 2 in front and behind the Earth, and then of course 1 on the other side. But the reason I brought up ACE is because it provides really space weather information. So one of my favorite tools to look at for what's going on in the with the sun and the solar wind at any given time is to go to what's called the Space Weather Enthusiast Dashboard, and you'll see they have like 9 or 10 plots. But this is one of the plots in the lower right-hand corner that I like to look at that gives you BZ, BT, density and speed of the solar wind, and the temperature. And then, of course, I've got a list of the scientific instruments that are on ACE. But it's a pretty incredible mission. It's been going this long. You may be asking, well, what are we going to do when it runs out of fuel? Well, NOAA has actually put together another mission called Discover, and it's already actually up there at L1. I think it was launched 2 years ago. Now I want to talk about the GOLD mission. GOLD is near and dear to my heart. I'm part of the science team on GOLD. GOLD stands for Global Scale Observations of Limb and Disk, and it's a NASA mission of opportunity, which means that we're hosted on a commercial spacecraft. And in this case, it's called SES-14. It's a communications satellite, and it's located in geostationary orbit at 47.5 degrees west, which is about the Amazon River mouth. The GOLD instrument itself, which is, I don't know if you can see this pointer, is actually just this little white and black thing right here, are 2 identical independent far UV imagers, spectroscopic imagers, and both scan the limb and disk independently. They're fully commandable, so you can do different sorts of campaigns if you have different ideas of what you'd like to look at. But basically the data that we get is on Earth's disk. We get daytime radiances, temperatures, we call it T-disk, and composition of the thermosphere. So this is the O to N2 value that you hear talked about quite a bit. And then on Earth's limb, we get temperatures and densities of the thermosphere. I forgot to mention that we also get nighttime densities of ionospheric plasma on the disk. So this is an active mission. just search for NASA Gold and you'll find the website to get data. We have quick look products and all that kind of good stuff. The next mission that I hope you've heard of is called ICON, which is the Ionosphere Connections Explorer. It's been in operation since 2019. And unlike Gold, ICON is in low Earth orbit and it's at 27 degrees inclination. And what that means is that it's focused on low and equatorial latitude, so it can't see the polar region. It has 4 instruments. The first instrument is called MIGHTY, and it's remote sensing of thermospheric winds. There is ion velocity meter, IVM, which is in situ sensing of ion velocity, density, and temperature. They have an EUV measuring instrument, which is sensing ionospheric plasma density. And finally, they have a far ultraviolet instrument, FUV, which is remote sensing of thermospheric composition, which is a very complementary instrument to Gold. And this website right here will take you to the mission webpage, and you'll be able to get to data and that kind of thing from there. All right, future satellite missions. There are a lot of them, but there are a couple of really important ones for our community that I want to talk about. The first is called GDC, which is the Geospace Dynamics Constellation. And it was a priority of the 2013 Decadal Survey. The idea is to understand how high latitude ionosphere thermosphere systems respond to variable solar wind and magnetospheric forcing, as well as how internal processes in the global ionosphere thermosphere system redistribute mass, momentum, and energy. So the thing that's really cool about this mission is that it's slated to be a 6 satellite constellation mission. It's supposed to be in situ measurements. So the instrument selection is supposed to be done in about 2023, and it's expected to launch in 2027. So depending on where you are in your education and your career, this could be a mission that you get involved in and really spend a lot of your career working on. If you're interested in the GDC, I recommend that you read the Science and Technology Definition Team Report, which the link is right here, as well as the Design Reference Mission, DRM, which talks about the different constellations and how that will work and why we need constellations. Because the idea is that we're trying to measure gradients of certain scale, spatial and temporal scale. And to do that, we need a special constellation in order to do that. The other thing that's really special about this mission is that we haven't studied the high latitude system in this kind of detail since the Atmosphere Explorer missions. And so there are probably, some of you probably have advisors who worked on the high latitude system from the Atmosphere Explorer missions in their grad school days, and we're only getting back to it now. It's been over 40 years since we've gotten to study this region in this kind of detail and really unravel what's going on up there. Just again, some subjective highlights. There's another mission called AW coming up, which is the Atmospheric Waves Experiment, which is scheduled for 2022-ish, and it would be going with the International Space Station. The next one is called TRACERS, which stands for Tandem Reconnection and Cusp Electrodynamics Reconnaissance Satellites. This one's scheduled no earlier than August 2022. And the last one is SUNRISE, which is the Sun Radio Interferometer Space Experiment, which is a group of satellites, so again, a constellation, so 6 CubeSats, and they're looking at solar particle storms. But this again wouldn't be launched any earlier than July 2023. And I've kind of tried to pick some example missions here that focus on neutral atmosphere, thermosphere. For AW, TRACERS is kind of the connecting tissue of thermosphere to magnetosphere. And then SUNRISE is looking at the sun. So if any of these piqued your interest, I hope you'll go and look them up and find out more about them and maybe communicate with the teams that are working on these. So I just wanted to finish up this talk with some tips and tricks and common pitfalls. The first thing I want to talk about is using the data. Number one thing I would tell someone who's starting with the new satellite data is to use the quality flags. Quality flags could be anything from the instrument didn't have enough voltage to you were in the South Atlantic anomaly. So use those quality flags because if you try and publish data with poor quality data flags, you're going to have to go back and redo it because a reviewer will catch that, and you don't want to have to redo your work. My other tip involves keeping track of local time. And by local time, I mean solar local time. So there's an equation that's something like solar local time equals the universal time plus the longitude you're located at divided by 15. This local time can be important for various phenomena within the ionosphere and thermosphere. And if you try and lose track of solar local time because it's critical for a lot of variables. I would also suggest, looking up other papers, the instrument papers that were written on the mission. And, it's okay to contact the science team if you're having trouble or ask about the quality flags or whatever it may be. I mean, obviously don't pester them, but it's okay to ask for help and say, hey, I'm really interested in this data product. I have this idea. I'm just struggling with this one little thing. Can you help me? As someone who's gotten these emails before, I love helping people. So definitely think about, you have to do your literature review first, so look it up. But yeah, I love helping people. So please do reach out to science teams if you need help. And then the last thing on using the data is keep track of the version of the data you're using, because frequently, I don't know about frequently, always, teams basically do reprocessing of data. And when they reprocess the data, things change, and whether that could be a major or minor impact on your research really depends. So not only do you need to say what version of the data you're using in any manuscripts you publish, it's really helpful to keep track of the version of the data you're using so that you can keep your research going, and if there's any changes or problems, you can keep track of that. Always check out the mission webpage for publications related to the mission. I think I'm going to hammer on this a little bit hard, but consider contacting the PI with any manuscripts you have for review. First of all, PIs like to know what research is being done with their data. They like to make sure that not only is it quality research, but that you're using their data appropriately. They don't want papers out there that use their data in an inappropriate way. And the last thing is it's frequently considered courtesy to include the mission PI as an author. The other thing this really helps with is the PI needs to report to their agency that funded them. So in my case, NASA, how many papers were published using their mission, and this really helps support the mission and continuing to get funding. This is all tied together. I think I'm saying the same thing in several different ways, but if you do publish a manuscript using data from a mission, understand what kind of acknowledgement is requested by the mission. I usually call this rules of the road. Sometimes you'll even find a document on a mission webpage called rules of the road. If they do have one of those, I'd recommend reading it just so you know what's expected of you as a researcher. And for example, ICON really just asks that you put this line in your manuscript about what funded it. And that's important. But again, I would also contact the PI if it were me. And then the last thing, for those of you who are really interested in missions and getting involved in hardware, one place to really consider getting involved is to apply for the PI Launchpad. This is a program through NASA, and basically they teach you how to propose a mission, including creating a science case, what your science objectives are. I think they even go through what requirements mean and how to write requirements for a mission. Learn how to create a science traceability matrix. I cannot emphasize enough how important the science traceability matrix is and how important it is to write one well and have everything consistent with the science traceability matrix. They also talk about how to create a science team and handle group dynamics. One of the things that's being pushed by NASA right now is team resiliency. And I think this would be really important for you guys to maybe pay attention to, in that they like to see teams composed of senior and junior personnel, because if, say, the senior people retire or something, they want to see the mission continue on and have longevity. They also help you with networking. How do you find perhaps industry partners and get some support from your home institution? And then, strangely enough, they also talk a little bit about storytelling, which is important in that it makes for a more compelling proposal. If you can tell a really good story that people are going to remember, your proposal has a better shot at getting funded. So I think that's all I really have for this presentation. If you have any questions, please submit them. I think the organizers have told you how to do that. If not, they'll tell you in a moment. And I really appreciate your attention, and I hope you guys really enjoy your CEDAR conference.
Thank you, Dr. Caitlin Greer. Unfortunately, Dr. Greer is not available for a live Q&A, and we will publish the answers to your questions from Slido in the student newsletter. Now, Dr. Cheng Li will be presenting a talk on the hierarchy of atmospheric models. After the talk, there will be a 5-minute Q&A. Please ask questions on Slido. Dr. Liu is an assistant professor in the Department of Physics and Astronomy at Clemson University. Her research focuses on atmospheric waves and magnetosphere-ionosphere thermosphere coupling using numerical modeling and observations. She is the recipient of the NSF Career Award and a Rising Star in Discovery Award at Clemson. Let's hear from Dr. Liu.
Hi everyone, this is Xian Lu from Clemson University, and thank you very much for the opportunity to introduce something about atmospheric modeling. And you can see from this slide, there are many applications of numerical modeling can do. And this is the simulation of coronal mass ejection published on Nature. And this is showing the flow trajectories flowing along the Himalaya mountain. And here, this is a super twister associated with a big tornado event. And numerical simulation can be also used to study breaking waves and even galaxy formation. And this is showing the turbulence and vortices associated with the blocking of the rock. So as you can see from these examples, our world is pretty much controlled by either ordinary or partial differential equations. Here are some examples. The wave equation, we know that it's going to transport the waveform at the speed of c. And no matter what kind of waveform you have, your solution would carry this would carry this form. And there are also like heat conduction or heat diffusion processes, which pretty much is going to damp your heat is also controlled by the differential equations. And the Laplace equation, if there is no source, no point source, no charge source in the system, then your electric potential is going to have to be, the Laplace of that is going to be equal to 0. And if you do have some nice boundary conditions, you can even solve for the electric potential analytically. And not to mention Maxwell equations. Maxwell equations are all controlled by the partial differential equations. And also for fluids, because we know our atmosphere is gas and it's fluid, it obeys the fundamental dynamics of fluids, and which is Navier-Stokes equation. And on the right and the left-hand side, usually it shows the tendency term. We have the zonal wind, meridional wind, vertical wind, and usually we also call this momentum equations. And the thermodynamic equations is denoted by the potential temperature. And heating term comes here, and the last one is the continuity equation. So you can see that the behavior of the fluid, for example, the winds, are going to be controlled by the Coriolis. There's no Coriolis in this equation, probably because it's more focused on regional scale stuff. So there's no Coriolis force, but there is a partial differential force. And because this is a local derivative, and there are transport term, convection terms, which also determine locally how your things are going to change. And there is dissipation or diffusion terms on the right-hand side, and also gravity, those kind of things. But no matter what, it's partial differential equations. Okay, so this talk, the outline of this talk is showing like here. It consists of 3 main parts. So first, I'm going to go through some fundamentals of numerical modeling. Hopefully, it helps you guys to get a little bit of flavor of what numerical modeling means. And we have different schemes and how to judge which one is good and which one is not, and depending what kind of performance you expect from those numerical schemes. And then I'm going to give some examples and compare different numerical schemes. Then especially put some emphasize the difference between finite difference and finite volume, because finite volume is quite popular and used in some popular models in our fields. And then I'm going to go through the hierarchy of atmospheric models and give some examples about empirical models, physical models, and also data assimilation models. So as we mentioned earlier, our world to some extent are dominated by partial differential equations. And here is just one example. And you can, partial differential equations usually tell us continuous things. Everything is changing continuously in terms of time, in terms of space. But however, when you try to study this using computer, for example, sometimes the equations are so complex, you don't even have the analytical solutions. Then you have to use numerical ways to solve for the solutions. We have to discretize the equation, because computer cannot handle continuous things. You need to make it digital. All right. So then it comes, say, what kind of finite difference scheme we use to approximate these partial differential derivatives. So that's the point. That's the key of developing finite difference schemes, because we know that, for example, if we use the so-called forward time and upstream space schemes to approximate the temporal derivative and the spatial derivative respectively, and you would end up with truncation errors, because we know that from Taylor expansion, there are some higher order arrows, in this difference. So those are called truncation arrows. Then later on, I'm going to talk about, say, how we can diagnose the arrows and actually judge which scheme is better. But no matter what, we have to approximate, discretize the partial differential derivative. And this is an example. Then from this example, then you can see, then we can model the system by knowing maybe, you know, what the fields look like in the previous step, for example, at time t. Then we can go forward and advance to time t plus delta t. And by knowing the solutions at previous time at different locations, for example, at x, and also at the nearby points, such as x plus delta x. So this is how fundamentally how the numerical modeling can do. It can advance to the future time by knowing, say, the initial conditions, the boundary conditions, the model can start to develop, okay? And in terms of the approximations to derivatives, as I said, we have different ways. So the whole point is actually, so this is the slope, right? So this would be the slope of this true solution of this curve at a certain location. So that is the exact slope of this one. So the thing becomes, say, then what is the way, first is what is the way to approximate this slope to make it as realistic as possible? The second one is also by involving maybe less points, because if you involve more points, they may increase the computational expense. And there are several examples showing here. For example, the backward scheme, the forward scheme associated with one step to the right, and the backward associated with the one step to the left. And the central scheme is involving 2 points nearby around the middle point. So there are many ways to do it. And then in terms of, say, which way is good and which way is not, we can actually analyze the amplitude and phase arrows. And amplitude arrows can tell you that whether your numerical scheme is damping or your numerical scheme is amplifying the true solution unrealistically or damping the true solution unrealistically. You can tell it by analyzing the amplitude arrow. For example, we can start with a simple example, which is oscillation equation. And you can say, this is the partial differential equation. And we know that the solution would be like this. And this is just oscillation, right? It's a wave oscillation. The amplitude wouldn't change. So the ratio of the two steps of your amplitudes is equal to 1. But if we use the forward time scheme, then the next time step versus divided by the current time step, the solution, the numerical solution coming from your numerical scheme is equal to that. Now you can see that the amplitude ratio would be a factor that's larger than 1. And depending on what your time step is, if your time step is bigger, then your arrow is bigger. And it's going to always amplify your true solution, okay, if you use the forward time scheme. Similarly, if you use the backward time scheme, you end up with also not exactly equal to 1 amplitude ratio, and instead it's going to be smaller than 1. And similarly, if your time step is bigger, then you end up with larger arrows in your solution, okay? And if you use a so-called trapezoidal numerical scheme, is actually using some, a little bit of manipulation, how you approximate the derivatives. It actually can end up with something in terms of amplitude is actually equal to 1. So which is good in terms of the amplitude performance. Then you can say, if I use very, very small delta t, because as we can see, if your delta t is small, you still have arrows, but not that big. You can say the three numerical schemes can actually give you very very close solutions to the true solution. But if you increase your delta t, actually you can lead lead to very significant errors. And the forward time scheme always amplifies, backward damps, and something like that. Okay, so those can be actually seen by doing some simple diagnostics. And we can also see the phase arrow. The phase arrow, again, we start from true solution. So true solution is the oscillation. But if we look at what the numerical scheme gave us, then you can see the phase comparing the real phase change is now equal to 1. So which means the phase is not going to recover whatever the true solution is showing. And if the factor is less than 1, it means your scheme is going to delay the phase of true solution. And in this case, the forward time, backward time, and trapezoidal all lead to the phase arrows, but a little bit different, because you can see trapezoidal is divided by 12. So the phase arrows is a little bit smaller than the forward time scheme and the backward time scheme. And you can also see this from your solutions. So this is a delta t equal to 0.02. And the true solution is this black line. The red line, which is trapezoidal scheme, is the closest one. As we can see, there's a little bit of delay, but not too much. And if you look at the forward time and the backward time, you can say backward time, again, is damping the solution. Forward time is amplifying, and both of them start to show significant phase delay in terms of comparing with the true solution. Okay, so this is some diagnostic tools that you can use if you really want to say, I just get a little bit of flavor of what different schemes would behave. Okay, the second part, then I'm going to continue talking about comparing different numerical schemes, because sometimes if you want to really solve your own problems, you have a question, you want to adopt a certain numerical scheme, you want to have the best numerical scheme. Sometimes you can actually try a little bit different things and say which one is the best for your problem. So I'm going to compare some of them, given as example. And you can see here, I used Ranjikuta numerical scheme. I tried the Lex Vandroff. I also tried Takas. So Ranjikuta is a temporal numerical scheme. So it's kind of like, so the forward time scheme, for example, only deals with 2 time steps, current time step, and the future time step, 2 time steps. Then Ranjikuta means between these 2 time steps, it's divided into, for example, 3 or 4 minor steps. And it's kind of like divided into a little bit more steps in between in order to better approximate the slope of the temporal tendency. It has some advantages to some extent, but not always. And you can see here, so this is the transport equation. So the red, the true one is the true solution. The true solution, suppose, is something is going to advect it to the right. Then you can compare these different schemes. Okay, you can compare the different schemes. Then you can see from the Ranjikuta center space, you see these little ripples. And then these little ripples are actually caused by the phase arrow. The reason is because when the phase for different frequencies of your wave are different, then you start to show, if your scheme is dispersive, then you start to show different phase speeds for different scales. And in this case, the smaller scale stuff, which is 2 to 4 delta x, the smaller scale stuff, they tend to show the backward or negative group speeds, because the whole thing is actually supposed to advect positively. But if the scheme is dispersive, some solutions are going to propagate backward, then you start to going to be dispersive and have these ripples. So this Ranjikuta with center space is dispersive, and it's definitely not what we want. Then you can see the red thing is forward time and the fourth order in space, the TACAS scheme, is actually to some extent it can eliminate the dispersive thing in the numeric scheme. Okay, and as I mentioned, because sometimes if there is high frequency stuff which kind of like contaminate your solution, one way is you go to higher order, and another way is maybe you don't have to, but you still want to eliminate these small scale things in the numerical solution, and we can actually adopt some spatial filtering processes in order to eliminate those high frequency noises in the solution. And here is some example. Then you can say, so this one, the green one is the one without spatial filtering, and the other lines, the red line and the blue line, which adopts first order filtering, spatial filtering, and sixth order filtering, then you can say pretty much get rid of the small scale things. So this is another way. It's kind of like post-processing way to make the solution better. Okay. All right. And in terms of 2D problem, so this is still 1D problem. It's just involves with time, and it has a 1D spatial structure. So this is a 1D problem advancing with time. But in terms of 2D problem, so sometimes we still have to consider the directionality, because the reason is actually because if we have the 2D problems and if we adopt the traditional, the regular way to approximate the partial derivatives. So sometimes we start to have this direction, the secondary derivatives, and this has certain directionality in terms of which direction you really are propagating, simulating. So so in order to actually compensate for this truncation error, so they could represent some truncation error, because that's something you would end up if you do the Taylor expansion. So in order to compensate that, this so-called corner transport upstream method, in addition to adopting the regular difference scheme, it also as something that can compensate for this truncation error on the right-hand side. So to some extent, it's going to correct the distortion in terms of different dependence on different directions. Okay, so then you can say this simulation is going to compare the true solutions, which is propagating along this diagonal, and upstream highly damping and also distorted in different directions. Then CTU, which I just mentioned, CTU is going to correct the directionality, but CTU is very damped. So the last one, which combines Lax-Vandorf, which is less damping, and also CTU, which corrects for directionality, actually behaves the best comparing with these two. So you guys can see this simulation and get a little bit of feeling. So you can say upstreams, if there are no correction, starts to distort and also damp quite a bit. And the CTU, no distortion because you correct it to some extent, but highly damping, highly dissipative. And this one is the best. And this one is the best. All right. Okay. So all the previous schemes I mentioned, they fall into the category of finite difference. So finite difference means it deals with the values and derivatives at discrete grid points. So it talks about, say, what's going to happen at this grid, what's going to happen here, what's going to happen there at those dots. So this is a finite difference. But finite difference, sometimes it does have some limitations. If you want to really have a good performance, either you go to high orders of derivatives, which increase the computational expenses, or you may need to come up with some other fancy schemes in order to do good. But finite volume, to some extent, is more flexible, and people also can have a lot of maybe easier ways to manipulate how you come up with the flux, how you correct flux, how you limit flux in order for the scheme to have a relatively good performance. So finite volume, the idea is actually very different from the idea of finite difference. And you can say from the name, it's that finite volume. So instead of talking about single point, it starts to talk about a whole cubic. What's going to happen for the whole volume, the cubic stuff, the square stuff, okay? And then because we talk about volume, then what matters would be what is the flux coming in and what is the flux coming out. So the whole thing is really how you determine the flux. And this is example. For example, this is continuity or mass conservation equation. So these would be your flux term. And the divergence of your flux and convergence of your flux are going to change the local change of your density, okay? And as I mentioned, for the finite volume scheme, instead of talking about the truncation arrow or how the amplitude and the phase arrows would have for a finite difference scheme, finite volume is more talking about, say, how I can correct the flux that's coming in and coming out in order to more accurately simulate what is going to happen locally for this particular volume. Then for the flux, there are many ways to correct it in order to make the scheme, for example, monotonic, which means you do not have extra maximum or minimum coming out if you want a relatively smooth solution. You can do the flux correction in order to achieve that. This looks complex, but if you look into details, it does make a lot of sense in order to do this flux control. And this is another example, which is flux limited method. So similar to flux correction, this flux limited method is to times a certain weighting in order to do a correction. So basically it's weighted flux. It's not just a pure flux. It's weighted, and you will weight it because you want more correct solutions. And there are also many ways to do the limitation and also to do the correction. And here are some examples. So the left-hand side is comparing, this is a advection of the square form, a step form. And sometimes this is actually difficult to simulate than the sinusoidal waves. Why? Because the step function contains pretty much all frequencies in your solution if you do the Fourier analysis. So unless you have the good performance for all frequencies, otherwise you wouldn't end up with a very good solution. So this is actually, you can see this, right? So your upstream is highly damping. Comparing with the true solution, your upstream is very damped, very dissipative. Then your Lax Van Drove is very dispersive because you start to have these wiggles. So this wiggles is telling you that different frequencies of your waves are propagating with different phase. Then you start to disperse the waveform. So Lax Van Drove is quite dispersive. The flux corrected transport, the finite volume scheme, actually is the best in this case. And you can even do better. So here, in this simulation, flux corrected transport is the black line. And if you use the flux limited methods and using different ways to limit your flux, you can actually even achieve a better behavior than the flux corrected, which is already better than the upstream and the Lax Van Drove, some traditional finite difference ways. Okay, So then you can see this. Let's move to the between. Yep. Then you can see the finite FCT is the black line. It's a black line, but you can see the blue line and the green line can be even better. The flux limited stuff can be even better than that. So there are some advantages for the flux volume, the finite volume scheme. And actually, I believe many models such as CSM, the Wacom model, do have this option. And some other models also adopt finite volume schemes. All right, so those are some fundamentals of numerical modeling. I just want you guys to say what it means. So it really means it discreditize things than by either approximating the partial derivatives or by approximating your flux term equations, the equations in terms of the flux forms, and then you discretize that, then you start to calculate what will happen, next, or what will happen in your nearby points or your nearby volumes. Then you start to get the whole solutions for the whole domain and move it with time. You either move it with time or not, depending on whether it's a advancing model or not, time advancing or not. Okay, so now I'm going to move on to the hierarchy of atmospheric models. So in terms of the complexity, we can start from empirical models. So empirical models are based on statistical data and also parametric fitting stuff. It involves a lot of data, and it also is very good at showing the climatology things and those kind of things. Then physical models, also from simple to complex. We can have a mechanistical model, which is relatively simple, but still very good at being used to study the mechanisms. And we have regional models, and then we go to the monster, the big GCMs, general circulation models, the climate models, which is big. Then also combining the physics model and the data, there are also data assimilation model. So there are some examples. So those examples are actually limited to what I am familiar with and what I work with for my research. So those are not the complete list of all the good atmospheric models that we have in our community. So this is definitely not the full picture. And I'm happy to know more if you guys can send me emails, which I can include maybe in the future in my class lectures. So the empirical model, as I said, is data-based. It's mathematical and statistical. And some examples, we have MCs, we have IRI, we have horizontal wind model, and in terms of the high latitude electric field and aurora, we also have Weimer, Healy's, and aviation models. The physics model, it kind of like established upon the physical equations, the fundamental equations, and solve it numerically, do the digitalization, solve it numerically, and we also have steady state. Steady state can be understood like is actually not changing with time, but also can be say your wave amplitudes do not change with time. Okay, and we also for the steady state sometimes is forced by boundary conditions. For example, the stationary plane wave models can be forced by the boundary condition, and it can also be forced by external forcing. For example, the heating source, we can actually do that as well. Then in terms of the time involving models, and of course, because it's time involving, we have to give the initial condition in order to really trigger the whole model. And we have general circulation models, at least some examples. And for the traveling planetary wave model, and we also have to involve with time because it's it starts all the way from the initial condition and starts to generate those waves. And it's also similar for the ground wave models, such as MAGIC. And nowadays, the data assimilation model becomes more and more popular. And that's because every model has a limitation. Some of them are still, if you compare with observations, are still a little bit far off. So if we can actually apply the distribution, kind of like merge or fuse the information of the data of the observations into the physical models. Actually, it can be better used for prediction. It's kind of like your model then to some extent is better constrained by observations and supposed to be more realistic. Some examples are Welcome Dart, for example, and ECMWF and MERA, which are more like the lower atmosphere meteorology and the weather stuff. They all have the assimilation components. Okay, so this is an example of MSIS. And MSIS is the whole atmospheric empirical model of temperature and neutral species densities. And as you can see that it involves with the analytical formula, the parametric. Then you involve data and to do the fitting and get the parameters in these equations, which then you can further use for other locations where you do not have observations. And this is outputs of MSIS. The regular outputs include density of species, different neutral densities, and also the density and the temperature. Okay. And IRI is called International Reference Ionosphere, and this is also an empirical model, and it involves a lot of data from the radio observations, and of course from the name, it's going to provide a lot of information about the ion and electron composition. So the ions are included here, some examples, and also TC stuff. And it's very useful to look at the spread gap probabilities and aurora boundaries, and also the storm time ENF peak densities. And this is an example of the RI outputs. And this is showing the FOF2 in terms of megahertz. And you can see there are the ERA structures are very obvious from this figure. From this movie. Okay, so now let's move on to the physics model. The physics model, the first one I'm going to talk about the steady state. The steady state, it either talks, say, the mean values for wave amplitudes do not change with time. And we do have some examples right here that I'm going to go through. The first one is in terms of the global scale wave model. So this is a rough idea of how we have tides, and sometimes we can actually have a relatively first order picture of how the tides can be generated. So this is an equation that involves the heating, which comes to the J parameter, but there is no dissipation and there is no zonal and meridional momentum source in this case. So the atmosphere is actually frictionless in this case. So the nice thing about large scale wave is it has integer wave number. And also for tides, it has the periodic oscillation, which are predictable because they are subharmonics of a solar day. So to some extent, if you assume the waveform like this, you can actually simplify the 4D problem into 2D, because longitudinally and temporally, you can actually use this solution and plug into your equation sets. Okay, then you end up with the equations along the altitude, along the latitude, and along the latitude is actually the famous Laplace tidal equations, which we can use the spherical harmonics, the Legendre function or associated Legendre functions, which we call half modes. Half mode is the superposition of the Legendre functions. So we can use the half modes to actually characterize the tidal responses. And for certain tidal component, it does have some dominant half nodes, but it does change with season, but there are some dominant half nodes that can give us first order picture, okay, which is really nice. And the CTMT is a extension of the half mode, is a generalized form of half mode because it accounts for dissipation, which I said we're not showing in the previous equation. But if it's counted, which come up with the half mode extension, and if you fit the half mode extension to the data, then it can actually get the very nice ties oscillations in the MLT region. So this is the so-called climatology tidal model of the thermosphere developed by our colleague at Clemson. So there's these three components showing here. Okay, so another example of steady state is the stationary planetary wave model. So stationary means what? Stationary means it does not change with time. So basically you can get rid of del t, right? Because it does not change with time, the solution. And this looks a little bit of complex. So this is the under the QG assumption, quasi-geostrophic assumption. This is the equation about geopotential. So geopotential is combination of momentum equation and thermodynamic equation. Then you combine those, then you can get the equation for potential vorticity. And then potential vorticity and the geopotential actually they're related. They have quite straightforward relation with each other. So you can further convert the equation in this form, which is very, which is very good because it's a single solution equation for phi prime. But from phi prime, you can actually further derive what is u prime, what is v prime, what is t prime, for example, in this case. And for stationary planet wave, you can actually get rid of that. And another nice thing is, again, as I mentioned, because the large scale waves, they have integer numbers of longitude in terms of the wave number. So the delta lambda is longitudes. You can also simplify that. Then similar to the Laplace equation, the tidal equations, this equation can be actually simplified into 2D problem. Then you can see that the 2D problem is written like this. And so everything then comes up to this QM, which is called the refractive index square. So refractive index square is similar with the optical wave, propagation. Is very important to determine whether your electrical magnetic wave can propagate in the medium or not. And if this value is negative, means you do have the absorption or reflection in your medium, that your wave can stop propagating further inward, and pretty much your wave is gone. Okay, so for stationary wave, actually this also happens, and you can see this is the zonal mean wind, and this is the refractive index. And here, this is a positive wave refractive index, which waves can propagate. And if you go to other regions, pretty much it's going to block that one. And actually, this is going to be determined by zero wind line, because stationary planet wave has the phase speed of 0 in this case. And this is actually simulated. So you go with the lower boundary conditions like this. So this model is forced by lower boundary condition. So you go with a lower boundary condition, that internally your wave fields are going to be generated. So this is a very nice tool to actually diagnose how the mean winds are going to determine the propagation of the stationary planet waves internally. And you can see pretty much the wave are limited within these 0 lines. Okay, and in terms of the time involving, we can also start from the simple mechanistic model. So this is a very similar equation as the stationary planet wave, but this equation is we cannot get rid of del t anymore because it's the traveling waves, it's not stationary, so we remain this. Then what we do is we digitize that. We look at how the model advances with time. So that's actually what we want, right? And this is the simulation. So we start from a pretty much a random perturbation near the polar vortex. And then because the polar vortex is highly dynamic, the wave can absorb the energy from the mean wind and it starts to develop its own pattern. And in this case, there is a wave one traveling wave starts to be generated. And later on, it starts to stabilize and develop its pattern, and it becomes the short period traveling waves, which has period of like 3 to 4 days in my simulation in this case. Okay, so this is also very nice and it's time evolving. As you can see, it's changing with time. Okay, and another very good example is the gravity wave, the MAGIC model, the model for acoustic gravity wave interactions and coupling, developed by our colleague at Embry-Riddle and Rodrigo University, and Jonathan and his colleagues. So you can see the model is also based on partial differential equations, which has conservation of mass, momentum, energy, and also the heat equations, the diffusion and the convection stuff. And what they do is they can launch a gravity wave packet, for example, in the lower atmosphere, and let the wave packet to evolve with time and with space, with height and with time. And the gravity wave source usually can be a package, has the Gaussian form, and also has certain wavelengths and frequency, and which in this study is showing here. And this is the domain. And you can see a MAGIC model is very powerful in doing the high resolution and the regional domain simulations. For example, if there's a thunderstorm, there is convective activities, then generate gravity waves, how acoustic waves, how they're going to propagate, because those are very high frequency waves, then they can propagate upward and up, affecting the space weather. So how those waves are going to do. And these two simulations are the project that Dr. Li did in my class using the code provided by Jonathan. And you can see this is showing the wave reflection. And here, the part of the wave is reflected back and kind of forming the standing wave pattern. And some of them actually penetrate to the upper atmosphere. And this is an example using this model. We can see the wave reflection, and you can see the wave rays, the faces starts to tilt it and showing the reflection event. All right, so not last but not the least, I'm going to talk about the GCMs, so-called general circulation models, and I focus on two models. The first one is TIE GCM, the second one is Wacom, because my group run these two models quite often. So TIE, both models are community models, and TIE GCM represents for thermosphere, ionosphere, electrodynamics general circulation model. And it's, of course, very complex. It has a lot of equations. I'm not going to go into details, of course, but there is continuity equation, like usually what people have, continuity equation, neutral dynamics, and thermodynamics. But because TIE is a thermosphere, ionosphere model, an electrodynamic model, so it also deals with electron dynamics and electron thermodynamics, as these equations are showing. Then TIE GCM use the finite difference schemes, and you can see it using the leapfrog scheme in zonal momentum and meridional momentum equations. So literally, you have you have this partial differential equations like del T stuff. Then you start to crystallize those using, this is actually a center leapfrog scheme, the center in time. All right, and And also it applies the spatial filtering. So this is exactly the same as I mentioned earlier, because the small scale waves, the high frequency waves, they have the phase speeds distorted too much and cause the noise in the model and lead to instabilities in the model because they can grow too much. If they can grow significantly, those little jitters are going to kind of like explode your model and stop the model running. So we need to get rid of those high frequency noises, and spatial filtering is used in TI-HCM as it's showing. And this is for the vertical diffusion equation. And so this diagram shows the shows a rough structure of the TI-HCM model. So the whole, I mean, everything like internally, of course, is going to be related to each other. Different parameters, one affect each other, kind of like coupling back and forth. But the model itself also does have external things. For example, lower boundary is added externally, and usually it has min and tights in it. And the high latitudes, it's also driven by external drivers. Usually there are two drivers. One is associated with aurora, and the other one is associated with ion convection or electrical potential electric fields, the two cell pattern stuff. And the model outputs have many things, of course, as neutral things, and it also has ion, electron outputs. Okay, and this is a example. So we simulate a storm case using TI-HCM, and this is joule heating, neutral temperature, vertical wind at different altitudes. I think one is lower thermosphere, one is the middle thermosphere. And you can see when you go to the main phase of the storm, you start to have the significant joule heating. And joule heating is going to, of course, affect the thermodynamics of your the IT system. It starts to heat the temperature, starts to develop the upwelling because of the heating. And later on, these oscillations starts to propagate out as the wave forms. As the waves propagate, ITADs maybe propagating out and affecting the low and mid latitudes as they responding to the storm. All right. So the second one I want to mention is CSM, the Community Earth System Model. So CSM becomes very, very, very popular, not only in our field, but also in lower atmosphere colleagues, in people who are studying land, sea ice, river, ocean stuff, because it's really coupled model. And atmosphere model is one component, one subset of that. And for us, we usually run WACOM, whole atmosphere community climate model. It has a coupler that couples each component. So it's really complex. And I'm going to show a nice high resolution WACOM simulation developed by our colleagues at NCAR, Dr. Hanley. And I think probably many of you guys have seen this multiple times. And you can say, so in the lower atmosphere, there are prominent synoptical synoptical weather systems propagating eastward. But if we go to the higher altitudes, like 100 miles above, everything is dominated by waves. So this is the cyclone generated gravity waves and the breaking and tides in the mid latitudes, and it's very chaotic and very, it's like a boiling water. This is very cool. Okay. To summarize, I think numerical modeling is a lot of fun first, especially when your model can explain the observations, you really feel excited. And we know models are useful to explain observations, to fill up the observational gaps, because observations sometimes it still has missing data. in some like remote areas or the sampling stuff, which we cannot have the global observations at 24 hours. So it's good. It's also good to fill up observation gaps, and of course to study physical mechanisms. And you can design your own modeling experiment, numerical experiments in order to study the mechanism. And also is very useful for prediction, because you can run your model and predict for future. So that's then why model is sometimes is used for a prediction of hazardous weather, for example, hurricane, for example, cyclone, the tropical severe weather stuff, and also for space weather, and also used for climate change, what will happen, how people deal with that, accommodate that, and they can advance theories. And if there's significant discrepancy between your model and the observation, then people start to think what is missing, what important things are still missing in the model, which help to advance the theory. And last but not the least, I think no matter how fancy the models are, how great the model can show, the bottom line is we have to respect and serve data, serve observations. So that's why the data model comparison validation is still very important for us to do. Okay, so that's it. And thank you, everyone.
Thank you, Dr. Lu, for wonderful tutorial on different numerical methods and different atmospheric models. We'll have a quick 5-minute Q&A session now for you. So we have few questions for you, so you can unmute yourself to answer. So the first question is, what are the possible outcomes without removing high frequency noises? Dr. Lu is not able to unmute herself.
Oh, okay. So now
Yeah.
I can.
All right. Sorry.
All right. Okay. So the question is, what are possible outcomes without removing high frequency? Okay. So the outcome would be your model will blow up, and you end up with very big values, like 10 to the 30s orders of magnitudes. Then in the end, basically your model stopped running. So yeah, so your simulation failed in this case, which is very bad. we wanna avoid that.
Mm-hmm. So the second question, as you can read, is are the errors due to numerics and the discretization quantified in numerical models?
Yeah. Yes. Yeah. So when we think about to fully represent the partial differential derivatives, usually we use Taylor expansion, right? The Taylor expansion that involves with first order derivative, second order derivative, third order derivative, and even higher and higher orders derivatives. But in reality, we cannot do all of them, because the higher order we go, the more points we're going to involve. We cannot afford it, basically. So then we have to call a stop. So we stop at second order derivatives, which is already better than you just use first order derivative. Then you end up with truncation, your truncation arrows because of the higher order derivative stuff. So that's going to accumulate. When you run your model, and if you do not do something in order to compensate for that, so you may end up with some problems. And also computer itself also has, because computer is digital, so you also sometimes have some errors from the numerics as well. Yeah, It's a nice question.
Yeah.
Thank you.
And okay, so then another question, what is the typical delta T for different atmospheric models?
That's a good question, and it depends on which model you run. For example, right now I'm running for example, if I run TIE GCM, suppose I have two resolutions. The first one is regular resolution, say 2.5 degree, and in that case we can run delta T like 30 seconds, and O plugs maybe 10 seconds, and that are good enough because the resolution is still not that high. But then if I go to say even double the resolution, go to horizontal resolution of 2.25 degree, then my delta T has to also decrease correspondingly because there's actually so-called CTL criteria. If your horizontal resolution decreases, then some, more than often your delta T also has to decrease in order to really accommodate for your higher resolution, especially. So if I run double resolution, which is 1.25 degree, then I have to decrease my delta T to 10 seconds and O plugs to 1 second. So which takes a lot of time to run actually for higher resolution. Then for vacuum, if you run the regular resolution and for climatology run, you don't go to too much high resolution than maybe in terms of minute. It's okay. Then there also, again, then for magic model, for example, if you ask Jonathan or Chris for the resolution of magic, which is really high resolution, they may tell you second or even higher. I don't know. Then for my planetary wave model, I can even use I think it's I don't remember. I can even use days for delta T. So it really depends on what model you're running and what scientific problem you're looking at. Sometimes it's also limited to the scientific problem itself. If the science phenomenon is changing very, very quickly, then your delta T has to be small. But if not, then you may increase your delta T a little bit.
All right. So thank you, Dr. Liu. We will wrap up the Q&A session now, and we'll go for the short break before we start the next lightning session. So we will we'll come back in 15 minutes. Thank you. Thank you to all the speakers.
Hello, everyone. Welcome back from lunch. I hope you guys had a nice break. Right now, Mack Jones will be presenting the DEI's call to action, and this is from the CEDAR Diversity, Equity, and Inclusion Task Force. MacArthur Mack Jones is a research physicist at the U.S. Naval Research Laboratory in Washington, D.C. His work focuses on understanding how both external and internal drivers affect the climate and variability of Earth's upper atmosphere. Specifically, he is interested in our understanding of how synoptic scale waves of lower atmospheric origin impact the dynamics, thermodynamics, and chemistry of the ionosphere-thermosphere system using general circulation models. He is a father of 2 and enjoys playing Mario with his kids and playing golf in his spare time. Let's hear from Mack Jones.
Thanks, Megan. And I guess I'll first start by saying Happy Father's Day. I know that today is a special day for me and my household because it's a day where I can kind of be, you know, just a regular person and not have to be responsible for everything. So we'll see if my kids come and interrupt us during this talk. I think that would be a really cool thing to share with everybody on Father's Day. So that way give you a nice preview of what has been going on the last 15 months. But first, I'd like to just really start this sort of talk by, you know, paraphrasing a call to action or a line from a call to action for anti-racist science community for geoscientists of color: listen, action, and lead. And that is, to be silent on DEI issues is to be complicit in our own destruction, because racism, sexism, xenophobia, and LGBTQ related phobias destroys us all. And so, you know, over the past year or so, we've been, you know, the task force has been really working on tasked with improving sort of DEI in the CEDAR community. And the real motivation behind that was at the 2020 CEDAR meeting, community members participated in a workshop entitled DEI at CEDAR, where issues and practices regarding DEI and CEDAR surfaced. And so from feedback that we got, it was clear that it was a grassroots effort really was needed to really focus on sort of these related issues, these DEI related issues. And so we had 3 goals that we are really tasked with doing, and that's assess and formalize DEI efforts in CEDAR, establish and normalize a DEI presence in the CEDAR community, and foster improvement in CEDAR through implementation of actual initiatives that promote diversity, equity, and inclusion. And so below, at the bottom of the slide, you'll see I show the 8 members of the task force, all of which have been invaluable to the work that we've done. And I want to encourage anybody in the community that may be experiencing some sort of DEI related issue, please feel free to reach out to anybody on the task force, and we'll be happy to respond and assist in any way possible. And so really it's our hope that the CEDAR acronym not only stands for coupling of energetics and dynamics of atmospheric regions, but also represents sort of an inclusive community of scientists, engineers, educators, and students that promotes equity and diversity while showing allyship and respect towards and for the challenges that face CEDAR and the broader scientific disciplines now and into the future. There we go. Okay, so, but as you all know, not being silent entails more than just publishing statements or writing words, but actually taking action. So as such, the main role of the DEI task force, its duty really this far has been working on the following actionable steps for creating change in the CEDAR community. And so these actionable steps come from an active Google link or Google Doc link, in which you can go on, log on at any time and add to this. And these are about 6 of the roughly 30 proposed actionable items that we have that were a result of a community brainstorming session that occurred last year during the virtual meeting, during the virtual CEDAR meeting. And so here really green shows the items that are up and running or completed, if you will, in some ways. The yellow items are ones that are currently ongoing or ongoing conversations or preliminary actions have been taken. And then red are actions that are actual items that we'd like to work on here in the near future. And so over this first year, we focused on about 6 of these. The first of which was to include questions on the CEDAR registration, as well as the other Gem and Shine meetings, which I believe GEM is doing this, I think, to form or to obtain demographic information about participants, conveners, and speakers. And so hopefully when everybody filled out the registration this year, they filled these out. The goal here is really to see how we're doing in reference to the rest of STEM fields and the data collected by NSF, to have a baseline of where we could potentially target efforts. The second one, which has been a big one and has taken up a good bit of time, is to create safe spaces to enable members of the community and students specifically to discuss DEI issues. One of the things that we've done in this realm is to form these DEI happy hours, these CEDAR DEI happy hours that have occurred. I think we've had about 7 or 8 of them. Some of even which have crossed over with the GEM community, where we've done a joint CEDAR GEM DEI happy hour. And this is sort of the last Thursday of every month. We get together and we just have a conversation for an hour in the evening about DEI related topics, whether it be current events, whether it be the idea of safe spaces, how can we implement those, or how we can better be inclusive during virtual meetings, things of that nature. The third one here, which has been a really fun effort led by Angeline Burrell at NRL, is to create a group in CEDAR to proofread letters and recommendation letters or nomination letters to remove biased language. And so what was formed was this website, Equitable Letters for Space Physics. I've provided the link here below. And what you can do is you can, here shortly, right now, we're just accepting people who are willing to review letters, but soon we'll be accepting submissions to actually have letters of recommendations and nominations reviewed. And I think that's important. I think it's important that we recognize that we can all write better in any form, and to move any sort of implicit or explicit bias is important for any type of recommendation or nomination letter. The last 3 there, I won't go over step by step, but maybe the most important one is to connect with high school students during the CEDAR meeting and the student day. I know that that's something that Megan and Kamal have worked hard on. I've asked for volunteers. I know the virtual space makes it a little bit more difficult to deal with things like this, but it's at least something that we're continuing to think about, and would really like to see some volunteers help us out with this effort if possible. And so finally, there are a number of different ways that you can be involved with this effort. We are open to obviously adding more task force members, but one easy step is just sort of sign the CEDAR DEI call to action, which is also a Google Doc. I think we have roughly between 100 and 110 signatures now, people in the community. So if you haven't gotten a chance to read that and sign it, I think it's a great thing to do. Obviously provide input on the action items. The CEDAR DEI Slack, which is part of the CEDAR Science Slack, is a channel within that. We post articles, we share different opportunities and discuss things there. I think that's a great way to get involved, participate in the happy hours. We usually send out emails about these over the CEDAR mailing list. Obviously volunteer and encourage those to submit letters and recommendation letters to be reviewed to Equitable Letters in Space Physics. There's a number of different links here for the call to action for an anti-racist science community for geoscientists of color. And then obviously contact us about joining the task force, or reach out to us about anything that may be going on that you would like to discuss in sort of a free and open space. And so finally, I just want to preview some DEI speakers that are coming up at the conference. So Dr. M. Brandon Jones will be speaking on Wednesday in the plenary session for about a half an hour. He is the program director of education and broadening participation in the geosciences directorate at NSF. He will be speaking to us about these programs listed below, which promote diversity, but then also about the demographic makeup of the science and engineering community from the recent NSF 2019 survey of earned doctorates. And then please attend our session on Thursday afternoon, where we'll have 2 speakers and then a Q&A session with all of the speakers. The first speaker will be Dr. Melissa Burt. She is the Assistant Dean for Diversity and Inclusion at Colorado State. She's also a research scientist in climate science. And she is a respected colleague of mine and somebody who does really great work on DEI related stuff. And then lastly, our final speaker during that session will be Professor Matthew Kaplan from Penn State University. He's really going to speak to us about some of the work that him and his colleagues are doing on the idea of intergenerational language and how to better communicate with one another in the CEDAR community across a wide range of ethnic and age spectrums, if you will. So with that, I'd like to say thank you. And if anybody has any questions or wants to get involved, please feel free to reach out to anybody on the task force.
Thank you, Mack. Thank you for the talk and the great efforts that the DEI is doing under your leadership. So now we will start the second lightning round. In the first half of today, we heard about different instruments such as ground-based or remote-based and the models and how they provide us data to study the science that we do in this community. In this lightning round, we are going back to the basics on atmospheric concepts and events. There will be 6 talks total, with talks on ion neutral coupling, irregularities and instabilities, joule heating, sudden stratospheric warming, acoustic waves, and scintillation. These talks will give an overview of the diverse physical processes that we study in our field. For the Q&A, same format, please put your question at Slido with the speaker name, and we will ask the questions to the speaker at the end in the 15 minutes Q&A session, 15 minutes combined Q&A session. So with that, I will go to the next speaker. Our next speaker is Dr. Toshi Nishimura. Dr. Nishimura will be presenting an intro on ion neutral coupling. He got his PhD at Tohoku University, Japan in 2009. He worked at UCLA as a researcher until 2016, and he's now a research associate professor at Boston University. He received the AGU Outstanding Student Paper Award in 2007, the URSI Young Scientist Award in 2015, and AGU Michael Medal in 2016. He's currently the lead of the CEDAR Grand Challenge session on multi-scale ionosphere-thermosphere system, and his research interests are magnetosphere-ionosphere coupling by auroral imaging. So let's hear from Dr. Nishimura.
Hello, everyone. We are going to start back to the basics tutorial with ion neutral coupling topic. The ion neutral coupling is actually a common theme in 4 tutorials in this session. So I'm going to give an overview of the ion neutral coupling, including basic equations and key examples. And then Lindsay, Nick, and Pavel will give more details of specific topics in ion neutral coupling. So let me firstly explain why ion neutral coupling is an important topic. The International Space Station is a well-known platform in the low Earth orbit. It's at about 400 kilometers in altitude. The ISS is constantly falling down because of the finite atmospheric density up there. And there was a large geomagnetic storm back in March 2015, and the ISS suddenly dropped and became 150 meters below the expected altitude. That is a problem for the ISS tracking and operation purposes, and the same issue can occur to all the low Earth orbiting satellites. And there is a large momentum and energy exchange between ions and neutrals, so neutral density can largely vary and affect the satellite orbit. Therefore, the physics and understanding of the ion neutral coupling is very important for the space weather issues. Every 10 years or so, the National Research Council publishes a document that defines the priorities in space physics, and 3 of them are listed here. The first one is how does the ionosphere-thermosphere system respond to and regulates the magnetospheric forcing. Second one, how does the lower atmosphere variability affect the geospace? Third one, how do neutrons and plasmas interact to produce the multi-scale structures in atmosphere, ionosphere, magnetosphere system. So you can see that ion neutral coupling is recognized as an important topic at the national level. And CEDAR has its own strategic vision document. And one of the priorities in CEDAR is to understand the fundamental properties of the space-atmosphere interaction region. So it largely involves ion neutral coupling. So in the rest of the week, you will see many sessions and talks about ion-neutral coupling as a fundamental issue in our field. So we now understand why ion-neutral coupling is important. So to prepare for the session talks you're going to see in the rest of the week, so let's review the physics and key examples. The first equation is a momentum equation of neutrals. This equation describes wind speed change due to the ion drag force, pressure gradient, Coriolis, and other forces. When ions and neutrals collide, the velocity difference between plasma and neutrals drives a neutral wind. Nu is a collision frequency. And then the neutrals get redistributed. The pressure and other forces also contributing. The pressure equation is describing the evolution of pressure. The neutral pressure changes with the chemistry and heat exchange between ions and neutrals, the heat exchange between electrons and neutrals, and also the velocity difference between neutrals and ions is important. And this is particularly called Joule heating, expressed as a J.E term. And this energy is coming from Poynting flux supplied from the magnetosphere. We have to deal with a few more equations. The current continuity describes a relation among three key parameters. And these are the maps of the field line current, the conductance, and convection, looking from above the North Pole, the signs to the top. The field line current map shows us the two pairs of the currents, which are called region 1 and region 2. And conductance comes from two sources, solar UV emission and particle precipitation in the auroral oval. The convection describes a two-cell convection pattern of plasma. And the conductance further has two components, parascend and Hall, and both of them depends on the electron-neutral collision and ion-neutral collision frequencies. So this is a key part of the ion-neutral coupling. And these three terms are primarily forced by the magnetosphere and also the sun, but ion-neutral coupling modifies these terms through here, and then the MI coupling tries to find an equilibrium. Another important thing is a gradient in here. So the localized gradient in the conductance and the electric field can also affect MI coupling. So these are all important issues that's happening in the magnetosphere thermosphere coupling process. So, all right, so we got equations. So let's see how ion-neutral coupling works using some key examples. So this is a two-cell convection pattern we saw in the previous slide. On the right is a neutral wind distribution in the same format. Interestingly, the neutral wind also has a two-cell convection pattern. This is because of the ion drag force that we saw earlier. Ions accelerate neutrals, so neutrals eventually follow the plasma drift. That's particularly seen on the last side. But the downside is a little different. The downside wind doesn't quite follow the plasma flow. This is because other forces also contributing, particularly the Coriolis force, which tries to turn the wind westward against the ion drag, which is eastward. The neutral ion collision frequency is also involved in this ion drag term, and that is really useful because the inverse of that tells you the neutral wind acceleration time scale. And this time scale is usually long, tens of minutes to some hours, while the plasma drift quickly responds to the magnetospheric input of the order of minutes. When the plasma drift increases in red, the neutral wind eventually follows and creates a similar flow pattern like we saw in the previous slide. When the magnetospheric input suddenly weakens, the plasma flow gets really weak, but neutral wind can't slow down that quickly, so neutral wind is still blowing. So in this situation, the ion drag works oppositely. Now the neutrals are accelerating plasma, which it tries to, so the momentum is flowing the other way around. That is called a flywheel effect. Now the neutral wind can drive plasma. Another important thing to point out is that the wind acceleration time scale is highly variable. The top panel here is the altitude distribution of the plasma density. it goes up and down very quickly because of variable magnetospheric energy input. It largely changes wind acceleration time scale. The time scale is shown in the same format in the second panel. Initially, it was a few hours, so wind didn't really follow plasma much, but then it shortened to a few tens of minutes. We measured wind and measured plasma flow, as shown here. The wind was initially slow, even though the plasma drift was very strong. But at the time, when the time scale was shortened, the neutral wind suddenly started to pick up, even though the plasma flow speed wasn't changing much. So that's because the coupling between ions and neutrals got tighter because of strong electron density enhancement. So it is really important to understand the dynamic variability of magnetospheric energy input to understand the behavior of the ion-neutral coupling. Now let's look at the heating terms in the pressure equation. The Joule heating term depends on the percent conductivity, which is enhanced in the Auroral oval on the solar UV on the day side. Plasma flow, the V term, has a two-cell convection pattern. The wind usually has a similar pattern, that's U, so you can calculate the Joule heating. This map only considered high energy electron precipitation in the Auroral oval, but the low energy electron precipitation is also important, and that has a spot on the day side that is called a CLASP. And in the end, the Joule heating peaks in the CLASP region and moderately enhanced in the Auroral oval. And in addition, electron precipitation and ion precipitation roughly form this oval shape. You transfer the heat to neutrals and change the neutral pressures. All these terms are contributing to the neutral heating. And Lindsay Goodwin will later talk more about the Joule heating. It is difficult to measure the neutral pressure, but the neutral density can be measured. So this is a map of the neutral density drawn in the same format. And it is pretty clear that the neutral density has a clear peak in the CLASP region where the electron heating and Joule heating are taking place. So this heating process through this equation is indeed known to occur. And then coming back to this momentum equation, then the pressure gradient like this can drive additional wind and modify the large-scale wind pattern. So far, we have looked at the ion-neutral coupling in our oval high latitude. So let's shift the focus to the low latitude. The winds created by heating in the Auroral oval aren't really localized in the Auroral oval, but they can propagate away from the oval. And then the wind usually turns westward due to the Coriolis force here. The wind modifies also the thermospheric composition of major species like oxygen atom and nitrogen molecule called O2N2 ratio. The ion drag also occurs due to this wind, and the ion drag would redistribute the plasma and creates additional electric field at low latitude. They are called the disturbance dynamo electric field. And the signal also propagates as waves of the neutral density. They are called TADs, traveling atmospheric disturbances. The ion drag also modifies the ionospheric plasma density. They are called traveling ionospheric disturbances. So even though low latitudes are far away from the Auroral oval, the ion-neutral coupling in the Auroral oval affects the low latitude ion-neutral coupling processes. So it is very important to understand this global interaction processes, no matter which region you are eventually studying. So this is a simulation showing some of what we saw in the previous slide. So in this case, the Auroral oval is here. The Joule heating is suddenly turned on in the Auroral oval, and the heating increases the neutral density, as we saw earlier. That is shown in this color. And winds also enhanced. They are the vectors. The enhanced neutral density and wind propagate away from the source to a lower latitudes. And these waves are the TADs. And the ion drag perturbates the plasma density as well. So that is seen in the same way as the neutral disturbance propagates. So that is a TID. So they are actually indeed simulated in the model. Coming back to low latitude plasma structures, the low latitude ionosphere and thermosphere have some other interesting processes due to forcing from the lower atmosphere. So this is a map of the low latitude ionospheric density, and they show interesting longitudinal asymmetry. There are peaks and dips that can't be simply explained by ionospheric forcing. The important contributor here is waves and tides propagating from the lower atmosphere. So the recent simulations have shown that tidal waves have substantial effects on the ionosphere and thermosphere dynamics. One of the simulations is shown here. This calculation shows that more than 10% of neutral density it can be modulated by waves propagating from the lower atmosphere and create longitudinal structures like this. Nick Pedatella and Pavel Inchin will speak more details about the forcing from the lower atmosphere. So we have gone through lots of interesting processes happening in ion-neutral coupling. So I'd like to conclude this talk by mentioning the future of ion-neutral coupling. We have a lot learned already, but there are still many unknown issues. The NASA plans to launch a new mission called GDC, Geospace Dynamics Constellation. This is planned to launch in 2027, so many of you will have a chance to be involved in this mission. Now, neutral coupling is a key part of the science objectives of this mission. And 4 of them are listed here, determining how plasma convection and precipitation drive neutral winds. This is a momentum equation and ion drag we just discussed. Second thing, determining how the neutral winds, precipitation, heating drive the neutral density structures. This is a pressure equation that we talked about. We determine the relative importance of penetration electric fields and disturbance winds. We talked about neutral coupling and connection between high and low latitude processes, and identified processes that create and dissipate propagating structures within the ionosphere, thermosphere, TADs, TIDs. So these are exactly the waves we talked about. So if you understand the basic concepts we covered in this talk, you are ready to dive into these major open questions. It's important to learn the basics and current understanding to prepare yourself for exciting future opportunity. You will see many of them in this week. And that's it. Thank you very much.
Thank you, Dr. Nishimura, for the fantastic overview of ion-neutral coupling. Now, Dr. Titus Yuan will be presenting an intro on irregularities and instabilities. Titus received his PhD from Colorado State University in 2004. Currently, he is an assistant professor in the physics department at Utah State University. He has been the leading PI of the Utah State University Sodium LiDAR project since 2010, working on the development, deployment, and operating of sodium LiDAR. His work enables the robust, reliable daytime sodium LiDAR observation capability. Let's hear from Dr. Yuan.
Hello. For this talk, I will try to use some basic thermophysics principles to explain some atmospheric instabilities and demonstrate why they are very important for atmospheric dynamic and some prominent ion-neutral coupling process. I want to first show a cool movie about a typical wave-breaking event, which is likely induced by some kind of atmospheric instability. This movie is captured by the Advanced Mesospheric Temperature Mapper at Utah State University. As you can see, the wave enters the field of view of the camera from the bottom left corner, and everything is quite normal at the beginning. Large amplitude wave modulate the hydroxyl layer near 87 kilometer. And later on, the wave began to break up here, and quickly chaotic eddy structure appeared, and then the wave became turbulence and mixed with the background atmosphere. To understand the atmospheric instability, we have to first get familiar with the so-called hydrostatic equilibrium. This equilibrium is one of the most fundamental assumptions of our atmosphere and the atmosphere of the other planet. It is very easy to understand. If we look at a packet of air in this invisible box, it experiences gravity pushing it down, but it also experiences pressure force due to the pressure difference on top of the box and on the bottom of the box. If these two forces are balanced, this is the pressure force term and this is the gravity term, then this box will be just floating in the atmosphere without much vertical motion. Now, if we assume the thickness of the box, delta z, is very small, then we can change this equation to differential equation. So dp dz equals to negative rho g. From here, you can see the pressure is decreasing with height. Now, if we push this packet of air down a little bit, now the pressure force changes, and the two forces will not be balanced. We will have a vertical acceleration of the packet, but we will just leave it like that, and we will revisit this differential equation due to Newton's second law later in this talk. We all know ideal gas law from the thermal physics. It's PV equals to nRT. N is number of moles of air and can be calculated as atmospheric density times the volume divided by the average mass of the air molecule. For here, we can use the average. We can use the molecule weight of nitrogen gas to replace mu. And now we can rewrite the atmospheric density as P mu divided by RT based on the ideal gas law, and then put this rho back into our previous equation, dP dz equals to negative rho g, and we will achieve this pressure change with height. The equation of pressure change with height, dP over P equals to negative mu g divided by RT times dz. And that shows the atmospheric pressure is dropping with height. If we assume the atmospheric temperature is constant, basically in isothermal atmosphere, then we can easily calculate the pressure and atmospheric density are decreasing exponentially with height, z. And h here is the scale height. We call it scale height, equals to RT over mu g, which we already know. And as you can immediately notice, h, scale height, is a function of temperature. So at different region of atmosphere, you have a different scale height. If we here's an example. If we assume temperature is 0 and the average weight of air molecule is 29 g, and then we will have a scale height of 8 kilometers. If we go back and look at the differential equation from Newton's second law that we mentioned earlier, we can modify that equation a little bit. And then we can easily get a solution of the vertical displacement, dz equal to dz naught times e to the I square root of n squared delta n squared t. And this n square, based on the equation, is just a negative g over rho times the atmospheric density gradient. And this n square is the famous Brent-Wasserl frequency square. And from the solution of dz, we can see if the n square is positive and we have sustainable and stable oscillation. And we call this situation atmosphere is statically stable. However, if n square is negative, then the oscillation will not be sustained and it's unstable, and we will have static instability of our atmosphere. If we introduce the adiabatic concept in our consideration, since we know the temperature is changing all across the atmosphere, then we can modify the equation of Brent-Wasserl frequency square simply as g over t, t is the temperature, times the temperature gradient, plus a constant, 9.5 in this case, if we study MLT region. And this 9.5 is the adiabatic lapse rate, and we can easily calculate this 9.5 based on thermal physics. Now, if we introduce horizontal flow in this picture, for example, if we have a slow speed flow U1 and fast speed flow U2, these two flows will tend to interact with each other through vertical mixing. And this mixing process is called Kelvin-Helmholtz instability, or KHI. To prevent this kind of mixing, the static stability plays an important role here, because as we already know, the static stability prevent vertical displacement of this KHI interaction. So now we have a competition here. The positive n square will compete with the shear instability due to fast speed gradient. And the best way to describe this process is so-called Richardson number, which is the n squared divided by the square of shear magnitude. Based on theoretical calculation and observation, we found this 0.25 is a magical value for Richardson number. If the Richardson number is larger than a quarter, static instability wins. Further mixing and instability will be prevented. If it's less than a quarter, then we have dynamic instability, meaning the KH beta structure will continue to evolve and eventually become turbulence, and we have a complete mixing between the laminar flow and turbulence flow. Here are a couple of examples, all by numerical simulation in neutral atmosphere. The one on the right is done by Fries et al. In 2014, and the one on the bottom left is a plasma simulation by Lu et al. In 2015. So it is important to know when the flow will change from laminar flow to turbulence flow for our purpose. Based on thermodynamics, there are two kinds of flows. One is laminar flow, one-dimensional, relatively slow. The other is turbulence flow, which consists of all kinds of eddy structures and in all directions with different scales. The laminar flow can change into turbulence flow under certain conditions, and ununiform speed across the laminar flow is induced by the viscosity. To define when the laminar flow will change into turbulence flow, we introduce this Reynolds number. It is defined as the ratio between inertial force and viscous force. In this equation, we have density of the flow, rho, and the speed of the flow, and dimension of the flow. It also involves viscosity. There are two different kinds of viscosity. One is dynamic viscosity, and also we have kinematic viscosity. So when the Reynolds number is less than 2300, we have a very smooth laminar flow in one direction with less interaction with the background. However, if we have a Reynolds number larger than 4000, we will have turbulence flow, which is chaotic and has very efficient interaction with the background. The energy and momentum of the original laminar flow will transfer in or deposit into the background. Just like the gravity wave breaking, the initial smooth laminar flow of the gravity wave change into turbulence when it's completely mixed with background atmosphere. The turbulence processes are everywhere with all sorts of temporal and spatial scale. Unfortunately, GCM still cannot resolve all the turbulence processes and still have to rely on gravity wave parameterization to solve this issue. There's are a few successful turbulence measurement and calculation by LiDAR and radar instruments, but there's a lot more work need to be done. Now I want to talk about these atmosphere instabilities' role in the ionosphere instabilities and irregularities. One of the most prominent feature of ionosphere E region is the so-called sporadic E layer. It's a thin, high-density iron layers with different horizontal and vertical scale. Usually, the thickness is just a few kilometers. This example shows the common volume observation by an SR and coherent radar at mid-latitude, and through the observation of relative electron density, and the ISR can also observe electron temperature and major constituents of the E layer, and they are mostly metal layers, and we can also measure the horizontal scale of the sporadic E layer through the coherent radar. One thing you can notice that there's also some overturning structure or similar KH billow structure in the ES layer, and that is due to the dynamic instability or KHI that we talked about. They diffuse and distort the sporadic E in the E region. In summary, the atmosphere instability plays very important role in upper atmosphere dynamic and ion neutral coupling processes. They also contribute to the ionosphere irregularities. Instability induced wave breaking that can transfer the energy and momentum carried by the wave into the background atmosphere. Although we made some progress in turbulence measurement, they're still limited by just a few ground-based measurements, and we still need to work more on fully resolve the turbulence processes. Thank you.
Thank you, Dr. Yuan, for giving a short intro on irregularities and stabilities. Now we will move to the next talk. The next talk is from Dr. Lindsay Goodwin. She'll be presenting an intro on Joule heating. Dr. Goodwin has a bachelor's from University of Calgary, master's and PhD from the University of Saskatchewan, and she has postdoc from Boston University and then from New Jersey Institute of Technology, and now she's a NASA Jack Eddy postdoctoral fellow. And she also has a Manx cat named Zina who likes to complain. So I'll let Lindsay take the floor now.
Hi, everyone. Thank you so much for having me. My name is Lindsay Goodwin, and today I'm going to be talking about Joule heating in the upper atmosphere. So to start off, I'm going to give an introduction, but most of this presentation is going to be an introduction. Then I'm going to go into a couple examples of Joule heating that you can see within your own research. Then I'm going to talk about unresolved Joule heating topics. Then I'm going to quickly flip through all the references just so you have them for your own future studies. I like to start with really simple examples and really simple ways to think about these different topics. So Joule heating, when I'm talking about that, all I really want you to think about is that it's the heating that's produced when a current passes through a conductor. And I guarantee you that you have something in your home, your apartment or whatever that makes use of Joule heating. A very common example is a toaster. So a toaster contains a whole bunch of wires, and currents will pass through those wires, generate heat that then turn your bread into toast. And very similarly, currents will travel through the ionosphere and heat gases. Just to start to dip our toes into some formulations, we can write Joule heating as dP/dV, where P is the power and V is the volume, is equal to J dot E. So J being the current density and E being the electric fields. So from here, it's important to point out that something that's very common to do in the ionosphere is to put the electric field in the frame of the neutrals. And the reason why is that soon we're going to be talking about the relative drift between ions and neutrals, and it's a little bit easier to visualize that in the frame of the neutrals than it is to put it in the frame outside of either the ions or the neutrals or the electrons or whatever. But this is just something that's done for convenience. You can kind of do whatever you want really, and it just makes it simpler to visualize in general. So here we have J dot E. And we're going to say that's equal to J dot E prime, where E prime is the electric field in the frame of the neutrals, plus Vn dot J cross B, where the second term is the rate of work that's done by the ampere force. But we're not going to talk about that extra term. We're going to focus on J dot E prime. So now that we have this formulation, we can consider gases in a steady state and write J dot E prime is equal to sigma P E prime squared, where sigma P is the Peterson conductivity, or rather the ability for us to conduct an electric current parallel to the electric field. We can also say that J dot E prime is equal to rho I nu In Vi minus Vn squared plus rho E nu En Ve minus Vn squared, where rho is the mass density, nu is the collision frequency, V is the velocity, and subscript I is the ions, subscript N is the neutrals, and subscript E is the electrons. You'll notice that even though I'm adding in all these fancy terms, they all still have the same units, which is joules per second. So you'll see I expanded out here. This is joules per second, or J dot E, or the heat flow. And then over here, there are the units that we would see with the sigma P E prime squared. And then this is the units that we have with this last formula, or rho nu I Vi minus Vn squared. So it all makes sense at the end of the day. So breaking down that equation and looking at the first component and the second component, the first term in there describes the sum of the ion neutral frictional heating. I'm not going to go into great detail about it, but it is important to note that ions give their heat content to the dominant neutral gas through elastic collisions. Additionally, since the ion and the neutral masses are similar, particularly in the F region, where our dominant ion is oxygen plus and our dominant neutral is oxygen, atomic oxygen, they will contribute an equal amount to the Joule heating rate in ion neutral collisions. The second term here is the sum of the electron neutral frictional heating. And unlike ions, electrons will give their heat content to the dominant neutral gas through inelastic collisions. Once again, I'm not going to go into that, but that's just useful to know for your own researches. Additionally, electrons acquire the bulk of the power in their electron neutral frictional heating rate because their mass is so tiny. Because they are so tiny, it's essentially like hitting a ping pong ball with a pumpkin. You hit those two things together and the ping pong ball just shoots off. So electrons will acquire the bulk of the power. It's also important to relate Joule heating to temperature. So what I wanted to provide here was just a convenient way to like start to kind of do that. So for a given species, the energy equation that we have will contain a heat exchange rate as well as a frictional heating rate. So for the heat exchange rate, or QEX, we can say that it's rho I nu in over Mn plus Mi, 3 kb Ti minus Tn, where Mn is the neutral mass, Mi is the ion mass, Ti is the ion temperature, Tn is the neutral temperature there. But what's important to note is you have that Ti minus Tn term. That's the heat, that's key to the heat exchange. And we take the sum of all of that, and that's our heat exchange rate. And somewhat similarly, we have the frictional heating rate where we have rho I nu in over Mn plus Mi times Mi, Vi minus Vn squared. So sort of similar to what we've seen before, but now the key term is Vi minus Vn. So this is, instead of a temperature difference, this is a velocity difference that we have between ions and neutrals. And it's the sum of these two that we call the Joule heating rate. So combining those two things together. So given how critically important ion motion is for Joule heating, it's worth taking a quick detour and looking at the gyro frequency and the collision frequency. And in relation to these two things, we can discuss a highly collisional region and we can discuss a highly magnetized region. So a highly collisional region would be a region in which the collision frequency is much, much greater than the gyro frequency. So essentially what we have here is that ions are trying to travel along, but they keep undergoing collisions that dictate the motion that they travel. And then in cases where we have a gyro frequency that's much, much greater than our collision frequency, our ions will want to gyrate around the magnetic field, but then will undergo effects from the electric field and instead will ultimately drift along the E cross B direction. And so then we could describe these cases as magnetized essentially. So ions undergo the E cross B drift in magnetized regions, and ions will undergo the neutral wind drift in more collisional cases, and heating is introduced through electrostatic electric fields. This is important to consider when we start to actually think about the IT system. So the transition from collisional to magnetized is around 118 kilometers, which you'll notice is within the E region. So the gyro frequency to the collision frequency ratio will range from 0.09 to 2, meaning that in the lower E region, ions will follow the neutral wind. Otherwise, they are considered magnetized and they'll start to follow the E cross B drift. Meanwhile, in the F region, the ratio between these terms is 4.6 times 10 squared, 10 to the 2, to 5 times 10 to the 3 in that region. And what you'll have is like collisions will still occur, but the ions are magnetized and they'll be E cross B drifting within the F region. You'll notice that I'm not really talking about electrons and whether or not they're collisional or magnetized. And that's because electrons are considered magnetized throughout the whole ionosphere. In other words, their gyro frequency is much, much greater than their collision frequency, and they'll move with the E cross B drift. I do want to emphasize that just because something is magnetized doesn't mean it doesn't undergo collisions. Collisions are still important in these regions, but this just guides like how the plasma is moving within these regions. So it's also important to be able to identify what Joule heating looks like in actual data. And this is a very classic example of Joule heating. This comes from atmospheric explorer spacecraft data, or rather, this was in a publication from St. Maurice and Hansen in 1982. So over on this top here, we have the ion drift velocity. And you'll see that you have like a ion drift that like increases and increases as the spacecraft orbits through this region. And then there's a sudden reversal. And our ion drift velocity is still strong, but pointing in the opposite direction. Then over here, we have the ion speed, which increases, then it dips down during the reversal and then resumes because of these strong flows here. And then over here, we have the ion temperature perpendicular to the magnetic field. So you'll notice that the ion temperature increases with this initial bump in the ion speed, but then it drops down and plateaus out. And the reason why is because the ion drift velocity is initially going against the neutral wind. It's pointing in the opposite direction. So here we have a large amount of frictional heating, and then our frictional heating disappears as the ions reverse direction and start to follow the neutral wind. They're also provided on this figure are the MSIS neutral temperature, and this is just to substantiate that there shouldn't be a reason why the the neutral temperature would be leading to this increase in the ion temperature. And additionally, there's the O density and N2 density, suggesting further that this ion temperature bump is not due to like any other thing, it's due to frictional heating itself. So we can also find excellent examples of Joule heating within the E region. And one example was published in St. Maurice and Goodwin 2021. So in this case, in this top panel here, we have F region plasma flows that's from two different locations that are like nearby, but are just slightly separated in latitude. And we can see that there's an increase in the plasma flow here, which is directly related to an increase in the electric field. Because you'll remember earlier I said F region plasma flow is guided by the E cross B drift, and there'd be no reason why B would be changing. So this is an increase in the electric field. Now, keeping in mind that this electric field can penetrate and does like go into the E region, we can then say that this is also our E region electric field. And then going down into our E region, here we have the electron temperature at 110 kilometers. We can see that at the same locations, so blue is related to blue, and red is related to red in these two panels, that we also see that there's an increase in the electron temperature with this electric field that's in the E region as well. So here is also an example of Joule heating, but here it's going into the E region, heating electrons. So just to finish off this talk, I wanted to go into just a few of the topics that we still don't understand when it comes to Joule heating within the ionosphere. And the nearest and dearest topic to me is that we actually still don't know what nu IN is within the F region ionosphere, or rather, we don't know what the collision frequency between O plus and O is within the ionosphere, within the F region ionosphere. We do have some good guesses from Knopf et al. 1964, as well as Pesnel et al. 1997. But the reason why I'm calling these guesses is because we still have a lot to understand about the resonant charge exchange between O plus and O. And why I say that is because O plus and O have this relationship where if one collides into the other, your O plus can very easily become your O, and your O can become your O plus. So it just makes it very difficult to understand what the resonant charge exchange is between these two things. And it's very difficult to therefore characterize our ion neutral collision frequency within the F region. Another topic that you see a lot of talks related to, particularly if somebody's talking about Farley-Buneman, they might talk about this, is that we don't know what the E region electron heating rate is. So it's clear that like the electron heating rate depends on other processes. You'll notice before that as my plasma flow increased, my electron temperature increased almost like linearly, and we don't really understand why that is, what's causing that. But we are like pretty sure that like it has to relate to Farley-Buneman instabilities, and that plays like a huge role in the E region electron heating rate. The last topic that like I'm seeing is becoming more and more topical with like a lot of people is that we don't know how Joule heating cascades through different scale sizes within the ionosphere. So I emphasize flows a lot within this presentation, that like we have a lot of VI terms essentially, and VN terms and stuff like that. But we still don't really understand like all the different scale sizes of flows that we have within the ionosphere. So models have been very helpful in being able to like answer these questions and being able to model the smaller scale flows that like maybe our observations don't see. But overall, we still have a lot more to understand about mesoscale flows, like where they exist, how many there are, and like what's their magnitude. But yeah, that's all I really wanted to say. And thank you very much for your time. I appreciate it. And now I'm just going to flip through the references just so you have them for whatever you'd like to look up later.
Thank you, Dr. Goodwin, for that insightful introduction on Joule heating. I never realized my toaster had connections to this concept. Now, Dr. Nick Pedatella will be presenting an intro on sudden stratospheric warming. Nick Pedatella is a scientist at the High Altitude Observatory at the National Center for Atmospheric Research. His research is focused on the application of whole atmosphere models and satellite observations to understand the different processes that couple lower and upper atmosphere variability. Let's hear from Dr. Pedatella.
This presentation gives a brief overview of sudden stratospheric warmings as well as their impact on the middle and upper atmosphere. And I'm Nick Pedatella from the High Altitude Observatory at National Center for Atmospheric Research. So first, just a brief outline of what I'll discuss during this presentation. First, just give a brief overview of what sudden stratospheric warmings are, then the impacts of sudden stratospheric warmings on the middle and upper atmospheres, and then a brief discussion on whether sudden stratospheric warmings can potentially improve space weather predictions, and then I'll conclude with some outstanding questions. So first, sudden stratospheric warmings are dynamical disturbances in the high latitude wintertime stratosphere, and they influence the entirety of Earth's atmosphere. And this is a schematic showing all of the influences of sudden stratospheric warmings throughout the atmosphere. I'm not going to discuss all of these in the presentation, but just to give you a sense of the sort of effects are global and throughout the entire atmosphere, ranging from changes in tropospheric weather all the way up into the upper thermosphere and across from northern hemisphere to southern hemisphere. So sudden stratospheric warmings have several characteristic features in terms of their influences on the high latitudes in the stratosphere and mesosphere. First is a warming of the high latitude stratosphere, which is of course where the name comes from. These are some examples just showing the impacts from a composite of model simulations. So here is the altitude versus time, and the time is referenced to the date of the sudden stratospheric warming. And this is the zonal mean temperature at 70 degrees north. And here you see this warming of the stratosphere at the time of the sudden stratospheric warming, and that's associated with the cooling of the mesosphere. And if we look at this in altitude versus latitude in terms of the change in temperature that occurs during the sudden stratospheric warming, you see this warming of the stratosphere, a cooling of the mesosphere, and then a slight warming of the lower thermosphere. And you can also see these temperature effects extend across the equator all the way into the southern hemisphere mesosphere as well. And these temperature changes are associated with changes in the zonal mean wind. Here is a similar type of plot where we have the composite altitude versus time, and here now is shown the zonal mean zonal wind at 60 degrees north. And you can see there's a reversal of the winds in the stratosphere at the time of the warming, and this is actually how we define the central date based on the reversal at 10 hectopascal of the winds in the stratosphere at 60 degrees north. And associated with this wind reversal in the stratosphere is also a reversal of the winds in the mesosphere during the time of this stratosphere warming. And the formation of stratosphere warmings is due to the interaction of planetary waves and the zonal mean flow. And in the northern hemisphere, stratosphere warmings will occur roughly 6 times per decade on average. This is a time series of the yearly occurrence of the number of stratosphere warmings based on the zonal wind reversal at 60 degrees north and 10 hectopascal. And you can see there's time periods when they occur almost every year, and then there may be a gap for a few years, and then sometimes several, and periods where several will occur every year, and then some time periods where you don't have any for several years in a row. But on average, as I said, they occur about 6 times per decade. In the northern hemisphere, in the southern hemisphere, major stratosphere warming is a fairly rare event due to weaker planetary wave activity in the southern hemisphere. And now I'll go into some of the impacts of the stratosphere warmings on the middle and upper atmosphere. So first, there are large changes in the atmospheric tides during sudden stratospheric warmings, and this is in both the solar and lunar tides. And here are plots from model simulation showing these enhancements. On the left is the migrating semi-diurnal solar tide, and the right is the migrating semi-diurnal lunar tide. And the dashed line here indicates the timing of the stratosphere warming. And you can see there's a large increase in the amplitude of the tides following the warming in both the semi-diurnal solar tide and as well as the lunar tide. And the mechanisms for these enhancements have been studied by a number of researchers, and they're due to what is listed here. First, a change in the propagation conditions due to the change in the zonal winds that I previously showed that occur during sudden stratospheric warmings. There is also a change in the generation of the solar semi-diurnal tide due to changes in the stratospheric ozone during sudden stratospheric warmings. The tidal amplitudes are also changed due to nonlinear interactions between tides and planetary waves. And then there's also a shift in the resonance mode of the atmosphere towards the period of the lunar tide, which is a mechanism for the enhancement of the lunar semi-diurnal tide during the sudden stratospheric warmings. And these tidal effects essentially change the winds in the E region dynamo region, and that leads to large changes in the low latitude ionosphere, especially in terms of the vertical plasma drifts and also electron densities. Here's an example of the change in the vertical plasma drift velocity based on Hikamarka observations during the stratosphere warming. So the stratosphere warming occurred here, and so day of year is on the x-axis here, and then local time on the y. And this is a change in the drift, and you can see at the time of the stratosphere warming, there are these large perturbations in the vertical plasma drift on the order of 30 meter per second. So these are quite large changes in the vertical plasma drifts, and you can see they tend to have this sort of semi-diurnal character where there's a morning enhancement, and then roughly 6 hours later there's a decrease, which would be consistent with a semi-diurnal, with this being driven by a semi-diurnal tide. And these changes in vertical plasma drifts impact the electron densities. And here is an example showing at the same latitude as Hikamarka, the observed change in TEC. This is latitude versus local time now. And here on the top, you see the mean total electron content behavior during January 2009, and you see the expected sort of enhancement in afternoon. And if we look at the change in the TEC during the stratosphere warming, we see this increase in the morning and then a decrease in the afternoon. And these are about 50 to 100% change in TEC, which is a similar magnitude as we might see in a major, a moderate geomagnetic storm. And this behavior in the TEC with the morning enhancement and afternoon depletion is, of course, consistent with what is seen in the vertical plasma drift. So these TEC changes are, at least in the equatorial region, largely driven by this change in the vertical plasma drift velocity. And in addition, there's a significant change in the atmospheric circulation in the middle and upper atmosphere due to the dissipation of a variety of waves, both gravity waves, planetary waves, as well as tides. And here's an example, just cartoon schematic showing the circulation of the atmosphere before sudden stratospheric warmings. And due to this wave dissipation, you get an altered circulation during the sudden stratospheric warming. And this can have a large variety of effects, as I'll show in the next few slides. So first, the circulation changes can alter the chemistry of the middle atmosphere, especially at high latitudes. And an example of that is this enhanced downward transport of nitric oxide. These plots show the nitric oxide observations at high latitudes in the northern hemisphere for a variety of winters. And in the winters that have a strong stratosphere warming, say 2006 and 2009, 2004, you get this large descent of nitric oxide following the stratospheric warming, and this is due to the change in the circulation. And this is important because the nitric oxide, if it reaches into the stratosphere, can destroy stratospheric ozone and then potentially lead to effects at lower altitudes. The change in circulation also leads to a decrease in the atomic oxygen in the lower thermosphere, and then this propagates to higher altitudes due to molecular diffusion, and then you get a decrease in the upper thermosphere in the O to N2 ratio. And that's been seen in both simulations, as shown here on the left, where a few days after the sudden stratospheric warming, as indicated by the dashed line, there's a, say, 20% or so decrease in the O to N2 ratio at about 375 kilometers altitude. And then more recently, we've been able to see this in observations from the GOLD instrument. And here is a change in the column O to N2 ratio observed by GOLD. And at the time of the stratosphere warming, you can see there's about a 10% decrease in the O to N2 ratio, consistent with what we've seen in simulations. Another effect of the wave dissipation is reducing the thermospheric density and atmospheric drag. That's been seen in both observations on the left here, which shows a composite from satellite drag observations, showing a decrease at both 475 and 575 kilometers. At the time of the warming, you get about a 5 to 10% decrease in the thermospheric density at these altitudes. And by performing some simulations with enhanced wave forcing at the model lower boundary, it's been shown that the decrease in density that you would get due to enhanced wave forcing in this sort of magenta color matches the observed decrease, which is in the blue color. So this decrease is due to these changes in wave forcing, and then there's also a cooling that's associated with this few Kelvin in the thermosphere. And last, I'll just briefly discuss how sudden stratospheric warmings may contribute to improving space weather predictions. So sudden stratospheric warmings can be forecast about 10 days in advance. And here are some examples. This is for a sudden stratospheric warming in 1998, and these are based on the ECMWF forecasts. And the black line here is what actually occurred in the stratosphere. So this is stratospheric wind at 60 degrees north. And then the different dots indicate when forecasts were initialized, and the gray ones are unsuccessful, and then the red were successful forecasts of this sudden stratospheric warming. And you can see about 10 to 15 days before the warming, the forecasts start to be successful, and that is for one event here. Here is another example. There is some event-to-event differences, but on average, it's about 10 to 15 days. And if we can predict the sudden stratospheric warming effects in the middle and upper atmosphere, because we can predict them in the stratosphere, then we may be able to extend the range of useful space weather forecasting, at least during geomagnetic quiet time periods. And here is an example of that that we have recently looked at. And this is an analysis of 14 sudden stratospheric warmings in initialized hindcast experiments. And this shows this sudden semidiurnal tide amplitude during sudden stratospheric warming hindcasts. The dashed black line here is a verification field, and then the different colored lines is the composite of hindcasts initialized at different lead times, and you can see that there is this predictability of the enhancement in the semidiurnal tide in these forecasts about 5 to 10 days in advance. So it may be possible to get forecasts of the ionosphere thermosphere variability as well, since we can predict the tidal variations. And so just in summary, it's now recognized that sudden stratospheric warmings can have a significant influence on the middle and upper atmosphere. And the good forecast skill of sudden stratospheric warmings at least offers the potential to potentially extend space weather forecasting, especially during solar and geomagnetic time periods. And there are, of course, several outstanding questions, some of which are listed here that are still to be explored in the future. And I will conclude there. Thank you.
Thank you. Thank you, Dr. Pedatella, for the nice intro to occurrence of sudden stratospheric warming and its role in space weather forecasting, the middle and upper atmosphere. So the next talk would be from Dr. Pavel Inchin on the acoustic waves. Dr. Pavel Inchin is a research associate working at the Embry-Riddle Aeronautical University. He does research in atmospheric, infrasonic, and gravity wave dynamics and theory and application of Earth, ocean, atmosphere, ionosphere coupled processes from utilizing both numerical modeling and the observation-guided approaches. So let's hear from Dr. Inchin.
Good day to everyone. My name is Pavel Inchin and I'm a research associate in Embry-Riddle Aeronautical University. In this presentation, I will provide a short introduction to the phenomenon of acoustics and its manifestation in the MLTIT system. First, let's address the etymology of acoustic. This word, or its Latin synonym sonic, relates to the adjective audible, something that we can hear. And as the translation of information can be performed in the form of a propagating wave, from a physical perspective, broadly we define acoustic wave as a type of mechanical wave motion, which translates the energy by means of compression and rarefaction of the medium. And the first such interpretations date back to Greek and Roman philosophers, in particular to Aristotle, who wrote that sound is a certain movement of air. In such movement of air, the restoring force responsible for the propagation of a wave is simply the pressure change, and acoustic wave is compressional in nature. Thus, at least with linear assumptions, it is a disturbance rather than the fluid itself that is moving with this wave. So the disturbance may propagate large distances, whereas the fluid particles themselves remain all the time close to their original position. Acoustic waves are also longitudinal waves, because the induced fluid velocity is parallel or antiparallel to the direction of wave propagation. Generally, acoustics include a wide variety of activities that affect our life every day, starting from communication, through art, applications in medicine and engineering, to geophysics and planetary studies. And in my presentation, I will only slightly touch one of the branches of acoustics, sound in the atmosphere. To warm you up, now you will see the video of the effect of propagation of acoustic shocks in the atmosphere generated during the eruption of the volcano.
Watch out for the shock, it's coming.
Addressing the wave phenomenon in the atmosphere, we see that acoustic waves are characterized by comparatively high frequencies, with ultrasonic waves of higher than 20 kHz through the audible to human spectrum of waves between 20 kHz and 20 Hz, and down to infrasonic, so-called acoustic gravity waves, the waves for which, in addition to comparative elastic force, the gravity force starts playing role. For those interested in other types of atmospheric waves, I provide references to CEDAR presentations from previous years on this slide. There are many natural and man-made sources of acoustic waves readily or potentially detectable in the MLTIT system, and some of them are presented on the slide. Due to the coupled nature of the geophysical system, the energy from Earth or ocean interiors, for example associated with earthquakes or tsunamis, can leak into the atmosphere in the forms of acoustic waves. Convective and thermal sources in the troposphere include hurricanes, tornadoes, thunderstorms, and lightnings. Acoustic waves can also be generated from the evolution of atmospheric waves of larger scales, or even be generated by auroral activity. And I will show you a couple of examples of acoustic gravity wave detection in IT system. On this slide, you may see the animation of perturbations in GNSS TEC over continental US. During the morning section, you may have seen the presentation devoted to this measurement technique, and I also provide references to previous CEDAR presentations related to it. The red circle defines the position of tornado of category 5 that occurred at that day. In addition to long-period concentrically propagating perturbations that are driven by gravity waves, you may see rapidly propagating fluctuations to the south from the tornado location. Their periods are in a range 3 to 4 minutes, and apparent propagating horizontal phase velocities are around 900 meters per second, consistent with the speed of sound at the bottom of ionospheric F layer. Another demonstrative example is the detection of acoustic gravity waves that were excited during the 9.1 magnitude earthquake in Japan in 2011 from the rapid uplift of ocean surface induced by seafloor deformation. Again, on the slide you see fast propagating perturbations in TEC that are driven by strong shock acoustic waves. Let us investigate main characteristics of wave dispersion equation and the propagation of acoustic waves in the atmosphere. For simplicity, we first consider a windless, lossless, and isothermal atmosphere, omitting all quadratic terms in perturbations. We also assume that the atmosphere acts as an ideal gas, obeying appropriate equational state. Considering two-dimensional problem and adjusting axes in vertical and horizontal directions, we may derive the system of fluid equations shown at the top of the slide. Assuming plane wave solution, we can then find a non-trivial solution of this system and derive the frequency dispersion relation. First, you may notice that there are two entirely different internal wave zones in the dispersion diagram presented on the slide. One is for waves with frequencies higher than the so-called acoustic cutoff frequencies defined in the zones of acoustic waves. Another one includes waves whose frequencies take the isothermal Brent-Weissel frequency as its upper limit, whereas waves in between region are evanescent. We may also compute phase and group velocities from this dispersion equation, obtaining the expressions for horizontal components. For gravity wave zone, we see that they never exceed the speed of sound. For sound waves, with the increase of frequency, we have both group and phase velocity approach the speed of sound, meaning acoustic waves of comparatively high frequencies are non-dispersive. However, as frequency approach acoustic cutoff, the phase velocity moves to infinity, whereas group velocity moves to zero. Let us now investigate the propagation of acoustic gravity waves in the realistic atmosphere to demonstrate the most important effects. Up to a certain level of approximation, the atmosphere is a stratified media, which means its main parameters mostly depend on altitude. The atmospheric density decreases practically exponentially with increasing altitude due to the effect of gravity. Likewise, the fluid velocity of acoustic waves propagating upward increases as a root of density as a consequence of conservation of wave energy. Such upward amplification is an important reason for the possibility to observe excited at the ground level acoustic waves even at ionospheric heights. The atmosphere is mainly composed of nitrogen, about 78%, and molecular oxygen, about 21%. The decrease of their densities is followed by increasing density of atomic oxygen starting from mesospheric heights that plays a crucial role in the chemical and radiative energy budgets in the upper atmosphere. And higher than around 400 kilometers, this is a dominant species. This density variability leads to the change of average molecular weight and thus the ratio of specific heats for air from 1.4 at altitudes below 80 kilometers from dominant diatomic gas to 1.67 for monoatomic gas. In turn, it results in the change of speed of sound. The temperature also varies from ground to thermosphere, substantially affecting the speed of sound. Having the values of around 343 meters per second at the ground level, the speed of sound decreases up to roughly 11 km heights, then increases in the stratosphere, then reverses up to mesopause altitudes, exhibiting values below 300 meters per second, and then again drastically increases in the thermosphere, reaching values of 8 to 900 meters per second. Mentioned two minima in sound speed serve as important turning points for acoustic waves, having positive speed of sound gradients and thus refracting acoustic waves downward. Generally, one can derive that acoustic rays always bend to the area where the sound speed is smaller. Likewise, the winds in the atmosphere affect the propagation of acoustic waves. When the wind is blowing in the same direction as the sound is refracted towards the ground, and vice versa. Finally, we talk about absorption of acoustic waves. First, the waves decay with propagating distance due to their spreading, refraction or scattering. That's called together as geometric attenuation. Secondly, waves decay from the absorption of their energy by the propagating medium itself from thermoviscous dissipation, leading to the absorption of part of acoustic wave energy via internal friction between gas molecules and the transformation of wave energy into thermal energy. The contribution of absorption mechanisms depends on atmospheric state and wave characteristics. In cases, the absorption by vibrational and rotational relaxations that results from atomic structure of atmospheric molecules themselves can be important. Likewise, the inhomogeneities in the atmosphere, for example from rain, snow, turbulence, may markedly affect acoustic wave propagation. Wave fluid velocity amplification with altitude can lead to the importance of nonlinear effects in acoustic wave propagation. In this case, propagating velocity of the acoustic wave is a function of wave amplitude itself. Where the amplitude is larger, the propagation is faster, leading to the steepening of waves. These steep wavefronts are what we usually call acoustic shocks, and they represent a phenomenon of an abrupt change in state parameters. We may find this distance and time required for harmonic wave to become a shock wave. The distance depends on the so-called Mach number that represents a ratio of fluid velocity of acoustic wave to the local speed of sound. Additionally, this distance is directly proportional to the wavelength of acoustic wave. Along with the steepening of the wave, the absorption effects start playing crucial roles, and the simplest but demonstrative equations that combines both nonlinear propagation and diffusive effects is the so-called Burger's equation that is used in many analytical investigations. Finally, when a shock overtakes another shock, they merge into a single shock of an increased amplitude, eventually forming in the so-called shock N wave, as its shape resembles letter N. This shock N wave then may exhibit lengthening, resulting in the increase of period of the signature. And let me now demonstrate these effects with the animation from simulation of acoustic gravity wave propagation excited by seismically induced surface displacements. The altitude frequency diagram to the left can be used to investigate acoustic wave evolution. The generation of acoustic wave high-frequency spectrum between the ground and mesopause is a consequence of the formation of shock waves. At higher altitude, thermoviscous dissipation leads to attenuation of high-frequency acoustic waves along with shifting of acoustic wave spectrum to low frequencies due to the lengthening of nonlinear shock N wave. We may also see a refraction of waves driven by temperature gradients, notably at turbopause altitudes around 100 kilometers. We also see the second packet of acoustic waves propagating from the ground level, which results from trapping of acoustic waves between lower thermosphere and the ground. In the time left, I'd like to demonstrate the applications and studies the scientific community is working on in the field of acoustic waves in the MLTIT system. With the improvement of data coverage, there appears to be clear pathways towards the incorporation of upper atmospheric observations of acoustic waves from below into the analysis and constraining of their sources. For example, some studies are focusing on the possibility to evaluate the tsunamigenic potential of ocean surface displacements from the sounding of related acoustic waves in ionosphere. On this slide, you may see a diagram that represents the relationship between seafloor maximum volume displaced and total electron content perturbations induced by acoustic gravity waves. Such observations may serve as an independent source of information to supplement traditional ground-based tsunami early warning systems that in cases may fail in the identification of tsunamis. Recent studies also demonstrate that some aspects of earthquake rupture progression can be constrained from upper atmospheric observations and modeling of seismic acoustic gravity waves. This may be particularly important for undersea or complex earthquakes, for which classical ground-level seismic observations cannot provide sufficient information. Last but not least, the investigation of the dynamics and the resulting energy deposition from these waves in the upper atmosphere is in the focus of our community. Let me summarize. The detection and quantification of acoustic wave in the MLTIT systems is still challenging. This is connected with comparatively short periods and small spatial scales of disturbances generated by these waves. For example, the periods of acoustic gravity waves driven by the largest earthquakes are in the range 2 to 5 minutes, with spatial scales of tens to couple of hundreds of kilometers of wavelengths. In many cases, the signals are also fairly weak. Our understanding of Earth's natural infrasonic environment is largely phenomenological and lacks quantitative analysis of how and to what extent these waves affect the dynamics of the upper atmosphere. We also do not fully understand what information detected acoustic wave signals may provide about their sources due to the complexity of the propagating media, nonlinear evolution of wave, and induced by them perturbations in the upper atmosphere. However, the improvements of observational techniques and modeling capabilities currently allow investigating acoustic waves in the upper atmosphere on unprecedented levels of details, and there are many directions to go and opportunities to pursue. For those interested and new to this topic, I provide a list of literature on this slide. And thank you for your attention.
Thank you, Dr. Inchin, for the fantastic introduction on acoustic waves. Now we will have our last talk of the lightning round. Dr. Sebastijan Mrak will be presenting an introduction on scintillation. Sebastijan Mrak is a postdoctoral associate at Boston University. He's developing GNSS-based remote sensing diagnostic tools for sensing and reconstruction of ionospheric space weather. Let's hear from Dr. Mrak.
Hello everyone, I am Sebastijan Mrak, and in this final tutorial presentation, I will overview the topic of radio scintillations. Radio scintillations are defined as random fluctuations in radio waves amplitude and phase caused by atmospheric turbulence. There are two atmospheric regions that can scintillate radio signals. The first is the troposphere, where the turbulence resides in the rain clouds and scintillates radio links at frequencies primarily above 10 GHz. The second region is the Earth's ionosphere, which can scintillate radio signals at frequencies below 3 GHz. And this includes all frequencies used by GNSS constellations. In the figure on the right, I'm showing one example of scintillating signal-to-noise ratio, SNR, measured by one GPS receiver. And in the remainder of this video, I will be discussing why these GNSS SNR fluctuations are important, what is the physical mechanism producing them, and how do we measure them. First, let me discuss why would anyone care about scintillations, and in particular in the context together with the GNSS. GNSS provides timing, positioning, and navigation services that are invaluable to many industries. The National Institute of Standards and Technology, for instance, solicited a report on the general importance of the GPS to our economy. GPS was the key enabling technology for the new generation of cellular networks, for instance, for the telecommunications. GPS plays a crucial role in several other industries. In fact, the authors of this report estimated that a single day of the GPS outage would incur more than $1 billion in losses. And here, the most important natural hazard to the GPS services are ionospheric scintillations. To the importance of CEDAR community, on the other hand, these scintillating signals measured by GNSS receivers could be used as a diagnostic for studying ionospheric space weather, in particular, the ionospheric irregularities that produce scintillations in the first place. Now, let me briefly review the propagation geometry and some basic ionospheric parameters that were discussed by Seebany in greater detail. Satellites broadcast radio waves towards the ground, where they bend or interact with the ionosphere due to changing index of refraction. If these initial plane waves illuminate a region of localized, highly variable ionospheric turbulence, then the exiting wave is not a plane wave anymore. It is highly non-uniform in the plane perpendicular to the direction of propagation. This is due to the changing electron density or changing total electron content. In this case, this plane waves can interact with each other and cause interference during the propagation towards receiver. And this interference causes signal scintillations. In this slide, I will introduce the physical mechanism of the interference and its properties. Let's consider the later part of the previous illustration, where we described the non-uniform wavefront exiting the ionospheric turbulence. That wavefront deviates from a plane wave as described by a contribution of total electron content and varying total electron content delta TEC, which is due to the ionospheric turbulence. This description will be called phase screen approximation. The electric field at this phase screen can be written with the equation below. This equation has three phase terms. One is due to the total distance traveled of the radio waves, due to the total electron content TEC with this N sub T, and the contribution due to ionospheric turbulence delta N sub T. If this term is small, we can rewrite that equation in this form. Now we take a look how to describe electric field at any point beyond the phase screen. This is done with the Fresnel diffraction formula. And what this formula tells us is that the total electric field at any point x, y, z consists of two contributions. First is the direct field, the field that would be there without any phase screen or any ionosphere. And the other term under the integral tells us what are the contributions to this electric field over here due to the contributions of the phase screen from x prime, y prime deviation from the origin of the plane field approximation, which is which can be denoted as these R vectors. So we are looking at the phasor sum of all possible vectors coming from this cone. What can we do then next is to split this electric field into a contribution of the magnitude, of the amplitude and phase. And what we get is that the amplitude is due to the initial magnitude of the direct wave, modified by this contribution, which is due to the Fresnel diffraction integral. If we do the same thing for phase, we look for the imaginary part of this equation, we see that the contributions come from three sources instead of two. One is the direct wave, modification due to the total electron content, and modification due to the diffraction. Therefore, in phase, diffraction is only the second order correction to the total phase. We can see that this integral actually has a form of a convolution. And if we assume that this later part of the integral is the ionospheric impulse response, compute its Fourier transform to get the system response and go from electric field to the power. Power is proportional to the electric field squared. We get this standard set of formulas which describe phase, power, spectral density of amplitude and phase at any location z in the direction of propagation. What we can see is that this power spectrum of both depend on the power spectrum of the ionospheric turbulence, which is filtered by the ionospheric filter. And the total spectra would look something like this. So on the receiver plane, if we have the ionospheric turbulence denoted with this dashed line, then the amplitude perturbations would look something like this red line, with a peak at so-called Farnell's scale, which peaks at about several hundred meters for the GPS frequencies. On the other hand, the phase is low-pass filtered, so the majority of power in the phase fluctuations come from the wavelengths of much bigger spatial wavelengths. What we've learned is that the resulting scintillation spectra depends on the irregularity strength and the filtered spectrum. A receiver, however, measures the irregularities as a function of time, not space. So the spectra has units of omega, not k. The time series measurements experience a shift in the resulting spectral density, which varies with the regularity, drift speed, and the Farnell scale. The peak of the scintillation spectra is found around Farnell frequency nu-f, as depicted above. This image also shows that GNSS receiver have to sample the signal intensity at sufficiently high sampling frequency in order to capture the whole scintillation spectra at high drift velocities. GNSS scintillations are normally measured by ionospheric scintillation monitoring receivers, which provide measurements with sampling frequencies up to 100 Hertz. Here is one example of observed scintillation spectra from Antarctica. This shows a distinct peak in amplitude fluctuations at around 1 Hertz. This 1 Hertz would translate to the causing ionospheric turbulence drifting at several hundred meters per second. We see here that the measured scintillation spectra therefore can be used as a diagnostic for the causing ionospheric turbulence. We can find what is the spectral shape of the turbulence, what is the drift of the turbulence, and what is the origin of the turbulence by identifying Farnell scale. Observations of scintillations are usually measured with scintillation indices instead of actual fluctuations in time series. Usually, we use 3 most common scintillation indices. The first one is the S4, the intensity scintillation index defined as a normalized standard deviation over a period of 1 minute, where these brackets in the equation denote temporal averaging. We have sigma phi, or the phase scintillation index, is defined as a standard deviation of the detrended phase over a period of 1 minute. The detrending processing is arbitrary. However, it is usually a high-pass filter with 0.1 Hertz cutoff frequency. And the last one is ROTI, the rate of TEC change index, which is defined as a standard deviation of temporal TEC changes over a period of 5 minutes. The images below depict a typical space weather situation. ROTI image was derived from worldwide network of GNSS receivers and shows 2 distinct regions of elevated ROTI, one near the magnetic equator and the other one at high latitudes over Alaska here. But in order to find the regions of actual scintillation, the observation needs to agree with the scintillation definition, which is that the scintillations are fluctuations in phase and amplitude. Now, figure on the right-hand side depicts the occurrence of amplitude scintillations measured by the S4 index. The measurements here, however, come only from the American continent, not worldwide. But nevertheless, the image shows that only one of the 2 regions of elevated ROTI also measured amplitude fluctuations. Thereby, the signal perturbations from Central America were due to Farnell diffraction, therefore actual scintillation, whereas the elevated ROTI from Alaska and Canada was only due to irregularities with much bigger spatial scales. Therefore, ρt and sigma phi are general measures of irregularities. Only S4 measures scintillations only. Now consider the measurements taken from a GNSS receiver mounted on a satellite in the low Earth orbit. Here, the propagation geometry differs from the situation on the ground because the propagation distance L to the irregularities and the satellite at high elevation angles are very short. In this situation, the amplitude fluctuations vary rapidly with changing range, and so are varying phase fluctuations as varying range. In fact, at very small distances L, amplitude fluctuations are about zero or negligible. At the same time, phase fluctuations at very small distances are very small too in magnitude, but they change very rapidly. So in this bottom plot, we plot delta phi over dt, which has units of hertz. And we see very, very rapid changes in phase, despite the phase doesn't change much in amplitude. Nevertheless, GNSS receivers have very hard times tracking this phase. So for the low Earth orbit GNSS, for the lower orbit satellite receivers, the fast changes in the received phase d phi dt are causing losses of log, and hence these are the most prominent scintillation manifestations on LEO GNSS receivers. And lastly, we take a look at the global morphology and occurrence of GNSS scintillations. Whereas measured from the ground using S4 or actual amplitude fluctuations, or from the low Earth orbit using loss of log indicator, we see that there are two distinct regions that cause signal scintillations. One is adjacent to the equator, and the other one is near high latitudes. This is due to the particular ionospheric turbulence that is conducive to the orientation of the magnetic field. What we see also from these climatological pictures is that the scintillations vary with solar activity. They vary with geomagnetic activity, and they have very big longitudinal asymmetry. In summary, I want to resonate the most salient features of the ionospheric scintillations and their impacts on GNSS services. First, the physical mechanism causing the scintillation is Fresnel diffraction, which depends on the irregularity strength and the radio propagation geometry, featuring radio frequency, distance from the irregularities, and the irregularity scale sizes. The most potent irregularities have spatial sizes in the vicinity of Fresnel scale. Second, scintillations impact GNSS receivers with reduced signal-to-noise ratio, causing reduced system robustness, and with rapidly changing phase, causing losses of log. Scintillations are random phenomena, very difficult to mitigate in a straightforward manner. Scintillations observed can be utilized to study statistical properties of the ionospheric turbulence. Receivers with high sampling rate are the necessary requirement. And the global morphology of scintillation climatology is actually very well known, but the prediction of actual positioning, timing, and lifetime of the causing irregularities remain the active area of research.
Thank you, Dr. Mrak, for the wonderful presentation on scintillation. We just finished our series of short talks on the different physical concepts in our field. We will now have our Q&A session with our speakers, and I will ask questions for the audience. I will ask questions to the speakers in order of the talks. Speakers, when it's your turn, feel free to unmute yourself and turn on your video if you would like. The first question is to Dr. Nishimura. Dr. Nishimura, can the interaction between ions and neutral winds create heavier elements that can increase the overall mass of the plasma in movement? How would the energy transfer be in that case? Toshi? I do not have the permission. Okay,
He should be able to unmute himself now.
Thank you, Rita.
All right, here it works. Yeah, thank you. Yeah, thank you for the question. This is a very good and important one. So the heating creates mass distribution change. So like when you have the strong heating, heavier ions and neutrals can be lifted up because the scale height will change. There can also be upwelling. That's the reason why we have the heavy, we have the strong, the large mass density, the CLASP region at high latitude day side. So when that happens, the chemistry will change. There can be recombination, there can be the wind change. So that will change the way how the IIT system will respond to the next energy input. So that's interesting two-way feedback between ions and neutrals. So it's a really important dynamic system. So we need to understand all these dynamically to solve this question.
Thank you. I'll ask you one more question. We'll go with the next one. In your opinion, what observational capability are we lacking the most in terms of measuring ion-neutral collision frequency or other coupling mechanisms?
Yeah, this is another great question. So what we are critically missing is the composition. We can measure density, plasma flow, neutral wind, and also temperature in a reasonable way. But are we looking at oxygen dominant ionosphere? Are there any large nitric oxide? So those are really important because what species we have up will determine the collision frequency or the recombination rate and so on. But we don't know them usually. We only know there's the big plasma density or neutral density. So the lack of understanding of the composition is usually creating a problem of knowing how tight the system responds. Another thing is the scale dependence. We can measure large scale things with low resolution instruments, but important energy cascading is occurring at smaller scale. Saturation is one of them, like what Sebastian has talked about. We don't have a very good understanding what's going on smaller scales. So cross-scale coupling to resolve the small scale structure, that's been the important open question in our field.
Thank you so much, Toshi.
Thank you.
All right, next we will talk to Dr. Yuan. Our first question for you is, what is the dynamic instability? Can you explain a bit more?
Okay. So dynamic and so instability means that the flow will break and the mixing with the background or with the other flow will happen. Like I introduced in my slide, if this competition between static stability and shear instability proceed, the extremely large wind shear in the denominator will beat out the static stability, which is you have n squared larger than 0. And then if that happens, the shear instability will win, and you see the curving and curving of the KH below will get bigger and bigger, and eventually it will become turbulent structure and mixing with the with the in situ atmosphere will happen. So the dynamic instability is defined that this breaking of what flows or breaking of waves happen. So in this way, just due to mainly due to the large horizontal wind gradient. The other instability that I talked about is sort of it's the vertical motion. So if you have a packet bounce back and forth between its equilibrium position, and that's okay, that the oscillation is stable. There's it's, for example, if you have a gravity wave just propagating up and oscillate without breaking, then it is still a stable oscillation, it's still a stable propagation. But when you have the n square less than 0, induced by very large, mostly introduced by a very large negative temperature gradient, and then the oscillation will either decay or just break up. So that's, you can use that description to explain lots of wave breaking event in that we've seen in the MLT region, or even in the lower atmosphere. Hopefully, does that answer your question?
Yes, I think so. One further question. Does the spatial scale of instabilities change at different latitudes?
Oh, that's a great one. Let me think. Spatial scale. Well, okay. I think it will change, because if you think about it, there's a scale height term in the calculation, and the scale height varies with altitude. So at different altitude, scale height will be different, and that probably will likely define the will have some effect on the scale of the instability. And also there are lots of gradient terms. Vertical for example, du dz term, dt dz term, and different region of the atmosphere obviously has very different gradients, temperature or either horizontal gradient. So that also play some role and contribute to the scale of instability.
Well, thank you so much, Dr. Yuan. Next, we're going to go to Dr. Lindsay Goodwin. Lindsay, the first question I have for you is, what is the typical method joule heating is measured with?
So that's kind of a cool question. Also, you can hear me, right?
I can hear you, and I can see your cat, and I love her.
See, I had to prove I had a cat, but yeah, the typical method that joule heating is measured. So yeah, assuming you're meaning the heating rate, that one you can like measure it with a model, or you can use observations. And typically, what you would do is you would use the parameters that would go into the joule heating equation. For example, like you'd have to measure like the neutral winds, you'd have to measure like the ion flow, the ion temperature, and the neutral temperature, things like that. But kind of related to what Toshi mentioned earlier about like observational capabilities, there's some ambiguity sometimes about what we're actually measuring. So for example, like if you have like particles that are drifting up, then like maybe the mass will change. Yeah, she's gonna run away now. Maybe like the mass density might change. So yeah, there are some difficulties with trying to measure like these things with like instruments, but yeah, hopefully that answers your question.
I think so. We have one further question, and it is, how do the heat exchange rate, how does the heat exchange rate compete with the frictional heating. Is this a valid thought?
Can I share my screen for a second? Am I allowed to do that?
I don't see why
Yes,
not.
Lindsay, you can do that.
Okay, cool. So I'm gonna like tangentially answer the question, and like I'm assuming you guys can see. Can you see this formula, or can you see like a thing that has like a password and a user ID? Where are you guys looking right now?
We can see it. Well, now we can't.
Oh, now you can. Okay, now you can.
Yep.
Cool. And I just have to scroll over a little bit. This is what happens when you have dual monitors. There we go. All right. So that's kind of like an interesting question because like both are important, but they're important in different ways. So right here, what I have is the ion energy equation for in the F region ionosphere. And like this is kind of related to those equations that I had on slide 8, where I had a VI minus VN squared term and a TI minus TN term. So here, this is just like heating, looking at ions, just to keep things simple. So here we have the ion temperature, here we have VI minus VN squared, and here we have TE minus TI. And also we have MM and MI, and you can ignore this phi and psi that are over here. But basically, like what you can see is that like if you have a velocity difference between like ions and neutrals, you'll get like this squared term that'll impact it and like really create like heating that you have. Meanwhile, you'll have like this TI minus TN term, which will almost like stop the ions from being like less than the neutral temperature. So all I'm trying to say here is that the heat of flow that you have within the ionosphere, like it strongly depends on like both of these parameters, but like when you have a strong flow, when you have frictional heating, that'll like quite severely change the ion temperature that you have compared to like other terms that you would have like MI, MN, or TI minus TN, just because of the squared term. Hopefully that makes sense.
Yes, it does. Thank you so much, Lindsay.
Cool, thank you very much.
All right, next, we have a couple questions for Dr. Pedatella. Dr. Pedatella, how do we tell the causality between SSWs and the enhanced PW activities?
So going back to some of the early studies on the formation of sudden stratospheric warmings, they used fairly simple models to show that they were driven by planetary wave activity. So using simple kind of linear models with planetary wave forcing, you can form the sudden stratospheric warming. So these studies, as I said, dating back to say 1970s or so, showed the sort of the formation of the stratosphere warmings was caused by the enhanced planetary waves.
All right, thank you so much for that. We have one more for you. Does the enhancement in lunar tide have any effect on the enhancement of migrating semi-diurnal tides? That's not a word I've said out loud ever.
So my assumption here is that they're talking about, or the question is related to enhancement of the migrating solar semi-diurnal tide and its relation to the enhanced lunar tide. And as far as I know, there's been nothing to explicitly study how the enhancement of the lunar tide would affect the enhancement of the solar tide. But they are both formed by a similar mechanism. So in some way they are partly tied together, you know, in terms of they're both enhanced due to somewhat similar mechanisms.
All right, thank you so much. We'll move on to Dr. Inchin. We have a question for you. Dr. Inchin.
Yes, I'm here.
Oh, cool. Why does the speed of sound increase in the stratosphere and thermosphere?
Yeah, this is a good question. So if we assume a linear regime of acoustic wave propagation and also assume that the atmosphere is an ideal gas, what is a quite good approximation, the speed of sound fully depends on temperature and composition. So now if you look at the temperature profile of atmosphere from ground to thermosphere, we will see the increase of temperature in stratosphere due to the presence of ozone layer. And at the same time, the thermosphere itself is the substantial absorber of solar radiation. And that is why we have these two increases in speed of sound in these two regions, in stratosphere and thermosphere. What in turn leads to the substantial refraction back towards the ground of acoustic waves if they are propagating from the ground level. Yeah, I hope I answered the question.
I think you did. All
Thank you.
right. Well, thank you so much, Dr. Inchin. Now we will wrap up the Q&A for this lightning session and go to a short break. Thank you to all the speakers for joining us in this session. After the break, we will hear about planetary atmospheres from Dr. Cheng Li. We'll see you all again in, I guess, 5 minutes at 5:50. Well, sorry, 5:50 Eastern, 3:50 MDT. Thank you.
Welcome back, everyone. After a short break, we will have our last special talk for the student day now by Dr. Cheng Li. First of all, thank you, Dr. Cheng Li, for being part of CEDAR this year. A little bit about Dr. Li. Dr. Li graduated from Caltech in planetary science. Then he joined the Juno mission team. He spent 2 years at JPL and 1 year at UC Berkeley. Now he is an assistant professor at University of Michigan. His interest is in fluid dynamics, spatially atmospheric dynamics. We are very excited to hear for the first time on planetary atmosphere from Dr. Li in the CEDAR. Dr. Li, you can start whenever you are ready.
Hello, everyone. Thanks for inviting me to present at the CEDAR workshop. This is also my first time presenting here. And let me start sharing my screen. Okay. I hope you're seeing my presentation, right?
Yes, looks good.
Yes, okay. So I was asked to present at the CEDAR meeting and on planetary atmospheres. I know this is a big topic and it's very hard to choose what to present because it certainly cannot be condensed into like a whole 40 minutes presentation about the whole aspects of planetary atmosphere. And therefore I try to choose a topic that's both old and both new. And the topic is Jupiter's Great Red Spot. Jupiter's Great Red Spot is an older topic because people know it from the first time when they have a big telescope and not so big like a backyard telescope. They can use their telescope to see Jupiter, and then the first thing that they can identify is that there's a big spot in Jupiter's atmosphere. But it is also a new topic, because there's a lot of things we don't know about Jupiter's Great Red Spot, and thanks to the Juno mission, now we have a better picture of the structure of the Jupiter's Great Red Spot itself. Okay, so let me proceed with my presentation. And it happens that we have an animation of the motion of Jupiter's Great Red Spot, and it comes from the Voyager mission. And you can see that this is the picture taken by the Voyager spacecraft when the spacecraft is approaching Jupiter's atmosphere. And you can see that the Great Red Spot is a dynamic field. It is a vortex in a planetary atmosphere. You can think of that it's a big anticyclone or a giant vortex, a giant hurricane, like something like that on Earth. But the Great Red Spot is also an evolving field. And we have continuous observation of the Great Red Spot for about 20 years. And you can see that the top picture is the picture of the Great Red Spot in 1995. And then that's in 2009, and that's in 2014. And from these spending about 20 years of observation, you can see that the Great Red Spot itself is actually shrinking. So in 1995, the Great Red Spot looks like an oval with its east-west direction. It's about twice in size compared to the north-south directions. But now the Great Red Spot is kind of more spherical shape, and it is still shrinking. We have no idea whether it will disappear or not if we extrapolate the shrinking rate of the Great Red Spot, and we can find out the Great Red Spot will disappear in about like 40 or 50 years or so. But the shrinking will stop. It will create a hiatus phase. So we have no idea that whether it will disappear or it will keep the same and will stop it somewhere. Okay. There's a lot of unknowns about the Great Red Spot. For example, the most basic question is how did the Great Red Spot form? And unfortunately, we don't know exactly why, but there are a lot of research that's focusing on the formation of the Great Red Spot. And the typical model that to simulate the formation of the Great Red Spot is made by Downing and Inchin. This is a shadow water model. And the shadow water model means that we model the whole atmosphere as a single layer. This is because Jupiter is such a vast planet and the scale height of the atmosphere is very small. And therefore, if we neglect the vertical structure of the atmosphere and condense everything into one single layer, then that forms a shadow water model. So this model specifically start with a zonal jet, and they start with a jet speed that's more or less similar to the observed jet speed in Jupiter's atmosphere. And particularly, they make those jets unstable. Unstable means that the small disturbance in the jet will grow to form vortices. And this is what you are seeing. This is t equals to 0, and now t equals 100 days. Because the jets are unstable, you are seeing that random perturbations will become to form smaller perturbations in the geopotential height field. Now you are looking at the geopotential height perturbations, and then these smaller perturbations will grow, and eventually they will form big vortices. Now at time equals to 750 days, now you are seeing 2 big vortices, and they move at their own speed. And you can see sometimes they will approach each other, and once they approach each other, they actually will merge into one. And then the whole system, even if they started with a symmetric jet, they started with a random perturbation of the jet, it will end up with one single vortex. So this model tells that the greatest spot is formed by a smaller one starts to eating out the other smaller vortices, and then eventually itself that's cleared all vortices at its latitude, and that's the remaining one, the winner, is the greatest spot. So, and a basic understanding of the dynamical structure of the greatest spot is illustrated by this cartoon. The greatest spot itself is embedded in an anticyclonic sheared zone, and then itself, the north part of the greatest spot actually extruded a little bit into a neighboring belt. Then the wind field of the greatest spot has been measured by tracking the cloud velocities mapped from Earth. And then it's actually has a very peculiar wind field because the wind field of the greatest spot actually has a very quiescent center. It's divided into 3 pieces. The north part of the greatest spot, you can see that the wind field actually increases more or less linearly with the latitude. And then the center part of the greater spot is very calm. The velocity is almost 0. And then the south part of the greater spot increases again linearly. So itself is divided into kind of 3 pieces. The first time when people saw the greater spot, we got suddenly very curious about its vertical structure, its internal structure. And this is because we know a theorem in fluid dynamics from 1960s. And the theorem is called the Taylor-Prodman theorem. The Taylor-Prodman theorem states that in a fast rotating fluid, and if you place an obstacle at the bottom of the rotating tank, and this obstacle has a limited height, it does not span to the whole height of this rotating tank, but it will end up causing flow that's going around the obstacle as if the obstacle extended through the whole column of this rotating tank. And the rights, and I'm going to show a movie from the UCLA Spin Lab to show the Taylor-Prodman theorem. You can see now this is a rotating cylinder, and then this part is the solid obstacle. And even if the solid obstacle is only placed at the bottom, the top flow will go around the region that the obstacle is, as if the obstacle that extended the whole column. This is a property of a fast rotating fluid, and it is called the Taylor-Prodman theorem. And if we use this theorem, we might expect that the greatest spot we saw is at the surface, but it may be a manifestation of a bottom bottom object. So there may be some topography in Jupiter's fluid atmosphere, and we don't know that. So we are very curious about the internal structure of the Greer spot. And then some people like Phil Marcus put together a cartoon to illustrate the expected internal structure of the Greer spot. So on the left, you are seeing a cold core top, and then there's a mid-plane where a lot of cloud forms, and then there's a bottom that is hot. So this bottom fluid trying to go up, but it's kept by a cold core, so that the whole thing is kept in space. And then it's like the pot on the stove, where the stove is heating from the bottom, and then the top is cold, and therefore the whole thing is confined in space. So people have been speculating about the structure of the Greer spot for years, but without a clue, without an instrument to actually measure it, we cannot say for sure that's what's the internal structure of the Greer spot. And that comes the Juno mission. The Juno mission is the first mission that goes inside the radiation belt of Jupiter. And it did so because it is equipped with 6 microwave antennas, and these antennas they measure the radio emission of Jupiter as a significant wavelengths, such as at 25 centimeters, at 50 centimeters, and these radiances will be blocked by the synchrotron radiation of Jupiter if you are observing Jupiter from the Earth. And therefore, you have to go inside the radiation belt and to actually look at the radiation coming from the atmosphere. And so this is how the measurement is made. And you're seeing a spacecraft spinning incredibly fast, but the actual spin rate is much slower than that. And what happens is the Juno take a very elongated elliptic orbit, and at the perigeo, at where the spacecraft is close to the planet, it starts to observe the thermal radiation from the planet at the radio wavelengths. And then the major observer in the atmosphere is the ammonia gas and the water vapor. So it is equipped with 6 radio antennas and measure the atmospheric radiation from the topmost level, which senses the ammonia cloud level, and all the way down to the bottom to about 1,000 bars. So it covers a lot of cloud layers, including ammonia cloud, including the water cloud, and has the capability to measure the deep atmosphere as well. So during the 7th perigeo of the Greer spot, we have very lucky geometry that the spacecraft go right through the center of the Greer spot. And you can see that the background is the visible image of Jupiter. And then this colored map, color shaded region is our perigeo of 7 flyby. And then the white to yellow color is the high brightness is the observed high brightness temperature, and then the black color is the low brightness temperature. So this is one channel 6, 1.4 centimeter. It senses the ammonia cloud level, and then once you get more and more, you can see that now you can see that the Greer spot seems to be more or less the same as the surroundings, but the south edge of the Greer spot is actually warmer than elsewhere. Then you can go to deeper and deeper. Now we are at 5.8 centimeter. The feature is more or less the same. You are seeing a warm outer rim of the Greer spot. And then this is 12 centimeters. At 12 centimeters, you start to see new features. So at 12 centimeter, where you sense the 3 bars, you are seeing that the center of the Greer spot is actually colder than the surroundings. And now that's at the 24 centimeters censoring the 30 bars, the cold anomaly disappears, and more or less you start to see a warm anomaly. And finally, at our longest wavelength channel at 50 centimeter, you are seeing that the Greer spot is warm at the center. So we can put together a three-dimensional map of the Greer spot in this way. That's the topmost layer is the visible image of the Greer spot. And then what you see, the white here is warm and the black here is cold. And it's the Greer spot is warm at its south edge. And then the cold is a little bit cold at the center. Then the cold anomaly gradually shifts to warm anomaly as you sensor deeper and deeper in the atmosphere. We can actually compare the observation of the Greer spot to the other perijovs that did not cross the Greer spot. So this is a busy image, and let me go through it slowly. I lay the microwave radiuses in different frequency from top to bottom and corresponding to different layers in the atmosphere. The 22 gigahertz senses the topmost layer and the 0.6 gigahertz senses the bottom layer. Then the background in the atmosphere, the perijovs that did not cross the Greer spot is shown in this blue line with green shades. Green shades represent the standard deviation of all the perijovs that did not cross the Greer spot. And then the Greer spot perijove itself is marked by this orange line. And from this curve, it's actually more easier to recognize that the Greer spot it's a complicated feature. And you can see that at the top layer, it is separated by two branches. So the south branch is warm, the north branch is cold. And then this temperature anomaly starts to decay once you go deeper into its internal structure. At this 2.6 gigahertz, you're seeing that to the center of the Greer spot is cold. And then once you go down to deeper and deeper, you are seeing the temperature anomaly start to turn positive. And if you still remember, that's the cartoon image of the Greer spot. Actually, the cartoon image is more or less correct. So the cartoon image shows that the Greer spot has a cold core at the top and then the warm core at the bottom. This corresponds quite well with observation. So here we are seeing the brightness temperature anomaly of the Greer spot, meaning that I take the the observation of the Greer spot and then subtract the background brightness temperature. That gives the anomaly. And the anomaly shows a cold core at the top, at the warm bottom, at a warm core at the bottom. But the actual structure of the Greer spot is more complicated than the cartoon picture in the right, because we're seeing a bifurcation of the temperature anomaly. The south part becomes warmer and the north part is cold. And we didn't stop it here because this picture only shows the brightness temperature. And then the brightness temperature is affected by a lot of things. Mostly it's affected by the actual temperature of the atmosphere and the amount of absorber in the atmosphere. So this is radio transfer 101. And the atmosphere emits thermal radiation. And let's represent the thermal radiation by T. And then the thermal radiation passes through the absorbing molecules. Let's say that the absorbing molecules in Jupiter's atmosphere is ammonia gas. And then the result is that the absorbed thermal radiation reaches the antenna, and we got the brightness temperature, which is called TB. And therefore, if you observe the higher brightness temperature, and it can be explained by two mechanisms. A higher brightness temperature can either mean that the actual temperature of the atmosphere is high, or it can mean that the amount of absorber is low. Therefore, we have the degeneracy of temperature and the amount of absorbing species in the atmosphere. And as a fluid dynamics, we are really care about the density distribution of the atmosphere. And the density is mostly determined by the temperature and also a little bit by the composition. But since the ammonia gas is of tracer amount in the atmosphere, it does not contribute to the density a lot. And therefore, we care about the real temperature of the real temperature structure of Jupiter's Greer spot. So this is a job here, which is a remote sensing technique to deconvolve the contribution from the temperature and the contribution from the distribution of the absorbing species. And this is, then I used an inversion technique called MCMC inversion and using rectified Gaussian process. It's an inversion technique that samples both the distribution of absorbing species like ammonia and the distribution of temperature, such that to display a grid of models and with a combination of ammonia and the temperature, and to show us what combinations of ammonia and temperature can explain the observations. Now here is just a few sample that's to show you how the atmospheric inversion is done. First, you give a random sample of the distribution of ammonia. In here, I put 3 random samples marked by 3 different colors. And then you give random sample of temperature perturbation of the atmosphere, and also marked by these different lines. But there's one constraint on temperature profile, because the constraint is that the atmosphere must be stably stratified. A stably stratified atmosphere means that the denser atmosphere must be at the bottom, and then the lighter atmosphere must be at the top. So ammonia gas can vary a lot, but the temperature itself has some kind of restrictions. So it can only vary in one direction and not in the other one. And this is where the rectification process comes in. So you propose a variation of the temperature, such as the dashed line, and then you correct the parts that's not stable. And then the eventual stratification of the atmosphere is shown in the rightmost plot. The rightmost panel shows the virtual potential temperature, and it indicates the stability of the atmosphere. And you want to see that this curve of virtual potential temperature is monotonically increasing with altitude, and this is the final result. So so you can see that the correction process comes in and produce a kind of a constant virtual potential temperature, and then this correction process happens again and again in those 3 phases. So then we can apply one parameter. This is the parameter is called sigma. It denotes how much amplitude we allow the temperature to vary, and then we can control this sigma by progressively increase the value of sigma, so that this allows us to sample the combination of ammonia and the temperature to give us a complete grid of solutions that might fit the microwave radiances. So the first step is to obtain a background ammonia concentration using the inversion method, and the background is denoted by this green line and the shaded area, and then the results of the ammonia distribution of the background is shown in the right panel. And in here you can see that this panel shows the ammonia concentration in ppm, and then this black region shows very low ammonia concentration, and then the yellow, more or less yellow region shows a high concentration of ammonia. So in this case, the background atmosphere are suggesting a layering of ammonia gas, where you can see that the distribution of ammonia is more or less horizontally layered, and with some kind of ammonia minimum at the pressure level of about 10 bars. So this may be caused by the water vapor, because water condenses at about 10 bars pressure level. So after that, we can use the same process using the same process for the Greer spot. Now you are seeing this sigma equals to 5 Kelvin, which means that we allow the temperature variation of the Greer spot by about 5 Kelvin. Then I mark the 3 lines. These 2 side lines mark the edge of the Greer spot, and then the dashed line mark the center of the Greer spot. Now the left figure shows the ammonia distribution. Then the right figure shows the temperature distribution of temperature. And right now you don't have the scale, so let me just showing all 3 solutions so that you can see the actual scale. And on the on the left, you're seeing kind of 3 solutions and ordered by sigma t of 5 Kelvin and 2 Kelvin and 1 Kelvin. Sigma t equals 1 Kelvin means that we place a very strict constraint on the temperature distribution so that we don't allow the temperature to vary a lot, and therefore all signals coming from the distribution of ammonia. And then sigma t equals to 5K means that we give temperature more freedom to vary. And to the right, you are seeing the distribution of temperature anomaly. And what's most striking result is that you are seeing the north part of the Greer spot is actually warmer than the south part of the Greer spot. So here, the white space shows that the Greer spot is cold to the south, and then the Greer spot is warm to the north. And you can actually compare the ammonia distribution with the previous plot. That the ammonia distribution seems to have a very enriched ammonia concentration at the north part of the GRS. So here you're seeing that this yellow contour shows an enrichment of ammonia. And then this plot compares the observed brightness temperature anomaly with the modeled brightness temperature anomaly. From here, you can see that our model actually produced the observation extremely well. And we have a general warm brightness temperature anomaly at the bottom, and then the cold brightness temperature at the top, especially to the north part of the GRS. And then we find an extrusion of the cold anomaly to the south part as well. It's very illuminating if you compare the background ammonia with the ammonia gas inside the GIS. As I have said, that the background ammonia of the GIS is more or less horizontally layered, but the ammonia inside the Greer spot is kind of vertically layered. So, which means that the GIS may be a very rigorously convecting system. That convection can bring ammonia-rich air from the north part, and then it may sink to the south. And you can correlate this picture with the next one. This next one shows the temperature anomaly of the GRS. And then you can see that this picture, that's a rising branch in the north and a sinking branch in the south, correlates very well with the temperature graph. The temperature graph here, we are seeing that there's a warm temperature anomaly, and that indicates a rising motion, and especially the top parts of the graph showing the stratosphere. The stratosphere is a layer with high static stability, and then you are seeing a higher temperature anomaly, but actually convection. If you bring air from bottom to the top, the adiabatic expansion will make the air cooler. And here you can see that this part more or less indicates the adiabatic expansion of the air parcel, and therefore this air parcel is colder than its surroundings. And to the south, you are seeing a kind of adiabatic compression of warm air of the warm air at the top to the bottom, and then in this case, you're seeing kind of adiabatic warming of the air parcel. So this rising branch in the north and the sinking branch in the south completes the meridional circulation of the Greer spot. So previously, people think the Greer spot as an axisymmetric rotating oval, but now we have seen that the Greer spot actually has its internal dynamics. It may have a meridional circulation that rises from the north and sinks to the bottom. And this picture has been more or less identified in 1997 by a computer simulation of the Greer spot, although this is a hydrostatic model, so it does not really resolve the vertical motion of that. But actually, this computer model, now you are seeing an isosurface of temperature anomaly, has shown that this north-south asymmetry of the Greer spot. And okay, then the take-home message of this talk is that the Greer spot looks like a pot on the stove. It is warm at the bottom, and then it's cold at the top. But in addition to that, the Greer spot shows a north-south asymmetry. Its north part is colder, and then its south part is warmer. As a summary of what do we do in planetary atmosphere. So basically we do three parts. We do observations, and then using the observation, we do the inferences, and then we do some modeling to explain the features we have observed. Okay, so that's all. I've spent 30 minutes. Thank you.
Thank you, Dr. Li, for such an interesting and cool talk on Jupiter's red spot and all the physical mechanisms that you study. So we have some questions for you. Okay, so the first question is, Dr. Li, you may have mentioned it, but why is the great red spot red? Do you anticipate there being any other red spots in the future since there are storms?
Yeah, that's a good question. And actually, the gray red spot is a misnomer. It's not red. It's more or less orange shape. It's more or less orange colors. And people have done studies on it. And it's due to the photolysis of ammonia that interact with organic particles in the atmosphere to make it orange color. And people have done some laboratory experiments which shining UV on ammonia gas and on some of the hydrocarbons. And I don't remember which, but something like acetylene. That's acetylene reacts with ammonia that can give it a little bit orange colored. And also phosphine is another important species to give the color of the gray red spot. So then it's actually different spot has different colors, and we don't know why. It's probably due to that the convective strength in different spot is different. So the gray spot may have a very strong vertical convection. We can see that from the distribution of phosphine, because the phosphine is mostly enhanced in the region of the gray red spot. So the other spots, they kind of a little bit different in color, and this may indicate that their vertical convective strength is different from the gray red spot. We can actually use the coloring to study the vertical motion. Yeah.
Interesting. Okay, so the second question is, do we understand why Jupiter can host red spot and not other planets?
We don't yet understand. And Neptune has a spot, it's called the dark spot. And also there's only one gray spot in the southern hemisphere. There's no red spot or no spot in the northern hemisphere. And it happens that the planet does not like symmetric distribution. And Earth is asymmetric. Earth has more land in the north and more ocean in the south. This applies to Jupiter as well. So it's most interesting to see that ammonia distribution is very asymmetric in terms of north and the south. And so I think the planet may have two choices. One choice is to completely get rid of the spot and like what's in the north part. And the second choice is to have the gray red spot. And so we don't know why it chooses this configuration. It's just maybe just a flip of a coin.
Oh, interesting. All right, so another question, Dr. Li, have there been any efforts to map Jupiter's gravity similar to geodesy for Earth? It might be interesting to see what the gravity field looks like under the great red spot.
Yes, we have done that. The Juno spacecraft have a gravity instrument to measure the gravitational perturbation of Jupiter itself. So, but it is hard because the gray red spot is a localized field, and therefore the gravitational perturbation is mostly sensitive to lower J's, like J4, J6, J8, and you need to go to incredibly large J number to actually measure the the gravitational signal of the Greer spot. But we have done that. So we have been measured the J's of the Greer spot. And then the conclusion, more or less, is that the Greer spot is not a very deep signal. It's more or less confined into the upper about 500 kilometers measured from 1 bar region. So it does not extend all the way to the core. If it does, we can see a big signal, but we didn't see that. So it must be kind of a shallow feature.
Okay, another question, Dr. Lee, is the mechanism for the differing temperature with altitude subject to debate? Are wave phenomena considered? Are wave phenomena considered just similar like Earth's summer mesosphere being colder than the winter due to wave effects?
So I think yes. Well, okay. So 2 questions. First of all, we have measured the latitudinal distribution of Jupiter, and then the latitudinal temperature distribution of Jupiter. So the general consensus is that Jupiter does not show a strong latitudinal temperature variances. And however, this does not mean that the temperature differences with respect to latitude is not important. There needs to be a non-dimensional parameter to describe whether the temperature variation is big or not. So on average, we have seen that Jupiter's temperature at the 1 bar is on average 166 Kelvin plus minus 2 Kelvin. But it's indeed this plus minus 2 Kelvin, even though this 2 Kelvin is small, that gives wave phenomenon on Jupiter. And this wave phenomenon will accelerate and decelerate jets that causes the alternating jets on Jupiter.
Thank you. One last question. What is a planetocentric latitude?
Okay, thanks. This is a kind of good question. And sorry I didn't explain it. And there's 2 coordinates, the 2 coordinate system. One is called the planetographic coordinates, and then the other is called planetocentric coordinates. And we use 2 coordinates because the Jupiter is not a perfect sphere. It's kind of ellipsoid, and therefore the planetographic coordinate is defined by referencing to the normal direction of the geopotential surface. And then the planetocentric coordinate is defined by referencing to the angle measured to the center of the ellipsoid. So they differ a little bit. They are the same at the equator and the pole, but in the mid latitudes, those 2 coordinate systems, they differ by about 4 degrees or so.
Oh, very interesting. So with that, thank you, Dr. Lee, again for coming to CEDAR and presenting your talk. We will wrap up the Q&A session, and now Megan will end the student day with a short presentation. Thank you.
Okay, thank you.
Thank you everyone for attending the 2021 CEDAR Student Day. Como and I have enjoyed working on this day for all of you. Thank you to each of the speakers, the student volunteers, the CSSC committee, and everyone who attended today. Before I let everyone go, I have a few more housekeeping items. If you are not subscribed to the CEDAR mailing list, please do so via this QR code. Como is completing her term as CEDAR student rep, and we'd like to find a new rep to replace her. If you are interested in becoming the next CEDAR student rep or would like to nominate someone, please email either Como or myself. Again, if you would like to contribute to DEI efforts, please email us as well. And finally, students will receive a feedback survey over email later this week. Please fill it out to help us plan for next year's workshop. The CEDAR student newsletter will be published again this year. Here's the front page of last year's newsletter. This newsletter is written by the students and contains summaries and talks from the student day and written responses for the Q&A from today. Please email us if you'd like to join this effort. Thank you again to our student volunteers who help make the newsletter and student activities possible. They are Deepthi Ayagari, Zishan Chow, Joaquin Diaz-Pena, Andrew Pepper, Fan Yang, and Robert Urban. All the Zoom info, the Wonder.me info, and the QR codes are in the CEDAR agenda for your future reference. Please remember to join the Slack to communicate with everyone attending the conference. Now that Student Day is over, please join us on Wonder.me for trivia using this QR code. We hope you had a great time today and you enjoy the rest of the workshop.